Ciao Giulia, come stai? Good morning, everyone. So let us take the seat because we are a bit in delay. As you can see from the program, we have many talks today. So welcome again. I'm very, let's say, happy to see friends and to see a lot of faces that now in our third edition of AI for Oncology Congress, it became, I can say, a traditional Congress now. I am also very happy because today we started already our program with the first session, which was the poster session. And I wanted to thank everyone for participating, for coming, the participants, also the posters, but also the evaluators that they wake up in the morning to evaluate the poster session. So I don't want to take a lot of time. Just to say 2 words related to the fact that today I recommend to please to the speakers and the moderators, the chairs, to be very strict with the timing because we have many, many talks, and compared to next year, we have, let's say, designed a bit differently this year the program. We started with some educational talks, but also with use cases, because you know that one of the most important question is people are asking where we are in the practice, so we know also we have to convince people that we are also in real practice. And of saying that, I am happy again, I know that I say it two times. Let us start our work. I wanted and very happy to introduce, let's say, in this case, the head of the medical oncology department, my boss, Filippo De Bro. Every year he's here with me, believing in this new and innovation area.
Thank you, Arcela. Thank you very much to all of you to be here. I think that, as we can see, watching each other, the meeting is becoming more important and more important every year. There is more participation. You see that this program is very articulate. There is a lot of topics, a lot of issues to be discussed. My recommendation is that to use at the best our time. So try to be very synthetic in the presentation and have all time that we could have discussing even during the pause, the coffee break, and the lunch, because that is the moment each one-to-one discussion to improve more our knowledge about. On my point of view, this is a very interesting topic. I bet a lot on Arcela, and we, with Professor Apollone, we built up a whole program for the Institution for AI. So we strongly believe in it. Also, if probably for an aging problem, is something more difficult for me to understand that for most of you that are very young and digital generation instead of mine that is still the old style. But anyhow, I think we will, actually we count on you, because your work is going to, I guess, to improve the way of practice medicine or practice science, improving everything we can improve in terms of knowledge, using a methodology that is easier and quicker, and also taking advice from technology without, I hope, losing control on technology. So this is my introduction, and it's my pleasure to introduce Giovanni Apollone, who is our scientific director, for his comment.
Yes, thank you very much, Filippo. Welcome again also from my point of view. Thank you very much for being here and for the participation in this very important meeting, today meeting. I think that it will, given the program, it will be a very good opportunity to share our experience, expertise, and empirical data that we collect in our everyday activity, both in clinical practice and research. No doubts about the fact that it's very important to organize this meeting because there is a pressure about the utilization of artificial intelligence tools, both in clinical practice and research, from drug discovery to clinical research, clinical studies, and so on. I think that I have just to conclude a warning. My warning is that we have to use our human intelligence to use at the best the artificial intelligence. Because I have a very few warnings to give you, I will give you 3 keywords about my warning that are actually based on some personal experience about artificial intelligence. You know this is a Kindle. Kindle is a way of downloading a book in any languages, and I use it when I'm traveling, prefer to have Kindle than a paper book. And a very few days ago, I downloaded a book regarding science fiction. I love science fiction. I read it. It was a good book, book, but in some part of it, there was a very strange translation, let's say. The original language was German. I don't read German, so I have to translate it out in English and Italian. It was translated in Italian. And the reason why I feel something strange was last part of the acknowledgement written by the author that said, thank you very much for downloading and buying my book. Probably you find some part of it just a little funny, strange, because in order to have it in the European market, in all languages, I use artificial intelligence tool. I don't quote which one. And the first reason was the time. In this way, we will have the opportunity to read it, to have it in the 30 different European languages. And the second reason was that in this way I was able to fix the price lower than in other situation. So my warning is quality, quality, and quality. Because the utilization of artificial intelligence tool will accelerate everything. We have to work on any time we apply it to make a reasoning about the added value, but also about the quality of the results. I am not here to say that any artificial intelligence tool should be evaluated by a formal health technology assessment. But please pay attention to the quality of results, because we need quality. We do not have to make any discount to quality. Thank you. Now, it's my pleasure to introduce to you our brand new General Director that started this activity very few months ago. We are working together in several fields, trying to solve the problem that the big institution like this one has to afford every day. And we are working together also regarding the introduction of artificial intelligence tools in clinical practice and research. We are working together. Thank you very much, Maria Teresa.
Thank you very much. Oh, sorry. I'm very proud of our job because it's a new way to live medicine and science. I start to study artificial intelligence, but there is some problem open, and we have to improve our culture about it. There is a lot of data, but we have also organized data and think about quality and the ethical problem. Because if you speak about artificial intelligence, you have to think about also ethic data and how collect data, how storage data, and so on. There is we have to plan in our institution with you a new way to improve our culture about it. And so I am very interested in this meeting. I hope to participate and give a contribution for your job. Thank you very much.
Con piacere introduco oggi Pietro Auleta. It's again a pleasure to introduce Pietro Auleta from Patient Representative of the Association of Lung Cancer Patients in Italy.
Ladies and gentlemen, in the name of the IPOP Association, IPOP stands for Insieme per i pazienti di oncologia polmonare. It's a pleasure to bring the welcome and the best wishes of the association to you all. I see that the number of people is increasing year over year. This is the Artificial Intelligence for Oncology 2025 conference. IPOP, through the personal and volunteer commitment of its members, which are patients and caregivers, pursues projects and activities which are beneficial to patients with lung cancer. We strive to be a reference point for the patients and their families, to share personal knowledge, personal experience, bring together scientific information, promote patients' involvement and an active role in the cure and treatment of lung cancer. Also to increase public opinion awareness about the need of patients with lung cancer, and to foster the early detection and prevention of lung cancer. The use of artificial intelligence-based methodologies in all fields. I'm not a doctor in medicine, I'm a doctor in engineering, so I know about artificial intelligence in other areas. Is a big tool to make things happen much faster and to make some things happen which would not happen otherwise. It will improve diagnosis, it will improve the cure and the treatment of complex illnesses such as lung cancer. So it deserves our full support. It's raising hope and expectations among the patients, and therefore on behalf of IPOP I wish you all a knowledge-rich and fruitful conference this year. Thanks.
Thank you very much. Now it's my pleasure to introduce to you Dr. Monti, that is the president of the Regional Committee Board regarding family, housing, and social. So I think thank you very much for being here, and the floor is yours.
Thank you very much and welcome here in Regione Lombardia. Regione Lombardia is the biggest region in Italy, 10 million inhabitants, and I think the most important region for health in our state. So thank you to be here. Thank you to Istituto di Tumori, one of our most important research hospital in Italy. In Regione Lombardia, we have 7 out of 10 top research hospital of Italy, so it's also a place of research, of health. So artificial intelligence is a great topic. We were in UK last week. I'm also executive board member of our drugs agency, IFA. We were in UK just to talk about innovation, and artificial intelligence is really one of the most important topics. So thank you very much. Thank you to be here in Regione Lombardia, and we are really proud of your work. So thank you for the people that are hosting this Congress and all the organization. Thank you.
Thank you. Okay, thank you very much. So we are in perfect time, let's say, and I'm very happy to invite the chairs for the next session. Thank you.
So, good morning, everyone. My name is Sokol Costa. I'm associate professor in distributed systems and cybersecurity from the Aalborg University, located in Copenhagen, Denmark. And it is my pleasure to moderate this session together with Laura, and last minute change with Francisco as well, who will also be the first speaker, and I will introduce Francisco later. But maybe Laura, you can introduce yourself.
Good morning, everyone. I'm Laura Mazzeo, and I'm a medical oncologist. I work here in Istituto dei Tumori, and I'm also a PhD student in bioengineering. So let's introduce.
Hi. Yeah, hi, I'm Francisco Sanchez Vega. I'm a computational oncologist at Memorial Sloan Kettering, and this is my third year attending this meeting, and I'm really happy and very grateful to be here.
So, Francisco, as he introduced himself as well, he comes from Memorial Sloan Kettering Cancer Center from New York in the US. He's an assistant attending computational oncologist, and he's also the head of real-world data analysis at the Halforsen Center for Computational Oncology. His presentation today will be based on this topic, and it has a title of Real-World Data-Driven Models in Oncology. So, Francisco, the floor is yours as a speaker now.
Okay. Great. Well, thanks of all. First of all, thank you so much to Arcela and all the organizers for inviting me to talk today. I'm going to be telling you about the work that our team has been doing in the domain of real-world data analysis in oncology, and I want to start by mentioning the definition of real-world data within the context of cancer research. Within this setting, real-world data refers to data that relate to patient health status and the delivery of health that are collected from routine treatment of these patients at the hospital. And this can involve different data modalities. This can involve clinical data, data about treatments, data about clinical outcomes, and also data coming from radiology, pathology, and genomics. For the past decade, our team has been really focusing on the analysis of real-world data in the area of genomics. And this is because since 2014, patients treated at Memorial Sloan Kettering have been getting their tumor sequenced using a targeted DNA sequencing platform that we call MSK Impact. So the idea is that when a new patient arrives at the clinic, the patient is consented, we get a sample from their tumor and a sample of blood, and we can perform sequencing of the tumor DNA, which allows us to identify alterations in the DNA, including somatic and germline mutations, copy number changes, and fusions. This data is analyzed using bioinformatics method, is reviewed by an expert, and is used to generate a clinical report that goes back to the treating physician and can help to make clinical decisions. And it can be used for other purposes, such as clinical trial matching of patients based on their molecular profile. But one of the very important aspects of this assay is that all the data that is generated routinely as part of the treatment of the patients gets deposited into an institutional database that gets updated daily. So every day, new patients get sequenced. At the end of the day, that data gets de-identified, gets standardized, and is deposited into this database with some very basic bare-bone clinical annotations, such as some standard demographic information about the patients. We also use some knowledge base to annotate the genomic variants, and all of this is deposited daily in a database that is accessible for everyone at MSK through a dedicated instance of the CBio portal for cancer genomics that some of you may be familiar with. And this has turned out to be a real treasure for translational research at MSK. So when I arrived in 2015, we were very excited because we have 5,000 tumors sequenced. As of today, we are close to 150,000 tumors that have been sequenced for around 100,000 different patients. And as I was saying, this has led to a lot of very interesting research. So there have been more than 1,000 papers over these 10 years that have been published by MSK investigators alone. This is also something that is restricted to people in bioinformatics or computational biology, oncology. These papers come from all the departments in the hospital, from medicine, pathology, surgery, radiology. And this is not something that belongs to a single person. There's been more than 600 different first authors of all these papers. Now, a lot of this data is still accessible only within MSK, but we've also made a lot of it publicly available through the AACR Genie project. So you can go to that website over there and download it and start playing with the data. Now, one of the limitations is that, as I said, the clinical information that is made routinely available is very bare bones, is very basic. So a lot of the effort that our team has been doing in recent years goes in the line of expanding that clinical information. You need to think of this as a problem that goes along three axes. We get more and more patients. These patients keep having more and more follow-up, and we need to update their clinical outcomes, their treatments, and also we want to include additional data elements. So at the beginning, when we were working with a small cohorts of 100 patients, a couple hundred patients, we could rely on manual annotation. But lately, we have really moved into the use of natural language processing and machine learning in order to automatically extract this information from the electronic health records. So the idea is that before you could ask a person, if you wanted to know if the patient had been treated prior to arrival at MSK, you could ask a person that goes into the EHR and reads the patient notes, and you may be able to decide if the patient got treatment or not. Nowadays, you can use some deep learning algorithms that go through those notes and give you a probability of the patient having been treated before or not. You can apply this to many other alternative questions like different lines of treatment, different outcomes. And this is something that has now been formalized in a recent publication led by Nikki Schultz and Justin G. That maybe some of you may have read. We've called this the MSK core data set. And here we have provided an annotated cohort of more than 25,000 patients that have reached clinical detail annotations and annotations about clinical outcomes, and can be accessed by everybody. Now, as I said, we have clinical, we have molecular information coming from targeted DNA sequencing. We are also planning to expand this to include RNA-seq in the very near future. But our goal moving forward is to incorporate the other data modalities that I mentioned earlier. We want to incorporate information from pathology that ideally will be collected routinely from all of these patients, H&E slides, IHC staining. We also want to include information from radiology, like MRIs, CT scans, perhaps even endoscopic images. And in order to interpret all this information, we are going to need strong AI and machine learning tools that allow us to perform multimodal integration. So in the end, the goal is to be able to build better predictive outcome models and also to do more efficient patient stratifications. Now, in previous editions of this conference, we presented some of the paper that has already been published. This was the first paper by Kevin Boehm and Saurabh Shah, and others that focus on multimodal integration for ovarian cancer. There was a second paper by Rami Banguri and others that focus on prediction of response to immunotherapy in lung. And more recently, there was a collaboration with the group of Yakov Kather and Omar, where Kevin and Saurabh and others built some predictors for oncotype DX scores from the H&E slides. But moving forward, we are working on a larger cohort that resembles the idea of impact, where we have a large number of patients with multimodal information. We have called this MSK Mosaic, which stands for Multimodal Studies for AI-Driven Collaborative Research. And of course, being in Italy, I don't need to tell you about mosaics, and this is nowhere near as beautiful as some of the mosaics that you have here. This is a picture from Saurabh taken in Venice a couple of days ago. But in our case, the goal is to do something, is to expand the MSK impact cohort of 100,000 patients that I mentioned earlier by incorporating this detailed clinical information and also incorporating H&E slides. So once we have this, we can start building embeddings in the space of histology. We can start building embeddings in the joint space of histology and genomics. This is an example of what the pathology-based embedding looks like, and you can see that the different tumor types segregate nicely. I won't go into a lot of detail about this pan-cancer analysis because my colleague Kevin Boehm is giving a dedicated talk tomorrow, so I invite you to be there at 2:20, and he will provide much more details about this large pan-cancer effort. But I want to show you two use cases where we are using this data to augment other existing projects in specific cancer types. The first one is focusing on rectal cancer and response to neoadjuvant therapy. So a couple of years ago, we published this paper in Nature Medicine where we were trying to build predictors of response to neoadjuvant therapy in rectal cancer. These are locally advanced rectal cancer patients that receive neoadjuvant treatment. Some of them have a complete response, some of them don't. And we were trying to build predictors of who will respond. One of the most informative features that we found was related to the immune profile. There were some immune hot tumors that appeared to have very high rates of response, about 50%, and we thought that it would be great to be able to identify those in the clinic. Now, at the time we did this study with 100 patients with bulk RNA-seq. We've done some follow-up studies where we've done IHC to identify CD8 high, PD1 high patients, and we've seen that there is indeed a very strong correlation with response, where the immune hot tumors are responding much better than the immune cold. Now, one of the limitations for us is that all this very big cohort of patients that have MSK impact don't have immune profiling, so we cannot really tell much about their immune profile just from the targeted DNA sequencing data. So recently we have Marta Ligero from the cath lab that came to our group, and she worked on developing some deep learning models that could estimate immune infiltrates from the H&E slides. She trained those models using data from TCGA, and then she deployed them on our cohort of patients at MSK. She saw some relatively good correlations for different markers, including some specific hallmark pathways, immune signatures, and genes involved in immune checkpoint inhibition. And for example, this is the way that the correlation, this is what the correlation plot looks like for the epithelial mesenchymal transition variable that was the top scorer. This is what she was getting for cytotoxic cells, and when we use this information to stratify our patients, we see that there is indeed a nice correlation where the patients that have a high immune infiltrate are having higher response rates to neoadjuvant therapy than the patients that have lower immune infiltrate. The second case that I wanted to show you is related to lung cancer. I thought that this would be relevant for this conference. So a couple of years ago, we had published a paper where we analyzed the association between genomics and underlying histologic subtypes in lung adenocarcinoma, where we were comparing the tumors that have a strong lipidic component versus acinar, papillary, micropapillary, or solid. And this analysis was based on 600 patients at MSK that had stage 1 to 3 lung adenocarcinomas and had been manually annotated. So because we have the genomic profile for all of those tumors, we were able to identify differences in the occurrence of some driver alterations, like TP53, EGFR, RBM10, and others. We also saw differences in the tumor mutational burden between the lipidic, the acinar, papillary, and the micropapillary solid group, and differences in FGA. And this correlated with what we would expect in terms of aggressiveness of these tumors. Now, within the context of multimodal integration, we have started to build some tools in order to be able to automatically annotate our samples based on the H&E slide. So we got a set of tumors that have been manually annotated, around 1,200 tumors. We built some classifiers using deep learning and some pre-processing tools for these H&E slides. And now we have an algorithm that can predict the percentage of the different histologic subtypes in each one of these tumors. And this is something very interesting for us because even though we only have manual annotations for 1,200 patients, we can now go and deploy this at scale and annotate several thousands of patients that have MSK impact data. So once we get those scores, we can use them to define a general grade using the standard rules from pathologists in lung cancer. So, we can divide it into good, moderate, or poor differentiation, grade 1, grade 2, and grade 3. And this is what the confusion matrix is looking like for this problem at this point. So you see that there are still some grade 2s and grade 3 that are getting confused by the algorithm, but it's very unlikely that the algorithm will call grade 2 to a tumor that is actually grade 1, they will call it grade 3 to a tumor that is grade 1, or the other way around. The off-diagonals are very small. So we plot the recurrence-free survival. This is recurrence-free survival from time of surgery for all these early stage lung tumors. The plots that we see from the pathologist provided results and the AI inferred labels look very similar. And what we think is promising and it's interesting is that if we focus on the tumors that were classified as grade 3 by the pathologist, we can see that there was a set of tumors that were classified as grade 1 or grade 2 by the artificial intelligence who actually were having a better disease-free survival than the grade 3. This also happens the other way around. If we look at the tumors that were inferred as grade 3 by the AI, there were some tumors that were classified as grade 1 or 2 by the pathology that were actually also doing better. So you could think that there is some strategy where we could take the consensus. The ones that were called grade 3 by both the pathologist and the AI are the ones that are really doing worse. So we think that these are promising preliminary results that can help pathologists maybe refine their assessment. We are, of course, not trying to replace any of them, but this can be helpful for them to reevaluate their calls. And we are very excited about this because if this tool works, that means that we can apply and deploy it in the rest of the impact cohort that has right now probably 10 or 12,000 tumors that have already been sequenced. So just to sum up some take-home messages from my talk, I hope I've shown you that we have a very interesting multimodal real-world data cohort at MSK with clinical, genomic, and imaging data. We are using artificial intelligence and machine learning for two main purposes. One of them is automatic annotations of clinical histories, so we can get these annotations at scale. The second one is for multimodal integration of different data streams and data modalities. We're still in the early days, but we have some exciting preliminary results and many possibilities ahead. And we are always happy to collaborate and explore ideas to work with you guys, so please do not hesitate to reach out to us. So in terms of acknowledgement, this is of course a big team effort. We have a team that has really focused on the multimodal integration part, but we also have an engineering team that has made it possible to work with hundreds of thousands of H&E slides. We have a team that has really focused on the extraction of clinical data. And we also have several collaborators outside of MSK that we wanted to thank. We also want to thank our funders and people who have provided support for this project. And more generally, I want to give a big thank you to the Halvorsen Center for Computational Oncology, which is a great place to do this type of translational research. And yeah, happy to answer your questions. Thank you very much. Thank you, Francisco, for your presentation. And we have time for one or two quick questions. Oh, later. Okay, later. Thanks, Francisco. Yeah.
Thank you. It's a real pleasure for me to invite next speaker, Dr. Leonardo Provenzano. He's a dear colleague and a friend. He's a very good medical oncologist in breast cancer, and also is doing a PhD in bioengineering. So thank you. He's talking about Apollo 11.
Okay, thank you. Thank you, Marcela. Thank you, the scientific committee, for the invitation and for the presentation. So now we'll see a practical real-world application of this data-driven model in lung cancer. Is probably as probably most of you knows, the Italian healthcare is characterized by a real heterogeneity in terms of type of institution, facilities, and also distribution in the national territory. And as a consequence, this fragmentation in data collection and among centers, and often data remain unused in small peripheral centers. And even when it is possible to retrieve this data, a really great amount of ethical barriers occurs, and this, as a consequence, can slow down the research, and in particular the academic research. And this is really in contrast to what it happens in clinical practice when new drugs are available day by day in our oncology practice. To overcome these barriers, we established the Apollo 11 framework. It is coordinated by Dr. Arsela Pelai, which is the first data-driven model application in Italy on lung cancer. And it encompasses the collection of real-world data from our patients, medical images in terms of radiomics and digital pathology, and also tumor materials from patients and other biological materials that are collected for prospective patients. But the novelty is about the decentralized platform, since the data are collected locally and stored locally and shared with the center just to do the analysis. Well, the analysis were conducted with AI framework. But now let's see in detail which consists this workflow. In particular, there are some aspects that are important for the implementation of a data-driven approach. In particular, a broad inclusion criteria can allow us to include patients in subpopulation of patients that are usually neglected from clinical trials. And also the use of a dedicated REDCap platform can not only allow the collection of clinical data of patients, but also the annotation of the biobanking. And this is important because if we want to retrieve a query from the patients, we can just know which is the possibility in terms of samples collected. And about samples collected, as we saw before, there are, it is provided for the prospective patients the collection of numerous type of blood and biological materials, and they are conducted with an harmonization and a standardization in terms of time of collection, but also in terms of quantity and quality of collection. And another important aspect is about the ethical barriers, as we saw before, and the federated learning will be adopted in order to avoid the sharing of raw data. In this sense, the federated learning allows us to share data, centralized data, but not the raw data, but just the embedded data. so without privacy concern. Finally, the final aim is to find multimodal predictive models specific to the task, and the comprehensive model, as we saw in literature, allow us to obtain higher prediction performance and therefore higher clinical applicability. This is the centers and data with the cutoff of February 2025, with 20 centers that are active for recruitment. And as you can see, the data and samples collected are heterogeneous, but please consider that there is an amount of patients where all the omics are collected. So this is a really treasure to do the analysis. This is the core of data-driven models for lung cancer. As you can see in this slide, there is no pre-specified sample size calculation, but the collection of data is updated, is continually updated, and it can allow us to permit some clinical query and translational query from internal and external center. When a clinical and translational query arrives to the steering committee, it will be evaluated independently, and scientific proposal can be implemented. In this sense, when the query is from the internal centers, the federated learning framework allows to share embedded data, but when the proposal can come from external center, and this is possible, we will leverage the use of synthetic data to share also outside the consortium. And this is the basis for data-driven research for precision oncology. This slide just to underline the fact that this is our website, and how much is important the patients and local oncologists' empowerment to make the model trustworthiness and applicable. These some examples of some results that we obtained from the Apollo 11 dataset. This one of the first analysis was presented in the European Lung Cancer Congress by Dr. Miskovic, and this is a classification task. We wanted to predict the probability of long responders with overall survival more than 24 months in non-small cell lung cancer patients treated with immune checkpoint inhibitor. The analysis was tuned to have an high sensitivity of the positive class, so the long responders, and as you can see, the accuracy in terms and the AUC was nice. But we can also improve these results with the use of multimodal data, as we saw before. In this case, the clinical values, lab results, but also immune profiling, peripheral immune profiling, and radiomics to predict the probability of early progressors, so the probability of progress before 6 months. And here you can see the results in terms of 5-fold cross-validation with the multimodal AI framework with some performance that exceed 0.8. About another application is about the foundation model. So the use of foundation model to perform radiomics analysis on our dataset. In this case in particular, we take advantage of the RadImageNet. It was pre-trained to the radiomics models. In this case, we predict the probability of overall survival more than 6 months in 360 non-small cell lung cancer patients, again with accuracy even with just one modality. And just before concluding, this is the automatic structuring of retrieving of features from electronic health records using LLM. This is conducted from our group. And this is a clinical unmet need, since we want to predict, to extract automatically some features from standardized electronic health records. And in this case, we use the pre-trained models to predict some features of patients with EGFR mutated non-small cell lung cancer patients in the Apollo 11 trial. The accuracy overall was nice and exceeded 0.9 in terms of AUC for some subgroups, for example, brain metastasis and bone metastasis. So I'll conclude just to remind you this important congress. It will be an important opportunity to all of us to meet again. And I want to like to thanks all our group in Lung Cancer Group and the IO Lab. So thank you.
Thank you, Leo. So we have time for the discussion. If someone has any question.
Yes, I would invite both speakers maybe to stand at the microphone so that we can accept the questions in the meantime.
Yeah.
Thank you.
Good morning. First of all, congratulations for the presentations and the experience that you've brought us. I've got a question for Francisco. And since you've been curating the data from 2015, if I got it correctly, so how can you cope with the ever-changing NLP and LLMs algorithms? I mean, do you train the algorithms over and over as soon as the technology delivers new models, new AI models, or what?
Yeah, thank you. This is a great question. And in fact, I must clarify, we've been putting together these cohorts in 2015, but it's only been for the past 3 or 4 years that we've really looked at the use of these natural language processing algorithms. In this case, one of the key challenges is how to get a good training cohort. So the way that MSK court manuscript was designed, it really relied on a set of manually curated cases that were annotated by the GNA-BPC consortium. So there were around 3,000 cases where a human went and extracted all this information, and that's what was used to train the models. So that's based only on data that was processed in the past 3 years, even though it includes data going down to 2014.
So you adopted supervised algorithms?
Yes, in that case to train the model, yeah. And then it was deployed on the larger cohort.
Yeah, and then the second question comes, sorry, I don't want to take. And the second question is, you talked about multi-omics data being wrangled, right? How do you cope with the manual annotations, the bioinformatics always? How do you cope with it?
Yeah, that's an excellent question, and that's a whole project on its own. So also around 2014 and 15, when I arrived at MSK, there was this whole project that started that we call OncoKB, the knowledge base for oncology that can tell you if a mutation is a driver or a passenger or a variant of a non-significant. It also includes a lot of annotations regarding clinical actionability, which alterations can be targeted by specific drugs. And that's something that has taken years and a team of maybe 20, 25 people, so it's not trivial at all. And that's really focusing on the DNA. Now, if we want to move to the RNA, we'll have to do a lot of additional work.
But apparently the RNA can be a little bit simpler, apparently. According to the DNA, as far as I experience at the European Institute of Oncology are doing. Because we are wrangling also RNA-6 data out of the tests. But thank you so much. Yes. So we are hitting the same problems, I guess. Okay.
Hello. Is it working? Thank you. I had a question for Leonardo. It's very simple. Very cool project. I can guess the amount of dirty work that it takes to build up this kind of system. I was just wondering whether there are any plans to extend this to other types of cancer and how far you are into that.
Okay, thank you for the question. Of course, this is just a model that can be applied, of course, for different type of cancer, and for sure we plan in the future to do this, and so please contact us to further collaboration.
Okay. No, I can add because this is a good question. So also in the paper that we submitted, we highlighted, let's say, 3 possible ongoing works and ongoing future directions. So For example, in Italy, we are considering and discussing with the scientific director of the Alleanza contro il Cancro, which works and focuses the biggest network in the cancer centers in Italy, which involves different types of cancers, in order to endorse the Apollo 11 model under the umbrella of different types of cancer, and we will start with some different models, for example, in GI and head and neck, and to see how it works. However, obviously with some refinements, because we have focused Apollo 11 in innovative treatment, which means target therapy and immunotherapy, and also the longitudinal material that are collected are at different some points, so can be, let's say, adapted, but this is the first direction. The other direction is that we are also externalizing a bit the model internationally. So at this moment in Switzerland in 2 centers, in Spain, in Greece, in France and Germany. So it's very difficult, and now I will start to face the difficulties with the ethical committees, because obviously these biodata-driven models are not very simple. We have done, I think, around 120 rebuttal with the ethical committees in Italy until we obtained a national approval on the next 9 October, so which make approved in all the centers. So it's very difficult to make, to understandable that we need for AI biodata-driven model and prospective data and translation and tissue collection. So yeah, thank you.
Yes, just to add that we try to cover all the possible omics and to make the model as broader as possible. But for sure that in some refinements for specific pathology will be necessary. For example, the use of different type of data collection for specific cancer is important. For example, the collection of immune profile is more relevant for non-small cell lung cancer, of course, and less relevant for breast cancer, for example.
Thank you. We have time for more questions. Yeah. Here.
Hi there. Hello? Yeah, Surab Shah from Memorial Sloan Kettering. Arcela, thanks for organizing the meeting again, and it's great to be here. So I think that these are fantastic talks, both of you. Thank you very much. One of the big open problems that we all need to face is understanding the relationship between the different measurements that are being taken, and trying to explain why we see an improvement in accuracy when we integrate data types. This is something we've been facing for a long time. We wrote about it a few years ago, et cetera. It's still an open problem. I wonder if you could both offer some perspectives on this particular challenge, because I think it's a grand challenge in our field. We like to think about multimodal data integration, but the understanding of what is the combinatorial versus complementary effects of multimodal data is not yet understood in this context, and I wonder if you could offer some perspectives.
Just a quick comment is, in my opinion, we didn't do this now because we didn't have data to do this. So this is the right framework to collect enough data to establish which is the best way to aggregate data and which data to prioritize to collect. But for
Yes, I think this is a great point. I have 2 comments about that. The first one is that I think in some scenarios, I think we have a very good rationale for trying to combine these data modalities. For example, in some of your papers, you could think that perhaps the pathology data is going to give you a perspective more at the microscopic scale, and the radiology is going to give you a bigger view of the tumor and the anatomic location, and hopefully by integrating both, you can capture things that you cannot capture with one of them alone. That's something that we still need to really prove in the real settings. The second thought is that sometimes it may not be the case that by integrating a lot of these modalities we do better, but it may be still informative to know which modalities can be replaced by others, because sometimes some of these modalities may be readily accessible in the clinic. So if we don't really gain much by doing genomics and we can work with H&E slides that are routinely collected, that's also useful information. So yeah, those 2 thoughts.
Yeah, no, I just wanted to comment or to take the opportunity to thanks, because I didn't do it before, Pietro Auleta, that represent EPOP Association of Lung Cancer. they was the key researchers, this group was the key researchers in Apollo 11 because they designed by themselves the informed consent, the one-shot informed consent, and how they wanted to read the informed consent. So, and was, I mean, a great work also how to really integrate. So we did a working group with the patients. We explained to them every, let's say, the design, and they decided how they want to read informed consent. So this is, I wanted also to take the opportunity to say that we need to involve patients. I know that the empowerment of patients recently has been, I mean, we are doing it a lot compared to before, but we really need to involve them in the research part because they are not only the design, but the participation. I mean, so Apollo 11 was in these 4 years, it takes a lot to build the whole infrastructure. So in the last year, 1 year and a half, we started, let's say, to enroll patients, which were historical one, retrospective and prospective one. So, and they are, let's say, are very happy to participate because if they feel themselves involved in the research. So this, I wanted again to thank them for this collaboration because they will have a key role here.
We still have time for one final question from, yeah?
Thank you. I have a question for Leonardo. Just a curiosity about using RedCap for this big project. Did you use it also for imaging? And if yes, did you find it efficient to manage bioimaging?
So thanks to the question is a practical question, but we encounter in daily practice. So we use RedCap just for annotation of the presence or not presence of all the data. So this is important when one researcher do a query to assess how much data we have on that specific problem. For example, EGFR mutated small cell lung cancer or small cell lung cancer, for example. But we do not use RedCap for all the modalities, just for annotation. Okay, thanks.
There is time for more questions, actually.
Hello. Yeah. Hello. Thank you both for the presentations. They've been really interesting. And I was wondering for Francisco, maybe you've mentioned it. I just took one coffee and I'm struggling a bit to keep up. But so you mentioned that you're using the LLMs for the extraction, which is a hot topic right now. And I was wondering if this is something that you are doing with generative LLMs or something different, so that you can, because sometimes generative can be a bit controversial in terms of them tending to hallucinate and maybe extracting data that it's not really there or missing things or stuff like this.
Yes, I think actually a lot of the work that was published was even before the latest round of LLMs, so it was not necessarily very sophisticated. It was using some of these BERT models. And I think now the clinical data mining team is exploring new ideas and trying to, doing a lot of work in avoiding these hallucinations and things like that. But I think what we have so far is not even at that point. It was much simpler, more supervised training.
Nice. And if I may also for Leonardo, so I was wondering, when you mentioned the way you're treating the CTs for the representation, you mentioned that you're treating them in a 2D way. But as they are 3D, I guess you have a lot of representations, one per each slide or something similar. So maybe it's a bit of a technical question, but how do you then manage aggregating the representations of all these slices?
Okay, thank you for this important question. This was just an overview of the possible activity that we are doing using the Apollo 11 framework. And that one was just an example of using foundation model with the 2D slides. It is the largest lesion that was manually selected. So in this case, we just use this one, but again, important is to have a platform to collect more data to test how different modalities to treat this, to manage the information can have different impact on accuracy. But this is a really quite relevant question. Thank you.
Thank you both.
We have 2 more minutes, and I wanted to ask a question to Francisco, actually, before concluding, maybe. We talk a lot, and it looks like there is a lot of focus on open data, and that's very good, real-world data. And my understanding is that you also have the open database where you publish the data after anonymization. But what about open software or for reproducibility purposes? Do you do that, or what is the community doing about that?
Yes, definitely. I think that's also critical, and you know, in all of our manuscripts, we always try to include some GitHub repository where people can download the code and you can reproduce the figures. I think at least my group has not really focused on the development of methods. It's more in the analysis, but we want to make sure that all of the analyses are reproducible, and of course, I think whenever new methods are developed, it's really important to make the code accessible and open source. One example is the CBio portal. You know, it started at MSK, but it became open source, and now it's a collaborative effort across multiple institutions. So the more transparent and the more open, the better.
Nice. Thanks. Then we conclude this first part of the session, and we will invite the other speakers.
Thank you, Leonardo. Thank you.
Yes, so actually our next speaker is Claes Lundström. He's an adjunct professor at the University of Linköping, and he's also the director for the Analytic Imaging Diagnostic Arena, or AIDA project, which I'm sure he's going to tell us about. Thank you very much for joining us.
Thanks so much for the introduction, and thank you for the invitation. Very happy to be here. Very excited about the rest of the program as well. So I'm going to talk about the topic of how we really work in Sweden on a national scale to try to boost collaboration and boost all those individual groups that are working with research and innovation in AI for imaging diagnostics. So AIDA is what we're talking about. It stands for Analytic Imaging Diagnostics Arena, and I'm the founder and scientific director of this. And as you heard, I have a job as adjunct professor at the Linköping University, but I also have a position in industry as research director of the company Sectra, so that's also my declaration on conflict of interest. AIDA is about putting AI to use in the clinic, in diagnostic imaging. And we've been around for some years, and I've used the same image to kind of describe the overall mission since then. And it actually, despite all of the progress that we've made, we still have a similar situation in that it's very difficult to get AI out there in robust clinical use and providing value to patients. Those challenges are changing. We have solved some of them, but then new ones arise. And really making things work in the clinical wilderness is really tricky. The overall view of AIDA is this national initiative, national program, national arena, covering all of the country. As you see from the map, all the empty spots is where there's no people, just reindeer. And we're coordinating it from Linköping University at the center where I do my research, CMIV. But it's a national thing. It's governed by a national steering group, and it's been around since 2017. And as you can see, the partner organizations are evenly spread between academia, healthcare, and industry. And I'm going to walk you through the different components of AIDA really quickly, just to give you the overview and then conclude with a bit of lessons learned and experiences that we think we have, that's things that might be useful also in other places in the world to pick up on. So we actually have two halves of AIDA. To the left there you see the ADA program run by Caroline Bivik-Stadler, which is the community part of the thing. And then to the right we have the ADA Data Hub run by Joel Hedlund, and that is the infrastructure part of things. And actually we combine here two different logics of the Swedish innovation system. So the left part is funded by the Sweden's Innovation Agency, more focusing on societal impact and healthcare and industry, whereas the right-hand side is more in the academic setting and this national structure we have called SciLife Lab and government funds for research infrastructure. So let's start with the program part. Since we started, we have been the host for more than 100 different projects. I'll give some examples in a minute. And then a main part of this is the community that we're building. So what we had, or especially back in 2017, but still today, is a case in Sweden with a lot of fragmentation, as I understood we have here in Italy as well, with lots of smaller care providers, 21 different regions for a population of 10 million. So this means that in each place it's very small teams and you don't have that many colleagues. If you're in diagnostic imaging and interested in AI, you don't have that many colleagues in your home department to discuss with. So bringing this together in national scale, creating close colleagues in other geographies in Sweden has been a really, really important part of the ADA contributions. And this community we're building through workshops and meetings in different ways and different types of collaborations. We also have a big part that's on competence development, partly through the workshops and different seminars, but also an AI course for clinicians that's now happening for the 12th time next week. It's a 3-day course, actually going in some depth into technical AI training, etc., for radiologists and pathologists mainly. Not with the goal that they should become AI developers, but they should be able to speak to AI developers, because we need healthcare professionals to be in the driving seat of creating these innovations for healthcare, right? And then we have a specific project type, clinical fellowships, where you can also develop your competence as a care provider employee. The innovation projects we have hosted span all types of imaging. Pathology and radiology are big things, but we also welcome other types of imaging. As we see, there are lots of synergy and nice discussions coming out of that as well. And these are run by an academic group or a company, but it's mandated that they have a really clear idea about the future clinical use case, and that they have the healthcare professionals actively in the project, and then they can get partial funding from ADA to do this. What's becoming more and more important is also the evaluation piece. Now in 2017, not that many solutions were available. Now we have lots of them, especially in radiology. But now healthcare is realizing, okay, we need to deal with this evaluation and monitoring piece as well. Even though if we have a CE marked product, we can't be sure that it actually works for us. And even if we're sure that it works day 1, we need to be sure that it works on day 100 or day 1,000 as well. So we support those types of products as well. And we also had a specific initiative to try to join forces nationally for this as well. The realization that this is very burdensome for care providers, especially small care providers. They don't have the staffing, the competence to even do it. So, and also it's a waste if we repeat the same type of evaluation for very, very similar scenarios in Sweden. So the idea was to, well, let's create national AI validation platforms to do this instead. So we just concluded a project where we built 3 pilots in different areas, with VB in mammography screening being the most advanced one. And yeah, very successful in showing that yes, this can be done. So now we're working on making this a permanent part of the Swedish healthcare system, with some legal challenges, etc. But we're working on it. But also a lot of knowledge that we gained in the process. So This is very new results coming out in digital medicine on the mammography screening side, like, okay, yeah, you say that we need to locally validate, but is that really true? Well, here we can show, even in the most mature area of AI for mammography screening, even just subtle differences in data distribution between the data you have for training and calibration and the data you have for inference in your real clinic, that can have real impact on the performance of these algorithms for a number of different aspects of the data distribution that you can see there. But to conclude the community side of ADA, it's the most rewarding part of it is when we see impact happening for reals. And we have this very nice example from Halmstad Hospital that when they first engaged with ADA, they had no AI program whatsoever. So participating in the AI course was their first entry point to this world. And then through ADA events, they got in touch with vendors that they were interested in, and they have now evaluated and implemented this pulmonary embolism tool very successfully, achieved the patient benefit, and now going full circle, they are back at ADA in the AI course and sharing their experiences with their colleagues in Sweden. All right, moving on to the other side of ADA, the data hub. This is infrastructure, as we said. We just launched the new generation of these services that we call the data science platform. We're still running an older version of it since 2018, but now we are expanding in different ways. And the basic thing that we contribute here is a workspace for sensitive personal data that anybody in Sweden can use. And that's been a real bottleneck in Sweden. Individual research groups might have had, the bigger one, the stronger ones might have had these good solutions for themselves, but many of them did not have this possibility. It was a real headache for a lot of groups. And now there's a national thing where we who are specialists in this can provide these services for all of Sweden. And well, the two main things you do there obviously is to have you can store your data there either for primary or secondary storage, and then have compute embedded in the same system, so it's really no hassle to move data around. And then we are adding more and more features to these services as we speak, but it's also based on standards and other systems that already been developed for the genomics side in the European collaborations there. So it's a quite stable tech stack in that sense. And basically, the segmentation is the important thing here, right? Security-wise, you have your own secure bubble. Nobody else can see your data, even though it's in the same system. And we're basing it off a user fee model. And this is actually quite flexible in terms of who can be the customer of this. So we started out in academia and in research, but actually it's useful for anyone working with sensitive personal data. So industry and healthcare are very welcome, and they have started using it. Agreement-wise, there is the heavy agreement is on the organization level, so for a university or so, but then it's very easy to start up new secure bubbles. You just assign a PI for it, and then you can organize within that bubble as you like, and even include other organizations within that bubble. It's your responsibility. So it's a bit of evolution going on. We're in a constant flux in a sense. We started out in imaging, and that's where our basic funding was coming from, but really we have built this platform now for any sensitive personal data. So why shouldn't we offer it to anyone that thinks that it's useful? We also have this evolution going from previous generation of the system was really only for someone that liked command line interfaces, whereas we have the possibility to expand to broader services for a more broad set of users, including clinicians working with the data. And as we said, expanding to also industry and healthcare, expanding from research to any type of secondary use, but even we have discussions with healthcare provider about non-critical primary use in healthcare. It is quite interesting to have a non-American cloud these days, so that could be useful. And then also what we haven't really started to explore yet is this has been built for Sweden, but if it's useful outside of Sweden or for international collaboration, all of Europe is most welcome to inquire with us. And another part of the evolution is that we are very closely connected to the computational supercomputer efforts that are happening in Linköping University. You might not know this, but Linköping is the supercomputing capital of Sweden and one of the supercomputing capitals of Europe. So we have a long tradition there, and the last example of that is we were one of the first sites that got awarded these Euro HPC AI factories a few months ago. So we're building that, starting to build that system now called Mimer. So that's going to be dedicated to AI. We have lots of promises there on handling sensitive data and taking special responsibility for life sciences and healthcare. And this, as you can understand, merges very well with the expertise that we have at Ada Data Hub, and actually expertise that they don't have traditionally in the supercomputing side in Linköping. So we're working closely together to really scale these type of services up 1 or 2 orders of magnitude. We also do other stuff, so a service for researchers wanting to share. I would say now that we heard about the MSK core and other things, it's mostly smaller data sets, but a very useful service for a researcher wanting to share their data. We have 52 data sets out there that you're welcome to apply for a little bit of paperwork, and you can get access to it, and we've done so 300 times to research groups in 4 to 5 countries so far. So the final minutes, some take-home messages. What can you learn from what we have done? I think one of the success factors here is really embracing the triple helix thing at a very ground-up level. Individuals from these 3 sectors meeting and getting to know each other in this community is really something that pays off in the long run. We have a specific role, at least in the Swedish ecosystem. We have a very positive situation in general that AI and AI for health is really appreciated, and there is a lot of both money and funding and pressure coming from the government and from the top and from the top level of the healthcare providers. And that's great. That's a great macro climate to be in if we want to do progress here. But it's often the case that the grassroots, the individual innovators, for instance, at the care providers, they don't really see that. They don't really get access to that. The problems that they're facing every day to take those small steps to bridge the gap to clinical use of AI, they don't get help with that. So our conclusion is that we can do a lot to help this microclimate with the bottom-up support and grassroots community that ADA stands for, in complement to the top-down parts. And then we have this paradox of being both progressive and challenging the status quo, but also being very careful. So I tried to generate an illustration for this in this health data superhero going really fast, but with a securely fastened seatbelt, right? This is really, I'm borrowing an expression from Kaiser Permanente, chief of AI, that this is really innovation at the speed of trust. We cannot afford to lose the trust in what we're doing, so we need to, while also challenging status quo and making sure that everybody understands the potential, we also might very diligently need to work with these questions such as robustness and quality assurance and all those things. And then a pillar of success for us is sharing, collaborating. We're doing that a lot on a national scale, also outside of the ADA community, some of the big initiatives you see there, and also on the European scale. For instance, the Big Picture project is building a multi-petabyte database of pathology imaging in Europe for AI training. And with that, I thank you very much.
Thank you, Klaus. And it is now my pleasure to invite Daniel Tran from University Hospital of Aachen. And Daniel, he's leading the AI in medical imaging group. And I take the opportunity also to let everybody here know that we also have at least 100 people connected online as well. So we would like to thank the online people as well. And Daniel will have a presentation with title Federated Learning and Swarm Learning for Decentralized Data Sharing, HYPE or New Horizon. Thank you, Daniel.
Exactly. Thank you very much for the kind introduction, and thank you, Arcella, for inviting me. It's really a wonderful conference and a pleasure to be here. So I'm going to speak about federated learning, and it's expected to open up some possibilities, right? Because the possibilities are there, as you know now, for several years. So there's this gap between what is promised by AI, that you can really use it to classify images into all those different classes, basically the same that you do in medicine, and that can be done in almost every other category, like classifying different kinds of dogs and differentiating them from mobs. And that works really well. So it has not been long after this has become clear that medical people then soon started to use that as well. And it's actually relevant for medicine because you use that a lot. Everything that we do as a radiologist, so I'm a radiologist by training, is classify images. So I'll give you an example for breast MRI, for example. It's, as we have heard in the preceding presentations as well already, it's really important to catch if there's a cancer present in the image or not. And I can already help with that. We have seen, or what you all know is probably breast cancer screening via mammography, so via conventional X-ray imaging. And that helps, but it can't catch all of the cancers. Some are really hard to catch, especially if you have like a high density breast, so meaning that in X-ray imaging you can't really see through the breast, but there may be maybe a lot of different tumors hiding, maybe tumors hiding within the dense breast tissue. And there's actually a recommendation that you can improve upon that, so that you take those examinations which are really hard to assess and then perform an MRI on those. Because in MRI you can go through the breast in different slices. So you can 3D image the breast and then you can look for the lesions that you might have missed. And actually there's a recommendation by the European Society of Breast Imaging now that you should do this for a special subgroup of patients. So for the subgroup of patients 50 to 70 years of age, and which have this kind of dense breast meaning that you have a lot of fibroglandular tissue, less fat tissue, so it's harder to see through, then you should offer MR imaging every 2 to 4 years. And if you do that, you can actually, then you should act on this now, so I'm jumping over this, you can actually save lives, and significantly so. So around 9 lives per 1,000 women invited. So it's very attractive to do that. Now, performing an MRI is in principle straightforward. So you put the patient in the MR imaging device, you take images, but there's already the first step, which is different depending on which site you are taking the images, because each and every site in MR imaging, contrary to mammography imaging, is using a different protocol. So there are sites which use T2 images with or without fat suppression, and dynamic contrast imaging, seeing how contrast is accumulating in the breast with or without fat suppression. And there are lots, basically hundreds of different parameters that you can use to adjust the image quality in the scanner. That's a problem. It's not a problem for us as humans because we are famously very good at abstracting away. So once you have been trained at one location, say in Aachen, you can also change hospitals and go to Milano, and you will quickly adapt to the way images are performed there. It is, however, a problem for AI models, as you all know. So you can train those models at one side, and that works really impressively well, almost achieving the same sensitivity and specificity as expert radiologists. But then if you apply that to other sites, that doesn't work as well. It's a problem for imaging, because if you had not this problem, you could basically have the same successes that you have with mammography, where you actually now see the advent of AI in radiology. So actually, this study here is one of the first cases where radiologists will then actually be replaced, making the vision of Geoffrey Hinton that he proposed, I think, 10 years ago or so, that radiologists should stop being trained, almost a reality, but just in this very tiny application case, because in this study it was shown that for the double reading you could actually replace one radiologist by an AI and you achieve basically the same accuracy. It's quite nice. We would like to have that for MR imaging as well. Problem being, of course, mammography is really heavily standardized, so you have rules of how the images are to be acquired, and if it's not acquired in that specific way, you have to repeat that examination. So you have a heavily standardized imaging examination, and those images are 2D. So rather simple to make the transition from classifying mobs and dogs, now classifying breast cancer cases against non-breast cancer cases. As I hinted at, MR protocols differ quite a lot, so you can have all these different parameters, resolution changing, 3D or 2D acquisition. All those images are, of course, 3D. You could, during the examination, you usually compress, you put physical pressure on the breast to make the examination, has physical reason, make the examinations quicker. Some do it in a different way than other sites, so the images look very differently. This is, of course, a problem if you now have this, if you had all of these examinations in one place. Even then it would be challenging for AI models to extract the information. You have many different scanners, you have many different sites, as I said, many different kind of acquiring those images. So a solution to this could be federated learning. So basically you take, in this project for example, and we will hear from Oliver directly after my presentation about the Odelia project, you take the leading breast cancer centers, leading MR breast cancer imaging centers from Europe, you assemble them in the project and you ask them each to provide these cases, and what I would like to have as an AI scientist, I would like to have all these cases combined at my center then, and then just apply my AI models on a high performance computer. Ideal case. Fortunately, that's not the way medicine works. Everybody wants to keep their data, understandably. So I can't do this. I can't just train the network on all of the cases at once. I need to leave the cases on site. And the solution to this is federated learning. Federated learning basically is sending the network, instead of assembling the cases at one central location, sending the network around and training it at one site, then continue training at the next site, sending it such updated weights again to the next site, in this case, for example, University Hospital of Aachen, continue training there, and so on and so on. And do this cyclically a lot of times. That's a good way of approaching this problem, and in principle it works. There are some caveats though, or some technical difficulties, which I will go into in the next slides. So, for one, let's first look at what is needed, or what is the basic infrastructure needed. So you have a global model that you want to keep and that you want to send around the sites, but you can't just send it to the sites because there are security protocols in place. So IT is also understandably pretty tight. IT security is pretty tight. You can't just access any computer from the outside world. Ports are blocked, and you can't just send your model there, and you can't just receive a model back to your own place. You have to speak to the IT department. But basically that's what you want to do. You want to send your model weights to all these different data carrying centers, like the community hospital or the research medical center or cancer treatment center, specialized centers, and then do all of this updating cyclically until you have arrived at a model which can then easily easily examine all of these things. There are some success stories which have been published in the literature. So for example, during the COVID pandemic, everybody was more lenient towards making things happen, so you could motivate even IT hospital people to like overcome the barriers, and success stories have then, such as this one, appeared, in which people trained an AI system on predicting clinical outcomes in patients with COVID-19. And they did this on a wide variety of centers from all over the world, actually. In this case, from 20 institutions. And this model could then predict the future oxygen requirements of symptomatic patients. As you remember, back then was very like a big point of discussions. Will those patients require oxygen at some point in time? Because these places where they could sufficiently be treated were limited in each and every hospital. Now, the improvements expectedly of having access to all of this data as compared to having only access to one specific site were much better, so were high. So 16% improvement in average AUC, which is quite a lot. If you have dealt with AUCs, that's quite a significant change. And exactly what you expect as well, you get an increase in generalizability. So expectedly, when the model has seen a lot of examinations, it's easier for the model to adapt to new examinations as well, to never before seen examinations, never before seen centers as well. This has also been proven by Jakob's group, for example, in histopathology. They explored a variant of federated learning, swarm learning, in which you do not have a central server basically collecting the weights and coordinating everything, but in which the role of the central server can be attributed to each and every center, and it's actually changing, making the whole thing more secure and more like democratically accessible, so to speak. And this works in the same way. The results are basically the same as those that you get from federated learning. You get increased accuracies, you get increased generalizability as well. And the data in this study showed exactly this that these AI-trained models outperformed the locally trained models. So the big question then is, if it works, and it has been proven in those like studies, in those landmark studies, why don't we use it more often then? Why don't we use it all of the time? Now let's look back at the general infrastructure and let's go through it step by step. So the first thing that you need is, and let's look at those connections, is you need to establish a connection to a local machine learning server at the specific site where you want to like then send the model to and locally like update the model. This is hard. If you have ever tried that, if you've ever dealt with IT department in hospitals, it's frustrating, it's tedious, and it takes a long time. So you can really spend years for something which could be done in 10 minutes, actually just discussing with the people why you need it, and then discussing with other people, the data protection officer, and he's on vacation, and then you have to discuss it with another person, and that person is ill for 2 months. So it's really frustrating. But ultimately you can, I guess, overcome these things, but you need to put a lot of energy into this. Now, the next thing I want to look at is this data, or how can we prepare the data for this federated learning? Because with the conventional models, as you know, you need to, a lot of work when you develop such a model is put into preparing the data, making it like homogeneous for the training of the data. Like the model could crash if it's used to seeing DICOM images and is then presented with NIFTY images, for example, another data format. So you need to have all of the data in place and tidy it up such that the model can then actually use it for its training. Problem with this, of course, you can't really see the data on site, and that gets a big problem when the data is getting more complicated. For example, in our project, easily there are hundreds of parameters that you could gather or that you would be interested for assessing breast MR images. So are there genes, risk genes involved? What's the family risk like? That's just a tiny bit of the table that we are actually acquiring. And each and every hospital needs in this setting to have this table filled and have it filled without having any like things inside which the model which you don't account for in your algorithm. So if there's a 0 and you just told all the centers if you don't have any lesions, just put none, and instead they put 0, for example, and you don't account that for your model, for your, like in your data pipeline, that's a problem. So you're stuck with the idea of basically examining the data without actually seeing the data. You have to trust that the clinical partners do it exactly as you told them to do. Mostly they try to, but even if they try to, there are still drawbacks or still some things which can be wrong, as you can imagine. Now, one possible solution to this, and we have heard about this in the preceding presentations as well already, is that you could use large language models, for example, or the capabilities of large language models to structure the data, because most of the data, as of now, is actually in unstructured format, in long radiological text reports, in long pathological text reports, or clinical reports. But if you can use large language models to extract those models or those parameters for you and fill those tables, that supposedly works then better than to account for the variability of, say, 20 human annotators that you account or that you have to approach in 20 different hospital centers. And this is, I think, a real possibility because these large language models can actually kind of think as us humans. So ideally you have a very patient and you have a very capable thinking entity, in this case a large language model, in other cases like the humans before, which then allows you to instruct it with specific ways of accessing the data and telling it, okay, go through the databases and look for the label cancer or no cancer. I think with the recent developments of agents, that's even becoming more attractive because agents are kind of autonomously acting, and also you can, like, maybe that's a vision still, but you can in the future maybe leave them unattended and they can reason on their own what to do with the data. So the vision could be that in the end you could deploy an agent in the hospital database which has access to the data, and it could decide on its own, and more, you could even train those agents, or you can train those agents in an end-to-end fashion, which is then actually easier than to have dedicated tables which you have to fill. You just have to have this one signal at the end, like survival, optimized survival probability. So there are lots of possibilities opening up right now with the recent development. Now there's, as you have noticed, there's a third column here, and this one is privacy preserving. So supposedly federated learning is privacy preserving in the sense that you don't have access to the underlying images, so you can't extract any data. No chance of finding the diseases of someone you know or so. But that's not quite true. So with some efforts you can actually extract just from the weight updates, you can extract the underlying data with which the network has been trained. If you listen long enough, if you listen carefully enough, you will be able to extract those images. And we have tried to prove this in a study, and you can actually do that. One solution to that could be that you use encrypted federated learning, so that you basically do the calculations, the updates, without using clear numbers, but doing the whole thing in a space which is encrypted, which is not accessible even on site. This is a bit complicated, like in mathematical terms, and unfortunately also complicated in terms of computational power that you need for that. You need a lot of computational power for that. And for images, which famously are high dimensional and large data things, this is out of reach at the moment. But it can be used for like simpler things like typing, like predicting your typing pattern on a keyboard or something like that. That's actually used. If you do that though, then trying to reconstruct those images is impossible. You might even, in the end, once you have trained the model, then extract the training data. This is already like 2 years ago, ages in AI terms, in which you could ask the model in a large language model, because it's trained to always produce reasonable text, you could ask it to repeat this word forever, poem, 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 poem. And it does this for quite a while. The answer is poem, poem, poem. But at some point it gets kind of bored if you want to anthropomorphize it. Sorry, that's a hard word for me. And the model just wants to produce some reasonable text, and it does so by just spitting out what it has learned, because it has no indication of what it should answer. It just spits out some text that it has learned during the training data. And the New York Times actually used this to test if their corpus has been used for training, and it has been used, and there's now an ongoing court battle. Unfortunately, OpenAI just recently said, oh, sorry, we deleted all of the evidence, surprisingly. Well, let's come to the last part, the conclusions. So the takeaways are, federated learning can definitely help to develop accurate and generalizable deep learning models, but the practical hurdles in implementing this are quite high. So you have that IT infrastructure that you have to speak with lots of times. You have to make friends in IT. Data annotation on site might vary, and you have to take care that no information leaks, otherwise the data protection officer is always like breathing down your neck. So with this, I'd like to thank you very much for listening.
Thank you, Daniel. So let's move for the last speaker. And before, I'd like to talk with the people online, and if they want to make question, we will discuss after during the discussion. So I'd like to invite Oliver Saldagna. He's a postdoc at team lead for computational oncology and decentralized learning, and he will talk about Odelia, a retrospective analysis of MRI data for breast cancer screening. Thank you.
Thank you. Thank you so much. So I'm sorry, Oliver, just to specify again that the online people, can they just write the questions on Zoom, and then we will read them during the discussion period for all the presentations of the session. Okay? Sorry to interrupt.
No problem. Thank you so much, Arcela, for this wonderful opportunity. And it's very nice to see so many like-minded people. When I say like-minded, I think most of us are using AI in our daily lives now. And in oncology, I think it's very important to start using and driving it forward. So my name is Dr. Oliver Saldana. I am a junior group leader in Professor Jakob Kather's group, and I would be presenting a use case and all the difficulties that Daniel just mentioned. I'll be telling how we made it possible and some of the information. So conflict of interest, this project is funded by Horizon Europe, and yeah. So moving forward, as Daniel told and everyone told here, there's a lot of work that goes into setting up this consortia and making it work, and without a team it would be very difficult. So this is a small team in the subgroup of Cather Lab. We have a swarm learning team based in Dresden and Heidelberg. So we work on a lot of consortia projects for decentralized learning. So the outline of this whole presentation would be to present the use case, that is Odelia, and what is its outcome, what are the concepts, and then some of the project resources that we would have. So I think this was already presented, a nice inaugural paper of swarm learning that our group presented and published in the past, where we showed that swarm learning can be used to predict biomarkers in digital histopathology. What we wanted to show there was there's no performance drop when you combine all the data together in a central location, or you divert it or decentralizedly train it for using swarm learning. So there's no drop in performance. We showed that, and then outcome of that was the Odelia. So a small background that I would like to show is these numbers are very surprising. So if you see the sex differentiation in breast cancer, that's a lot, but also it's a leading cause of diagnosis in cancer, and also it's very dangerous, and it's going on increasing from year to year. So it's very important that it has to be addressed and detected early. And this was also shown that in screening, it is important to detect breast cancer early, and we have to screen it early and detect breast cancer in women in the right time. So what is Odelia? So Odelia is the first distributed learning, swarm learning platform where we have multiple centers across Europe. So across Europe, we have multiple centers which provide data and centrally, distributedly train a model. So here you can see these are all the centers which are part of Odelia, and we have some of the industry partners. So what is the role of industry partners? So all the research that we do has to be available for everyone, and also it is very important to make it open source. So the research that we do, if it has to be available for open source and open access, the quality of the research that we do has to be up to the industry standards. So that's the reason we have industry partners. And here are some of the key working areas. So one of the main important outcome of this Odelia was to make the whole process open source. The research that we do has to be completely open source. We try to create a software, as it was already asked, that we try to create a software for training swarm learning and make it completely open source. And also all the partners who are onboarded in the Odelia consortium are part of this training setup that we do, and then they train a swarm learning model. So how did we make it possible? So in a recent publication, we tried to train data actually real time from multiple centers. So there was data from Zurich, from Cambridge, and also open source data in Duke, which was hosted in Dresden. So we tried to predict whether there is cancer, yes or no, from breast MRI. And then we saw that the results were very promising. So somehow what we did is we trained multiple techniques on the 3D MRI data that we have. And we saw that when we externally validated these results on two independent data sets, that is the data it has never seen, data from Aachen and Athens, we saw that the swarm learning model outperformed the other models. So the swarm learning model always had a better performance, and it was significantly better from the other models that was locally trained on these centers. Some of you all might say it's not a very good comparison because the swarm learning model has seen more data, but if we didn't have swarm learning, it would never be able to see this data. So the generalizability would never have been reached. So this is one of the very nice result which we recently published. And I would like to say that another important outcome of Odelia project is we'd like to publish open source data. So the open source data, around 863 patients MRI scans, will be published soon. And also we are hosting a challenge in MICAI 2025 this year where we would try to get a best workflow or a nice model and then try to use it in Odelia. And also there is, we are hosting a workshop where this public challenge would be a sub challenge of this workshop. So if anyone is coming to MICAI, please try to register for the challenge as well as for the workshop. So if you want to learn more, I think 10 minutes is too short to explain a lot of Odelia. So all the work that we do is open source, it's in GitHub, and the website is available. You can scan the QR code, and if you have any questions, you can write to us anytime. Thank you.
Thank you, Oliver. So let's go in for the discussion.
Yeah, let's invite the speakers to stand, and then we open the floor for discussions. There is a question already.
Thank you to all the three speakers. I have a question for Daniel. Federated learning is, of course, a fantastic paradigm for solving privacy problems and so on. But is it able to deal with the same patient going through different centers? I mean, for longitudinal studies.
That's a very good point. So what you usually want to avoid, for example, when you exemplify how good your model is, you don't want to have the same patient in both the training and test set, right? And this could happen, for example, with this, because you can't easily you can't easily identify a patient across different hospitals, even more difficult. It's even more difficult in the case where you don't even have access to the data, right? So you don't have any patient ID or so. That's a very good point. So that's a problem that you face there as well.
There is another question. No.
Hi, thanks to all the speakers. I had a question for Klaas. It's great to thanks for the presentation. It's great to know how all these big studies in Sweden came about. I was just wondering, since I guess this project started some years ago, can you expand a bit on the kind of regulatory framework you used to follow models from development to actual clinical implementation? Did you yourself request actual trials to be performed and above what was requested from the current laws, I think, or maybe? So, yeah, thank you.
It's a very good point. This is a really big struggle for everyone, but the setup we have is very distributed in that sense. So ADA centrally, we don't run studies as such, so it's the individual projects of the research groups or the companies that would have faced those type of questions. But then what we try to do ADA centrally is to help share knowledge about these things. So in our workshops and in knowledge sharing that we have, that's been a really a big focus area of sharing knowledge, so that everybody does not have to start from scratch in this area. But it's still a struggle. It's still so much uncertainty, and yeah, it's a big challenge for anyone taking this on.
There is a question on the third row. Yes, thanks.
Hi, thank you for the excellent presentations. I have a question for Daniel. It's a rather theoretical question. So in this federated learning system, let's assume that patients, of course, they have the right to withdraw their consent to use their data at one of the centers. What happens then? Because the algorithm was already sent to another one.
Sorry, did you ask what happens if the patient didn't give the right?
No, if the patient withdraws their...
Withdraws, okay.
Yeah.
Yeah. Another problem with federated learning. It's hard then, but it's then in the responsibility of the individual center to then withdraw that from the patient, from the data set that they are providing to federated learning. So you actually have within the hospitals, individual hospitals, you have to have some rules in place which patients can be included in that local training set. So that's definitely something that further complicates these issues.
Hello. Hi, thank you all for your fantastic talks. My question is for Dr. Lundström. You said something in the beginning of your talk that stood out. You mentioned providing value to patients, and I think that value means something different to a board on a hospital, doctors, and patients. Can you tell me what you mean by providing value to patients?
I'm sure I have. My definition would be kind of the same as your question comes from, like whatever is the value for the different stakeholders here. So I think that's also a very important part of the community building, and in our case, the triple helix side of things, just to understand where the other sectors, your colleagues in other places, are coming from in terms of how they view the world, what are their incentives, what are the targets that they're trying to hit, because that I would say that takes a few years to just learn about these things, that you're also self-evident when you come from one side of things, and then you just, okay, yeah, but now I understand why you're saying this, why we haven't reached, why we haven't been able to communicate well here, because you have different targets, and that makes sense. But now we can do work together.
And have you considered any kind of patient advocacy?
Absolutely, and we are in contact with those in a number of different ways in our outreach activities. It is. I would say it's a bit, I don't know, I would be interested to hear about your experiences. Often I feel in diagnostics that is one step, inside the hospital, inside the patient pathway, is that the most we hear from Sweden, maybe it's because AI is not a big discussion in Sweden. All the patient organizations are very much rooting for, we want to share data, we want AI, we want precision medicine, so it's not really any conflict, so everybody wants the same, but they don't have that much to say about, okay, should we go this or that way in terms of how we approach AI and diagnostics. So my impression is that it is much more to discuss in an oncology setting than in the diagnostic setting, perhaps, but very interested to hear your views.
Thank you very much. There was a question here first.
Yeah, I would like also to thank all of you for the great presentation. I have actually a general question maybe for all of you based on your experience. What I think was common in your talks was how is this gap big between research and when we want to really implement it in the real world. And recently I'm also experiencing this, that it's just my personal feeling, in research we say AI can do everything, and when you go to the real world scenario in the industry, you feel okay, we are still using really old models, and it's really difficult to catch up. And my question was what is your advice to younger generation of researchers to do, let's call it more responsible research, to not always say AI can do something, but also to show the challenge, difficulties, and what is your general advice to younger generation, let's say, how we should proceed somehow?
I think we'll all answer that, I guess, but I can start. I think it's very much about this, again, being in settings where you see all the perspectives. If you're in a perspective where you only have that AI hype research, don't care about the actual clinical wilderness issues, then you're not seeing all the problem. And maybe on that side is where you should do your contribution to the whole scheme of things, but you should be aware of all the other challenges that come next. I think that's very, very fruitful. So make sure to have an open mind and go to conferences like this and learn about all these things.
Yeah, I would also like to say similar things because it's very important to know the drawbacks. So whenever we address any younger researchers or any researchers in general, to know the drawbacks of AI and show that how it could be breached is very important. To have your guard, how to protect the data, and also show that what are the steps we are taking to protect, because we are speaking about federated learning, and Daniel already showed that there could be some ways where you could get back to the data. So proving the patients or proving the institutes what you are using to not let that happen, I think this is also important to tell to the community and gain their trust, and tell it's not only the good side, there's also some sides, and making everyone available of that, aware of that is also important, I would say, yeah.
I can add to that, and I want to underline that it's very important to have practical experience. And if you want to develop something for medicine, it's easy as an AI researcher who has not seen any work processes in medicine to just say, oh, I'll develop this thing and this will revolutionize medicine. But the problem is most often in the steps that you're going to take in your everyday life as a clinician. Sometimes it's just that you just want to have the program being quicker and you don't have any patients, and then that already kills your perfect, so patients in the sense, not patients that you treat, but patients in the sense time to wait. That already kills your project. So my advice is to try to really either spend some time in the hospitals to question medical doctors about that specific problem deeply, and to spend some time understanding the medical workflows, because that's what is currently one of the reasons that's currently stating the gap between what is possible and what is seen in the clinics.
So we have an intervention from Marcela here?
No, yeah, just a comment, because you did the same question that I wanted to do, because I think this the same question that many people pose every time we're talking about federated learning, because this is why the title of Daniel was a bit provocative and was not AI, hope and hype, because we are not talking about AI, we are talking about specific areas. In this case, federated learning, as Oliver said, we have proved also in Apollo 11, we are also collaborating with them, also not only in federated learning, but also in swarm learning, that they works. I mean, the technical part is solved. I don't think we have a lot of problems in the technical side. So we have proved also, for example, nitrate lung, in other work that we have done already. We compare the centralized and the local, let's say, data sets, and as we did, for example, with synthetic. So it works. The problem is the implementation. But I would focus, let's say, different levels of implementation. So the first one, also that we were facing with Apollo 11, and we are, let's say, starting, are two problems. I think the first one is the generation of the ECTs that we have. I mean, calling generation, but to say that obviously we have some ECTs, no, which are very focused on the care part, not the research part. So to my opinion, in this more than ever, we need to collaborate within the hospital between the care, and this is why we had today the general director and the scientific director, and we are also building institute a board care with science and also care in order to understand, because AI is moving very quickly with the research part, but so I think that you said also we are very, let's say, in trouble because models are coming and the models are becoming old. I'm not afraid about it. The thing is that we need to implement models even they become a bit old, because we are going very fast, for probably too much. We need to start and really try to focus a bit more how we can implement, interact with these ML models, dedicate a team, so discuss with the general directors and dedicate a team to the ECT and try to, let's say, educate more and more. For example, what we are thinking also internally, it's to take, for example, hybrid professionals, which are working half for care and half for research, in order to be in the same page for the federated learning part. This is the first thing. The second is the heterogeneity that we can, for example, in Apollo 11, we include not only cancer centers, but also academic centers, hospital centers. So and the level and the heterogeneity of the ECTs are very different. So I think that the key messages are that we have to be simple in this moment, to show them that with simple models, we can, because the efficiency we demonstrate, to show them that we can make it. And let's say, starting from simple databases, but we have to inform more and more, as we are doing with education, also with the federated. Because federated learning and swarm learning and decentralized learning, we know that are working. We know that can be for fast queries and fast questions, obviously the first step, no? As AI, as synthetic data, are the first step to answer to our models, generalizability. So it's important. This is why I dedicated this session today to the federated learning, because we are talking for many years, Daniel has shown, class have shown, so in Apollo 11, but it's, for example, Apollo is the last thing that we are doing, because we have designed everything. We have also did some pilots. Also we compared, but the implementation is the key. So we are not there with implementation absolutely at all in Italy. So we really, as class said, need to learn from each other. Probably I'm seeing that we need more and more to foster maybe a very focused workshop in federated learning and data platforms, how we can learn from each other. I'm not concerned about privacy, because the privacy thing was the first, this was a step for the privacy to go through the privacy preserving concept, but we really need to implement with the cities. Okay.
We have some comments from Dr.
Thanks everyone for a great session. So what is the role of the technology companies here? Because they've solved all these problems and many of the problems that we're facing. And so are we trying to, in an academic or oncology space, really trying to reinvent wheels that have been invented several years ago already? And is it better to partner with the technology companies, and how do we do that?
Well, I can start from my perspective at Sectra. So we're not, I'm guessing you're not referring to us in that case, but what we really see, both in terms of what's happening in the big tech companies and in academia is that we contribute very much with what we just discussed, that really deep knowledge and understanding of our customers, of the clinical workflows. And I have a number of examples of big tech companies doing, finding out when they have their great AI thing that they had and going to the real world and then publish stuff on like, oh, did you know the real world is difficult? And like, yeah, we are in this business for a reason. So
a bit of a facetious comment, by the way.
So I think there's a lot to contribute in being a really close partnership with the healthcare, and I see in the ecosystem, I see that's a different layer from where the big tech companies are making all of their contributions.
I think in particular in AI, there's a symbiotic relationship between academia and technological companies. Because if you look at the AI models that are currently in use, most of them have first been developed in academia and have then been spun out to companies. And that's actually what is needed. So for example, if I take the case of my own university hospital, I have an AI group developing lots of AI models, which would be useful in clinical practice. I was speaking to the CEO. I told them, yeah, this is our AI model. We want to implement it. And he says to me, okay, but who's doing the 24-hour telephone hotline if something goes wrong or something like this? This will never be done by academic groups. So I think the way to go is take successful and clinically validated AI models, which have been proven to work from the academic side, and then partner with maybe not the big guys, or maybe as well, but oftentimes it has worked with like smaller companies who are still flexible to then bring this to market. I think that's a very good symbiotic relationship.
I also just want to add something to this. So as you're told, reinventing the wheel. So there, I don't want to name a company, but there was a nice product for swarm learning, which was open source available. So they tried it on a lot of industry application, but when they released it for medical or healthcare, no one used it. So what's the reason is they never used it in AI applications for medicine, and then the application in medicine is completely different. It's a different, so when you simulate things, it looks very simple, straightforward, but when it comes to firewalls of hospital, everything breaks. So this was one of the things, that's why we wanted to do an open source implementation of Swarm where it is specifically built for AI in medicine, so or swarm learning or distributed learning in medicine. So this was a nice use case. And in Odelia, we have this industry partner for the interface. So they have already expertise in building interfaces to use our model and give it for the community. So this partner just provides the interface, and then we provide our models and make it available for everyone. So it's just the interface building, yeah.
Okay, thank you for the presentation. I'm a representative of the ITC department, the guys who turns very lively and promises researchers into skeletons. So, two considerations about AI with imaging. Two experiences, some cases from big tech companies and some others from startup companies spun out of universities and research centers. On the former case, I've been knocked at the door, say, we've got a very interesting and promises AI algorithm to put on top of our MR modalities or whatever. Please go and set it. Okay, and so we go through several interviews with these technology guys. They know nothing about GDPR, okay, and we are responsible for that, and also the legal representative of the institution, by the way. Anyway, we go through that. And then they say, no, it's a black box. You can't get any data out of it. It's a black box. And so there's a nice VPN going back and forth and connected to a port we as a hospital can't get access to, okay? So maybe a vehicle of some stuff, not very clear stuff, not very sure stuff. And so they go back and forth with our data. Okay, that's not very easy. It's a black box. And whenever you talk to them, you ask them about the explainability AI, the AI Act, European AI Act, bureaucracy. Okay, that's one side. And then come the other side with the companies starting from open source algorithms. And when you go to bring it to the clinical practice, that comes all the regulation. Is that certified? Is that a medical device certified? It takes, in Italy, if you are very good, it takes 18 months to get certified as class 1 and not class B. So this is our experience I want to share with you and partially to answer to the young researchers early on. Thank you.
Thank you, very good input. And actually, yes, I'm a computer scientist myself, and I can maybe add to this question as well. Taking inspiration from industry, I think that's what we try to do as researchers as well, and we try to sometimes catch up. But we should not forget also that the industry, sometimes they don't care too much about the privacy, they just apologize when it happens, while I guess in these cases that cannot happen, right? So when I consider this, that federated learning can actually be reverse engineered, I guess all the federated learning that the big companies are doing with our pictures, that could probably be reverse engineered, but they do not disclose it. They don't care about disclosing this information, while I guess the hospitals or the research centers who are working with clinical data are obliged by law probably to disclose if something like this happens. So it's true, that should be done, but yeah, we see with the generative models companies and AI companies, they simply say, oops, it happened, doesn't matter. Yeah. Maybe we have time for one final question or contribution. Yes, Daniel?
I just wanted to add, that's a very good point. So I think what is needed is actually, at each and every step of this chain, are people who want to make things happen and who navigate through the difficulties together. Currently, what is misaligned sometimes, at least in my hospital often, is that like the people who are at a certain point in the chain, they can't gain anything by saying, yes, we'll proceed. Because there will always be some kind of gray area. It's never yes or no. It's never white or black. Never, even in legal things. So you need to have some people who travel the journey with you. And if you have those in all of those different steps, then you can do great things.
Yeah, cultural mediators.
We are perfectly on time, and I'll give this speech to Laura, maybe to conclude the session.
Yes, thank you both. So let's move to the lounge. Thank you.
Thank you.
And so I'd like to invite the first speaker, Alessandra Pedrocchi. No, I think it's Vania Miskovic. Yeah, of course. Who is from Politecnico Milano and works a lot with Arcela, and we're very happy to have you for this session. Thank you, Vania.
Thank you for the nice introduction. Also, thank you all for being here. Obviously, I'm not Professor Pedrocchi. I'm today replacement for her. So I will be speaking today about interpreting AI outputs, and I think that actually the previous closing session was a great introduction for my talk today. So we closed the previous session with the gap between research and practice, and what we can do to a bit speed up the implementation of all of these tools that are being developed for oncology, AI tools. So it is true that tools are going out into, they're reaching higher performances, and there are a lot of publications about it. It is also true that some of them have been also implemented and gained regulatory approvals. But if we go a bit more into depth, we can see that most of these tools that have been approved are related to the diagnosis and screening. This is mainly due to the availability of the data and also established clinical pathways for these problems. If we're speaking about AI tools that are used for treatment prediction or for prognostication, the situation is a bit different. Here on this slide, you can see some of the key aspects why the implementation in general and approval are progressing slowly in this context. I will not be focusing on all of these aspects, since some of them we have already tackled in the previous talk. For example, data curation sharing, clinical IT integration and regulations. But I would like to focus on the ones that are more related to the human user and end-user perspective, such as biases, fairness, transparency, and explainability of these models. This brings me to the field of trustworthy AI. Right now, for the clinical implementation, it's not enough anymore that the tools are extremely accurate. They also need to be trusted in the end to be used. So trustworthy AI is actually the field that is quite in a hot, let's say, hot topic in the AI field, and these are the 6 core principles of trustworthy AI: fairness, universality, traceability, usability, robustness, and explainability. They are all tackling different points in the life cycle of development of AI tools, starting from the data that is being used, how the model has been built, how the results are being presented, and how this information can be used. Again, in 15 minutes, it's impossible to go through all of them, so I will focus on 2, fairness and explainability. So to start with fairness, algorithmic fairness is a relatively new field in this area, and it gained a lot of attention in 2019-20, when there were several groundbreaking studies showing that actually the models that have been deployed are performing differently across different populations. So we can see that the models are performing, having worse performance in some specific population groups, such as Black patients, women, or patients that have cheaper medical insurance. In this context, fairness can be defined as the absence of any prejudice or favorism toward the individual or a group based on their inherited characteristics. So why AI models can become biased? There are several reasons for that. First of all, we can have data that is being used to train these models. So data per se can be biased. We need to be aware of the data shifts that are present in the medical data sets. This means that if we are developing our tool to work with one specific population or data coming from a specific population, we need to be sure that the model will not lower down the performance if it's being deployed on a different kind of population. Then there is also algorithmic bias that is related to the model choice or the way that we are doing the training and the hypotheses that we have been posed. And finally, user interaction with the tools that are being developed. This is especially concerning now in the era of generative AI, when LLMs are being used a lot. And we know that LLMs, for example, ChatGPT, they're trained with data from the internet. And now most of the data on the internet are also generated by these exactly the same models. This can just enhance the biases that are already present in the data that is being used for the training. So what we can do about it? First thing, we need to be aware of it. First thing is that we need to, if we are collecting a data set and we are analyzing data set, and we need to be aware of the protective attributes in our data set. So attributes that we do not want to use in our model to make a prediction. And we need to analyze our data set using these attributes. For example, some commonly used attributes, protected attributes in oncology can be self-reported ethnicity, race, sex, access to the health care, such as hospital type, or if the patient is coming from a clinical trial or it's a real-world study. I just show you here an example. I think most of you know about our project, i3Lung. There will be talk more in depth tomorrow, but just how we approach this problem. So we identify two possible biases in our model, that is center from which data is coming from, since it's a multicentric study, and also ethnicity of the patient population in our data set. Then the second step, this is just like idea what can cause the bias. It doesn't mean that this will cause the biases. So the next step, we need to know if our model that we are developing is unfair. We can do this by quantifying unfairness of our models. For example, measuring the performance across these protected subgroups that we identify. Here you can see a floating head of Margarita, our PhD student. This is an example where we measure the rate, the error that was made by the models across the different subgroups, sex and age group. And we can notice that the model had a statistically significant different error in cross female, male, and younger and older patients. Next thing, okay, once we quantify what we do with it. First and most important thing is to report it, especially if the model is going to be deployed. Second thing, if it's possible, it's not always possible, to try to mitigate this unfairness in our models. This can be done using quantitative approaches, for example, pre-processing data or post-calibration during post-processing step, or we can also use some non-quantitative approaches. For example, we can, what we are also doing is that we're working in a collaboration with multidisciplinary team. We are trying to check a bigger picture, and also one that maybe not all of you will like, but we don't have to always use machine learning if the problem is not for the machine learning. And finally, trying to explain how model is making prediction. This brings me to the second big point for today, that is explainability. In general, explainability and explainable AI, it's quite a broad concept, and it's mainly related to explaining the reasoning behind the way the model is making a prediction and learning. But if we want to check it a bit more granularly, there are different aspects of explainable AI. Here it's very simplified machine learning pipeline where I wanted to show you, for example, here we can have algorithmic transparency. Algorithmic transparency can actually reply to us in the questions like how the model was created, which data was used to create this model for the training. Then once we created and selected the model, we can have interpretability, trying to understand how this specific model we created makes decision. And finally, we have explainability. Explainability refers to the point, to the question we want to reply, how did the model arrive to this specific result? Explainability sometimes can be very straightforward. In case of using linear, simple models, we can just try to enter into the white box of these models and try to see how the model make a prediction. However, most of the models right now are becoming more and more complex, and it's not possible to understand the reasoning behind these models, and often we need to go for the post hoc solutions. So we are trying to use another model to explain the behavior of our complex models. Okay, I will just show you some very straightforward, simple ways to achieve explainability. So as usual, trying to start simple, we can always start with very simple model, transparent models. For example, logistic regression or decision tree. This is an example how we use the decision tree to predict the efficacy of immunotherapy in non-small cell lung cancer patient by using decision tree, not just that we get the final prediction, but we also have the reasoning behind the model decision making. If we are using more complex models, such as ensemble models, I'm still not speaking about deep neural networks, we can use some other post hoc techniques. The most popular one is SHAP, that is giving us actually the information about which features were the most important for the model prediction. Here on this graph you can see the summary plot where all the features that have been used for this specific task have been reported in the importance order. The first and most important one was ECOG performance status, and aside that importance, we can also see that a low ECOG performance status actually is a key variable to predict long survival, together with younger age at IO start and low NLR. Aside from that, very interesting thing for a clinician is also what we can do with the local explainability. Local explainability explainability refers that we are explaining the prediction for one specific patient in independent set for which one we are making the prediction. Here you can see this is one example. This was a true positive prediction. And in case of this specific patient, the most important information again was performance status equal to 0. And this is the most important information for this specific patient that lead the model to predict it as a responder. If we are going a bit more into deep neural networks and images, things are getting a bit more complex. Silencing maps are still, let's say, the most used and state-of-the-art method to explain deep neural network models that are working with images. For example, this is just something that we are doing with our master student Laura and Rebecca. They are building a model that is using PET scans to predict if there are or no cancer lesions in the scan. And here we can see the explanation for the wrong prediction. Explanation in terms of this like a heat map that is present on the image that is showing you where specifically the model is paying attention when it's making decision. We wanted to see what was the reason for a wrongly predicted label in this case, and after analyzing and trying to come to some conclusions, we thought, okay, maybe the cancer lesion is too small to be for us to see it, or maybe it's the difficult location in this case. So what is the good explanation? Depends on the target audience. It's not one solution fits all. If we are explaining our models to developer, data scientists, or AI experts, we can simply use all above methods or even just a clear reporting. Sometimes also this will be enough. And we are doing this to detect biases, to improve efficacy, etc. If we are explaining our explanation to the domain experts, such as medical doctors, we are doing this for them to trust our model and potentially in the future to use it. And we can still use above all mentioned methods. However, we need to also provide a clear guidelines on how to understand and interpret this explanation that we gave it to them. And if we are targeting the patients, the reason is usually to understand the situation. In this case, the simple narrative explanation of what influenced decision is probably the best approach, but I think there will be talks about it after. And I just want to mention that it's not so easy to do the explainability. There are still a lot of ongoing challenges. First of all, it's the evaluation. There are quantitative metrics to evaluate the goodness of our explainability. However, they are often enough, again, for us, but they don't always show us how the end users are perceiving our explainability. So in this case, we are trying to work on using end users, keeping end users in the loop, and trying to organize with them questionnaires where they will give us the feedback about our explanation. Then image explanation do not provide enough details always. Sometimes we can see just where the model is looking, but we do not understand why it makes a prediction. For example, this is another example where we have exactly the same explanation for the wrong prediction and the correct prediction for the same image. Increasing in models complexity is another ongoing challenge, and I think there will be a very nice talk tomorrow about it. Now the models are becoming multimodal, and the explainability should move in that direction as well. Okay. We are also working more with foundation models, so the explainability is reaching another level of complexity. We are also dealing with a static explanation where we usually have a scenario, we have a prediction, why this prediction is being made, we have where on the area the model was looking, and then, okay, is this explanation any good? And this is where things stop. In the future, hopefully, with the use of the new tools, we are hoping to reach some level of interaction and prompting where actually the explainability that will be provided to us will also be actionable, and we could use also some LLMs and prompting to communicate and to guide the explainability in the direction that we kind of want to. So before concluding, I would just like to give a take-home messages. So transparency, evaluation, and reporting are extremely important. So we cannot just anymore focus on the accuracy and reaching the performance. We also need to think about what is needed for these models to be usable and actually applied. Explanation must adapt to the audience. It's not the same for for a clinician, patients, or a researcher. Future in AI and oncology must be co-developed, so we need to work together, psychologists, medical doctors, and us as AI developers. And finally, education for everyone. It's also closely related to my latest point. Thank you.
Thank you very much. So let's move on to the second speech. I invite for the speaking Dottoressa Paravettoni. She is a psycho-oncologist working here at the Istituto Nazionale Tumori.
If you like, I come. I'm at the European Institute of Oncology, but it's the same.
No, sorry, Istituto of Oncologia. It's a mistake.
I just explain because there are some colleagues of the European Institute of Oncology. I don't want to create some. No, nothing. I would be happy. But we work all together. So. Nothing changed because as Vanya concluded her speech, what we are trying to do is putting together oncologists and of course engineers with the psychologists. And I think to be the big elephant in this room because I'm the psychologist. So we started 3 years ago working together on a project, on a European project, iFree Lung. And what, I don't know if this works. I go? No? Doesn't work? Now it's good. And we just started working together from a psychological point of view was really everything very difficult for us because there are things that where we talk about usability, we talk about trust, we talk about things that are very important for the engineers, for the oncologists, and for the psychologists, but putting together all these things is really difficult. And we started with the idea of an artificial intelligence, like the idea of an old machine that became modern, and from a certain point of view, started from an app, a device, to an algorithm of something, somewhere, somehow. So very difficult. Why? Very difficult from the psychological point of view because we need to put together what we represent, what we see, who we are as professionists, and who is our patients. Because at the end of every presentation, we say, there are the patients, the patient is so important, and we really take care of our patients. The patient is at the center of our research, and we do everything for our patient, but how? We understood that was very difficult to understand the ideas, the values, the beliefs of the patient. And the patient is not the patient, is a person who is very different from another one, like an oncologist who is very different from another oncologist. So it took very much to understand that there was a person behind the machine that was not exactly the same. They had individual characteristics, different emotions, a different way to behave and to take care of themselves, of their families, relatives, and how they can handle with, for example, negative emotions. When I have negative emotions, how I react is different from another person. So, how we put all these inside the artificial intelligence, inside our platform. There are internal resources, external resources, and there is something that is a focus for the psychologist that came sometimes up also in other relations, that is in other talks, that is the decision-making process. how is this decision-making process? You know which is your personal decision-making process? If you think how I can make a decision, what I do? It's really different. We can say that there are two different main differences in the decision-making process, that is being a maximizer or being a satisfier. You know what it is? Is that, for example, me and my husband, I'm a satisfier. So if he says, next weekend we go to Barcelona or Berlin, and I say, okay, what you like? Doesn't care. We go to Berlin or Barcelona. I'm a satisfier. I decide now because I live in a urgency of time. I think that is important to make a decision in a very short time. I feel I have to make decisions very quickly. My husband started with the axis to say, oh, Berlin could be that the weather would not be so good like in Barcelona, but I think that the arts is more interesting for me in Barcelona. So the point is that with a maximizer, if you have one, leave him immediately. A maximizer is a person who decide after the weekend. So you stay at home. Waiting for this decision. Why is this so important? I'm trying to laugh because I know that it's difficult to follow a talk after the lunch, but it's really very important what I'm saying. Because when we work on artificial intelligence, we need to understand who we are before understanding who I have in front of me. And for the patient, it's the same. Is a maximizer, is a satisfier, is an extroversive, is an introversive, I'm introversive, I'm extroversive. And all these things make a huge difference because it's difference the adherence to the treatment, is the adherence, the perception of how I can decide on and decide what are my preferences on the treatments, which can I explain something on my rash, vomit, how I feel this. That is different from one patient to another patient. So, making a long story short, this is what we tried to do in this European project, and I always have to thank Arcela, who involved me in this wonderful project. I also met these colleagues of the Politecnico, and I don't know if I'm happy at the same time and in the same way, but they are funny. And because they change everything, I asked something and said, no, you cannot do that in this way. We have to change all the technical stuff. Okay, and it takes time to do things. It takes time. What we were trying to do is developing decision aids based on artificial intelligence, starting from the knowledge, the resources, reducing anxiety of our patients. So when we started, we focused at the very beginning on the patients. Working on that, I hope in the future we will consider also the fact that different oncologists with different pages behave in a very different way. So time is different and many other things are different. This is just to show you that we started 3 years ago writing things, analyzing what we had in this European project, and it's old now. What we wrote is really old. We are now, we went on, but we have to go on, and we have to work very much of course, I'm focusing on the psychological issues. I'm not talking of everything. This decision-making tool for us was, of course, understanding the preference of the patients and the process of decision-making of a patient, how is understandable and how are understandable the options, the different options that an oncologist explains to a patient for that particular person. And again, starting from the knowledge of a patient. Not all the patients are the same. We have different culture, we have different values, and it's difficult to understand and organize and decide in the same way. There are people that are saying, no, I understood. The most important thing is share the decisions. You know that, you heard that. I'm a psychologist, and I have to say that sometimes, I don't know if it happens also in other disciplines, but in psychology, what happens is that there are periods that are in which we have the fashion words. So there was the year of the empathy, the year of the resilience, the year of something else. This is definitely the year of the shared decision making. So what we understood is that we, Europeans, had to import the model of shared decision making coming from the US and apply to our patients. Completely wrong. Because they were working in how to share decisions with the patient just because they want to avoid legal issues with their patients. Starting from this model, we need to understand how we can work on that, considering the culture and considering who is the patient. So, the knowledge, when I say knowledge and values and ideas and beliefs of the person I have. And also, values and I said, and also how we can improve this tool. We are working on that. And how we can include in this tool the model of decision making that is the answer to the model what expected from our patients. So not how I make a decision, but how is possible that we share a decision because we connect with the model of decision making of my patients. This is something that we are trying to work on, and it's difficult. It's really not so easy. And but it's important because we saw, starting from a pilot, that for the patient, if you put attention not only in giving information, right information, simple information, but also the fact that you connect with their system and they can share how to make this decision, how to make the decision, the right decision. That is always, of course, a second best decision, because the first decision would not be there in front of you. The second decision is the best decision for them in that moment, at that time, with the cancer they have, and with the family they have, the relatives they have, and everything else. So, what is important, I'm going to the conclusion, what is important is that we understood that there is a risk of the overshadowing of our patient. Because we are putting so many things on this patient, and only to the patients, never to us, we are putting so many things that the patient do not understand, the patients do not understand who they have to trust. Who they trust at the end? Their oncologists, because they have a personal relationship with the person who take care of them. So even if we are working very hard on developing artificial intelligence, new algorithm and everything, at the end, for the patients, the most important person is what the oncologists say. Why I underline this? Because we can try to solve this overshadowing of the patients and create a trust between the artificial intelligence and the patients, and not only between the person and the artificial intelligence. Thank you very much.
Thank you, Gabriella. So let's start with the first discussion. There are some questions from the audience. Some question? No one?
So I have a question for Gabriella. I learned with this good presentation the importance of artificial intelligence tools and decision-making tools based on AI for the patient perspective. So it is the same utility for your practice of a psychologist.
Thank you. I have to say that the psycho-oncologist is really changing hardly, because years ago, if you said we can meet by remote, no, it's impossible. You need to be seated 1 hour in front of your psychologist, psychotherapist, and work with him. Now it's completely different, and we understand that the artificial intelligence give very good answer to a patient that asks for how can I reduce my anxiety, how can I follow the practice of mindfulness and everything. So I think that the psycho-oncology is changing very hard. What a psycho-oncologist need to do now is improve, of course, not only the practice, but understanding how the neuropsycho-oncology. So what happened in the mind of my patient, and how can I help these patients with tools, like the tools, device, and not me, unluckily, but there are some devices that are starting that are very good to control the anxiety, for example. That is very important, because your patient, the oncological patients, are not able to go every week to talk with a psychologist, and there are not so many psychologists in the institutes and in the hospitals, and I feel that in a world in which we don't have oncologists and surgeons and everything, we are not going to have so many psychologists or psycho-oncologists. So what we can try to do is help our patients with new tools and new devices. And in this way, I think our job is changing very hard.
Okay, thank you very much.
Thanks a lot. It's very inspiring talks. And maybe a question for both of you. So the good thing about AI, I think, is that you can automatize some tasks. So virtually, depending on the tasks, it could go for every patient for a task. For example, imaging, CT scan, or radiology, or breast MRI, or it could be automatized for any patient. So my question is, it's a good opportunity to have AI to translate into patient words and vocabulary or patient understanding. And my question, in fact, to you is how you could, what interpretability methods or outputs would be interesting to give to patients with some AI that would apply to their exam or something like that?
My answer is yes, and now you see the engineers.
No, I will be short. I also, maybe I didn't also tackle everything in depth today because we didn't have a lot of time. But I want to say that explainability is important, but it's not equally important for every tool that is being developed. So if we are speaking about treatment decision-making tool, for sure is extremely important. But if we are speaking about the segmentation tool that will automatize some of the work, then we can also maybe do it just for the sake of the domain experts. There is no need the patient to understand the logic behind the segmentation tool. I think that the best approach is the multimodal XAI that will, aside from all of this information, also give a textual explanation to the patients and the clinicians. And there are some examples in the literature, so it's not something abstract that I'm talking about. And usually, this kind of explainability tools are being co-developed between AI experts or engineers together with psychologists or directly with the end user. There was last year a publication, I think, in Nature Communication about digital pathology tool that is being developed to detect melanoma. And it's multimodal explanation in the sense that it's also marking the region of interest, but also giving very short explanation why this specific images was classified as melanoma with very simple words. Presence of, now I don't know, not the doctor, so presence of darker, multicolors, darker region, these specific edges, etc. And I think this is the way where we should go. I think we will hear more about it maybe tomorrow on the talk about multimodal XAI and in general, so I will not go into so much depth about this.
Okay, thanks a lot. I think for the sake of time, we have to go to the next presentation. So you can ask all your questions at the post to our presenters. We're very happy to welcome Evangelia Christodoulou from the German Cancer Research Center. And she'll be presenting on guidelines and metrics for image analysis validation.
Good afternoon, everyone. I'm very happy to be here. Arcela, thank you so much for the invitation. Today, I will be talking about guidelines and metrics for image analysis validation. It is often the case that when we think about an AI developer's work, we primarily focus on the output of their work, which is the machine learning algorithm. And there are so many other aspects that come into play when it comes to assessing the reliability of an algorithm that remain unnoticed. Today, I will be touching upon the metrics and the reporting. But before jumping into that, let us talk about all those articles that are making actually are overflowing actually the press and also the medical literature, where AI chatbots or new AI methods are outperforming human doctors, especially after the widespread use of LLMs and ChatGPT in specific. So there is this enthusiasm about those chatbots, but at the same time there are also articles that are quite critical in that direction. And the main conclusion of those articles that are criticizing or they're not so enthusiastic about those is that a rigorous AI validation is essential. And this need for proper validation of AI has led to the creation of multiple initiatives, not only from academia, like the Future AI initiative that has recently been published, but also from a national and EU level, like the EU AI Act. As I mentioned before, I will be touching now upon the metrics, and specifically the metrics that are relevant for reliable validation of medical imaging analysis algorithms. So there is this main question: which metrics should I use to assess my AI algorithm? There are so many metrics out there. Each of them has their pros and their cons. And a couple of years ago, we went in the community of biomedical image analysis challenge participants, and we asked them about the motivation for selecting a certain metric. And the most common answer was that they wanted to select something that is standard practice in their domain or most commonly used. And out of the metrics that they used, so for medical image classification, specific accuracy and area under the ROC curve were the most common metrics, and for medical image segmentation, the dissimilarity coefficient was one of the most common metrics. Let us consider scenario where focusing only on those common practice metrics is not a good practice. So imagine that we have this data set, and our goal is to use an algorithm to classify patients into the sick or healthy class. In this data set, you can see that we have a severe underrepresentation of the sick patients. And we get an algorithm that actually manages to learn from the majority class and then outputs or classifies our patients as healthy. If we were to use a standard metric like accuracy, we would have a very misleading result, thinking that our algorithm is performing really well. If we were to consider a metric that actually takes class imbalance into account, then we have a completely different story. But is balanced accuracy what we should always take into consideration when we have class imbalance? So imagine that now we have this confusion matrix. So we have a severe overrepresentation of false positives, which means that the model in the example wrongly predicts way too many cases in the positive class. If we were to use again accuracy or balanced accuracy, we would think that our algorithm is performing very well. But when considering metrics that are actually taking the predictive values into account, we have a completely different story. So positive predictive value is approximating 0 or equal to 0 almost. And then we have Matthews correlation coefficient that is also really low. Let's consider another pitfall. For example, we have a problem, we have a biomedical problem, but the metric that we are using is not really matching the problem that we have at hand. Here we have an image from colonoscopy. It's an object detection problem. We have 3 polyps. Ideally, we would want an algorithm that will be in a position to detect all 3 of those. We are using 2 algorithms now. One of them is able to detect one of the 3 objects, and the second is detecting all 3 objects. If we were to use the common metric like the dissimilarity coefficient, we would have been misled to believe that algorithm 1 outperforms algorithm 2, and that could have severe consequences to a patient's health because those small polyps can potentially develop into larger ones. So with this manner, we try to uncover pitfalls that relate to the selection of metrics, but our intention was to not only stick to that, but also solve those problems. And this is why we introduced the Metrics Reloaded Consortium. And the motivation was to actually, based on a kickoff meeting that was held in December 2020, we introduced the Metrics Reloaded framework, and we used a multi-stage Delphi process for consensus building. So the idea was that the Delphi coordinators would compile questionnaires or lists of metrics. They would feed them or send them to the expert panel, and then there was a loop of feedback. And this expert panel comprised of experts that had a broad range of expertise ranging from biology, medicine, epidemiology, statistics, and computer science. Figuratively or intuitively, the framework is starting from the driving biomedical problem. Then gradually, by answering certain questions that they are so-called problem fingerprinting, you get to capture the specific properties of the problem that you have at hand. And then those properties are get to be mapped to certain metrics. So we have a pool of metrics that are candidates for this problem. And in the end, by going a little bit more granular in the selection of metrics, you obtain a set of metrics and not a one standalone metric, because no metric is standalone. So we get a set of metrics that are reliable for the problem that we have at hand. So this problem fingerprinting that I mentioned is actually asking the user or the researcher questions with regards to the properties of the problem. So is there a particular importance of structure boundaries, or is there class imbalance present in the data? Is there a non-independence of test case? On the basis of those answers, then the selection of metrics gets to be a little bit more fine-grained. Our idea was to not only cover multiple imaging modalities, ranging from computed tomography, microscopy, endoscopy, and so on and so forth, but also consider multiple classification scales. So we went again to multiple levels of granularity. So image level classification, then we went deeper into object detection, object/pixel level detection, which corresponds to instance segmentation, and then even more granular to semantic segmentation, which actually classifies at pixel level. The resulting framework is quite daunting at the first sight, but when using the arrows are colored and they are intended to be visual aids for the metric selection. So the blue one corresponds to image level classification, the yellow one to semantic segmentation, the green one to object detection, and the purple one to instance segmentation. Let's consider the example of having an image level classification problem. Then we would follow the blue arrow and then obtain the set of metrics that we would want to use for the evaluation of our algorithm. Because there are a lot of metrics included in this framework, and I can imagine that for the user or for any researcher, it's useful to actually also know their functional form, their properties, if it is image level classification, whether there is a dependence on outcome prevalence and so on, or class prevalence, I'm sorry. So we also have those metrics cheat sheets, and I think they are very helpful for anybody that's using those metrics. But to go beyond that, we also introduced a standard implementation in Python, because there are multiple Python libraries that compute these metrics with small deviations from what we are actually introducing. And then to make it even more accessible to lay people, we are introducing a toolkit as well. So the user can just enter this website and click upon the task. So for example, in this case, it is semantic segmentation. Then they go about the fingerprinting, and in the end, after having answered all those relevant questions, they get to obtain a final set of metrics that they can also save in their private computer. So moving beyond that, as I mentioned before, it's super important to select the proper metrics for the validation of our algorithm, but we should not stop at that point. Like, it's extremely important to also be in a position to know how to report metrics in a manner that shows that there is a potential for clinical translation for those algorithms. I can imagine that a lot of you are familiar with this type of results tables in many machine learning publications. So there is a newly proposed method that magically, even with a small margin of difference in performance metrics, seems to outperform the rest. So in a form of a self-fulfilling prophecy, this newly proposed method is recommended for a certain task without any reporting of performance variability. So often we get to see plain values of metrics without really knowing how reliable those values are, which actually counteracts the recommendations from the FDA, which actually demonstrate and show that it's really important to incorporate good statistical practice when reporting performance metric values with incorporation of confidence intervals and so on and so forth. We wanted to challenge or also to investigate the practices in the community. So last year we went through a systematic screening of the MICAI 2023 segmentation papers, and we had multiple goals in mind. First, we wanted to see what is the current state of the art, what are the current reporting practices when it comes to variability in the community, how we could potentially estimate the missing variability parameters based on the provided data that we extract from the papers, and how do, when reconstructing confidence intervals on the basis of the data that we had available, how did those widths of the confidence intervals compare to the claimed improvements in performance? So the common practice results are quite disappointing. So more than 50% of the papers are not reporting any variability in model performance at all. And out of those, only one is reporting confidence intervals. And the majority of the ones that are reporting standard deviation are doing that in a manner or calculating the standard deviation in a manner that is unclear for more than 60%. So our intuition was to recover those missing variability parameters or the missing standard deviation and reconstruct confidence intervals, while having the concept in mind that a narrow confidence interval shows some potential for clinical translation, and a wide confidence interval demonstrates that we are quite far off from clinical translation. When reconstructing those confidence intervals for the MICAI 2023 segmentation papers, it was quite astonishing that more than 60% of the times the mean performance, the mean DICE score of the second ranked method in a paper was within the interval of the first ranked method, which is indicating that those claims are not well substantiated. And then we were quite motivated to explore how likely it is that those ranks would potentially flip. Those are some unpublished results, but I just wanted to give you some sneak peek on what we found. So we incorporated classification in our analysis, and on the left-hand side, you can see some graphs that are demonstrating the values of the so-called probability of false claims. So we introduced one formula that is actually showing how likely it is, or calculating how likely it is, that the second ranked method could potentially replace the first ranked method on the basis of what we have observed in the papers of MICAI 2023. So as you can see here, the black dots are the actual values of test set size and difference in accuracy from the actual papers that we observed. And it was quite astonishing that for classification, more than 86% had a high probability of false claims of outperformance, and for segmentation, it was more than 53%. The take-home messages of my talk are that for proper validation of biomedical imaging analysis, you need to choose the right performance metrics, define your problem appropriately, and report variability in model performance. Be aware of many pitfalls that can occur at any stage of the pipeline, and consider further aspects that can impact the generalizability and robustness of an AI application. Thank you very much for your attention, and I'm happy to receive your questions later.
Thank you, Evangelia. Moving on to the next speaker, Dr. Carlo Rossi Chevanet from the Bocconi University, with a presentation entitled From Code to Care, Navigating Regulation and Ethics in MedTech. Thank you.
Thank you for having me here. I'm part of that category that during the presentation this morning has been seen as a limit to the development of AI in healthcare. So lawyers, data protection officer, and so those people. For me, so it would be easier today to talk about some aspect that we have already seen. So the fact that the AI depends on the quality of data on which it will be trained, and the fact that AI is a substantial revolution in provision of healthcare, quality of healthcare, but on the other hand, needs to be verified, and it should be subject to some risk assessment, some continuously risk assessment. When we talk about AI in healthcare, we see that it is much broader than just talking about healthcare data, because it applies to anything that is related to machine learning, deep learning, and natural language processes, that is related to public health and care services, and self-care and health systems. So a lot of data coming from real world data, and they're not necessarily coming from hospitals and medical devices. On the other hand, we have seen that the usage of LLM not necessarily has the accuracy that seems to be acceptable at the moment, and therefore they need to be verified. This brings to setting the challenges in the development of new AI systems and in the usage and integration of data. First of all, privacy. Ensuring that the fundamental rights of individuals are protected, and this thanks to the usage of security and protection elements in the development of these solutions. Ensuring quality and transparency and non-discrimination. So we have seen about, we have talked before about trustworthiness AI and the need of non-discriminative unbiased data in order to create quality results, and then the ethical use of artificial intelligence. When we talk about AI, we don't just have to look at the Artificial Intelligence Act, but we have to consider a set of regulations that enables and not just limit the development of new solutions. I'm talking about the Data Act that mandates manufacturers and service providers to make data generated by connected devices and related services available to users and by user consent to third parties. So imagine manufacturers of IoT devices that needs to make available those data according to agreements that needs to be discussed and signed. Data Governance Act introduced the concept of a data intermediary, so a kind of bank of data in which you can exchange data. And I'm not talking about only healthcare data, but I'm talking about in general real world data. And then the European Health Data Space, that for me is a regulation that will completely transform the way data is shared. We've seen this morning the fact that the problems of data conserved in silos and the difficulties in training an algorithm using federated learning. So making this silos being connected somehow in order to develop an IA solution. The EU Act is a landmark legislation that is taking care in a comprehensive way the need to evaluate risk and include some certain provisions that will be in the next months being binding for everyone that will import, manufacture or deploy AI systems. And a critical element, a critical date in this is August 2026, in which high-risk AI solutions will need to be compliant to the AI Act. So everything that you're doing in terms of training AI solutions will need to be compliant by that date to the AI Act in order to make sure to be useful and to be shareable also. This leads to the need to understand the sense of this of the AI Act, which is based on risk, especially for high risk solutions, requires a lot of elements to be that you have to be compliant with before putting that into the market or starting using it. So a risk management system, a complete assessment of the data that you are collecting and using, and a strong monitoring of the usage of those data, a technical documentation of the solutions that you are using, log registering, transparency, and information for the user. So trustworthy AI it comes to relevance, human oversight, and then everything that is related to the IT, so accuracy, robustness, and cybersecurity. There are some guidelines that will be approved in a month by the European Commission that will go through very in detail on this, and to make sure that you are really building something that is relevant, you will need to be sure that all these requirements are met. Another strategic element to be considered is, who are you? Are you a provider according to the AI Act, or are you a deployer of the AI system? A deployer is a person or organization that uses an AI system developed by a provider, and a provider is an organization that develops an AI system and places it on the market. So develops or has developed, places on the market, and puts into service is the definition of provider, of supplier, according to this AI supply chain. And if you are a provider, this is the list of obligations according to the AI Act that you have to abide by. You have, before using it, to register it. You have a notification obligation. You have to have the mark CA. You have all sort of data requirements and surveillance that you have to continuously guarantee in order to make sure that the solutions that you have been developing is safe and is in accordance with the requirements. If you are a deployer, it seems easier, no? Because you just have to select an AI system provided by someone else. But to select that solution, it means that you have gone through a proper process. You have to have you need to have the proper qualifications and knowledge in terms of being able to select those solutions, and you have to gone through a fundamental right impact assessment, as well as a data protection impact assessment according to the GDPR. So you have to make sure that the systems that you are deploying, imagine that those are kind of softwares that you are taking from off the shelf, are coherent with fundamental rights. So there is one major question that you may ask yourself: shall I build or shall I buy an AI solution? Especially considering that if you are just buying it, so if you are a deployer, this will be faster. This will be you will use pre-certified solutions, but on the other hand, you will have less control on what kind of data, what kind of bias have been considered in training that model. So on one hand, training means greater transparency and explainability, and the quality of data that is decided by you. On the other hand, there is higher complexity and bigger investments. While if you are just purchasing that, you will have less AI compliance requirements. But remember this, if you are a deployer and you substantially modify the AI system that you have bought, you are starting using it. So for example, retraining it with your own data, or making it available with your own brand, you are moving from being just a deployer to being a provider. So you may risk to be not compliant with all the provider's specifications. This means a potential fine up to 35 million euros or 7% of the annual GDP, the gross revenues of the company. So this requires you to have to look into this, and brings us to AI literacy. So the need for continuous training of the person that will, in your organization, will select this AI system and will understand on how they are spending the money of your team and what they are building. If they are building something for the market or just for you, and what kind of availability this will lead. Coming to another element that is relevant, I want you to think about what will be the transformation in terms of availability of data. The European Health Data Space is creating the requirements for all data holders, so hospitals, to make available those data, not just for clinical, for primary use or for clinical use, but also for secondary use. And this will transform also the somehow the governance on the data, because now the more data you have, the more control you have on those data, the more power you have in research. But if you in the future will be required to make those data available in a European health data space, that will be different. On the other hand, it will be much more easier to have quality data to train your algorithm. So talking about secondary use and talking about precision medicine, a new element in terms of shareability of data is the usage of AI to anonymize data. I don't know how many of you are aware of the concept of synthetic data. Synthetic data is data that is generated by AI. So an AI algorithm that is trained on personal information, on personal data, and is able to generate data that are very similar to the original one, but are not coincident. So imagine that you have the data ascribed on the space. The synthetic patient data are very similar to the original one, but each single record is false, is fake, is created by the artificial intelligence. If you go to the thispersondoesnotexist.com, you will see images of people that you may have seen in your life because they look like a real person, but they are just generated by artificial intelligence. And this is relevant because if you have synthetic data, you can make those data available to the market, to other institutions, use those data to develop new applications, and then test those applications on real data in accordance with an agreement with that institution. Is what the Netherlands Comprehensive Care Organization has done with their own data. So they make them available outside in order to make the possibility for other organizations to develop new solutions and then test those solutions also with the real data in order to be sure that they are relevant. So what I see is that there is it is really important to understand the legal framework that is building the EU market for AI data and AI solutions, and be sure that you are working.
Excuse me, we have no time.
38 seconds.
Okay, thank you.
Just finishing, and see regulations. So not just as a limit, but as a possibility to build trust, safeguarding ethics, and enabling access to data. Thank you.
Thank you very much. So move on to the last speech. I invite Lorenzo Righetto for his talks. Lorenzo Righetto work at Nature. Correct.
Medicine.
Nature Medicine.
Yeah, it's okay. Thanks to the organizers for having me today. I think the journal, we were all impressed by the quality and the breadth of the program. And thanks also for choosing, I don't know, this is different from the program. The program has a very resounding and complementary title to this talk, which is instead, I should say, corporate-generated content, but I'll try to give you my personal reading of what's in the slides from my experience. I think as a researcher, I often felt like editors, like there is a meme, I think, of the editor as a gray entity, an oracle dispensing judgment on research. But I think it's important also to understand how the process works, to relate with to understand that it's ultimately a human process. And I think in my experience also the sort of, not the best researchers, but the researchers who appear more frequently on high impact journals are also the ones who are able to navigate the process and understand the inner workings of journals, etc. So I think, as I said, a human process, one thing to keep in mind, to do, I think, is to familiarize yourself with the structure of a journal. And we all have our backgrounds, our interests. Each journal has a scope, and there's a page with all the names of the editors, what they cover. The choice of the topics that the editors cover specifically also tells you a lot about the journal. For instance, I cover digital medicine, but medical AI, however you want to call it now. But this is not to be taken for granted for a medical journal. So I don't think JAMA or the New England have a digital medicine editor. Also, as I said, I'm a person. I graduated in engineering here at Politecnico of Milan, by the way. Another difference we have at the journal is that we have a dedicated team for commentary content. But we all have a PhD, and we all have experience, more or less loosely related to the topics we are handling. So I think this is not something we think about individually in our day job, but from a high-level point of view, the result of our job is this monstrous and ever-growing hierarchy of journals. There are new journals every day. I think one key thing to keep in mind is that this hierarchy of journals is not fixed top-down. It's not like we sit in a room, we look at all the papers and say, Nature Medicine gets this, Nature Communications gets this other paper. This happens in some publishing company, like at The Lancet, I think. What we do is just we work for our journal, try to maximize the impact and quality of the papers we publish. And so this kind of hierarchy is a sort of emergent property of this. And one also important thing to keep in mind that I think not many people know is that for instance, Nature Medicine, we have a publishing budget. We can't publish as much as we want. For instance, I have a target of 40 papers for a year, which is not a lot, considering I handle any kind of medical application of AI devices, other stuff. And so when we make decisions, we also have to take into account this factor. And this number, this 40, also dictates these numbers you see in the slide. So we can, only send out so many papers for peer review. We can only ask for revisions for so many papers and accept so many papers. We always have to think, if I accept this paper, I might not be able to accept another paper later this year. And of course, as I said, it's a human process, so there is no right or wrong. There is no set in stone decision. So as I said, to destroy a bit this image of the oracle, what do we do daily? I think the bottom line is that we read a lot of papers. I think I've read in 1 month, when I started this job 5 years ago, more than I had in 10 years of career as a researcher. So I think this is an important point to keep in mind when you approach an editor. We might not be familiar with the inner workings of the algorithm you're using. Some of them might be a hollow-sounding acronym to us, but we are able to, we've seen a lot of papers, we know whether this acronym has been used before or the conceptual difference from another acronym, and we know what kind of data is available for your specific problem, etc. And I think it's important also to, an important thing and also hard thing to do is to know how each journal works. For instance, at Nature Medicine, the only independent decision I can make is what to send out for peer review. So each post-review decision is discussed by the editorial team. So we'll bring the whole package to the team and say, I sent this out because I think it's interesting for these reasons. This is the feedback from the reviewers. And my colleagues will say, yeah, but for oncology, this is not useful in the clinic because of this. This is not useful to the patients or the clinicians. And or I think this concern by the reviewer is more crucial than you think, etc. And so familiarizing yourself with this will change from each journal to the other one. So I think, we editors have all been researchers, and so we know that the effort required to, publish the new universal cure for cancer is the same one as, a more negative result. But I think, and we understand this is a difficult exercise to do, but I would recommend when you choose the venue you want to submit your paper to is to take a step back and perform this difficult intellectual honesty exercise to think how important is this study I'm doing. Is it likely that it will appear on the front page of the New York Times, or that it will get me a keynote speech at a major conference? And this is what we will do for you in a sense. Also, this how does your work build on recent papers? So looking at the history of the journal can be sometimes misleading because journals change their scope in time. Nature Medicine used to be a very preclinical journal because at the start we weren't big enough to get trials, but now we do, and so we don't publish mechanistic work anymore. But especially now, this is a much more fast changing. Like we can't consider in the space of a few months there will be it will be impossible for us to consider the same things. I think, you know, given the objectively astronomical publishing fees we request, I think one thing to keep in mind that I didn't used to do when I was a researcher is that you can approach the editor at any time for any question. We are not only required to give quick feedback, but also grounded feedback. We read all the papers in full. We make decisions based on the content that you send us, and we will be able to tell you precisely why your work does not fit within the journal at the time. Of course, this is not a set in stone again. This is just my personal view. I think our job is mainly to maximize our journal's reputation. This is composed partly of the impact factor of a journal. I mean, there's no use lying. You will submit to us your best work because we have a high impact factor. But we take into account other, we know we will receive the best work because we also publish innovative work, because we publish impactful work for patients in the clinic. For instance, we are very interested in AI-based trials, but you know, AI-based trials are usually on more narrow applications. They use models that were developed maybe 10 years ago, and they cite very poorly. And so, as it says here, citations are not everything. So I'll speed up a bit. I think it's difficult to, when you get reviews, to really sometimes to align with the decision you got. We don't always only judge based on the technical concerns or whether the paper is flawed and can't really be revised. From the perspective of the publishing budget we have, we also try to get feedback on the enthusiasm of researchers on the topic, on the way the work was done, on the advance. There was the last time I gave this talk, a professor told me that the best way to reject a paper is to give a mildly interested review, because it's not really, you can't really, you know, attack that. And so, you know, again, reaching out to the editor will make you understand better why you got the results you got. We also get feedback also from our colleagues. You know, I can't possibly know what's going on, you know, in the whole of oncology, in the whole of mental health, and the whole of cardiology. So sometimes we have a different perception of what's priority in each field. But going back to what our skills are, let's say, is that we read a lot of papers, and so we are able to contextualize the feedback you receive from reviewers. We know how much data is available for a specific topic. If it's pediatric cancer, we don't know, and the reviewer is complaining about the amount of data, we know that there's not as much available. We were researchers, we have an understanding of the effort required to perform the experiments that are requested by reviewers. So we're able to say, this will take too long for this, or this is not useful. For instance, in clinical trials, we are generally lenient towards requests for mechanism, as long as the agent works. One thing important to say is that since this is a clinical audience, if you are doing trials, please know that we are very strict with the trial not being prospective, of course, but also with differences between the protocol and with what you report in the text. We don't care, well, we care to an extent of whether the trial is positive or negative. If it's negative, we want to know what information we can get from the trial. But please, I mean, there's no use in trying to spin the trial according to some exploratory outcome. Again, yeah, I think the best way is to either read the decision letter in full, sometimes explain why the rejection was done, or to reach out. It's not infrequent that appeals are considered. Again, as a researcher, I would think this would be more of a kind of gestural, postural thing to do. But normally, in my experience, without new data or new experiments, the appeal won't be considered. Of course, sometimes it happens. I'm sure you know that saying that this professor at Harvard said that the work is great is not a thing we consider, but sometimes it happens. This is a sort of example and sort of gradient of things we look for in nature medicine. So of course, artificial intelligence medicine is a nascent field still, so we still consider also some methodological work. But more and more trials are coming up. One thing to notice here is that if you were to look at citations over this gradient, you will find like top to bottom. So as I said, AI trials don't usually cite much. My last slide is to let you know that as there's more and more submissions, we are now launching a new journal that's more dedicated to population health, but still with a strong digital AI component, and that I will be moving there. But I'm saying this just to say that the Nature Medicine position for digital AI will be also based in Milan. So we will be able to apply to work from here. And if you have any questions about this position, sorry for the organizers to trying to snatch students, please feel free to approach me and I can tell you what it means to work for the journal. Thank you very much.
Thank you. Now we are going to start with the discussion. Just one question before starting with the discussion. A question for Dr. Righetto. Is natural medicine using some kind of larger language models, software in any aspect of the editorial or review processes? And if not, are you going to use them in the future?
I think there is some generally NLP tool to being studied for reviewer finding tools, or find similar research to help us in finding similar articles or finding people who have done similar research, but that's about it. Also, please remember that you can't use large language models to do reviews, or at least you can use it to with your own written. You can't submit articles to ChatGPT to get a review, please.
Thank you. Are there some questions?
Maybe just to stay on this topic, because there are people online also, and there is a question for you. Since there are many clinical trials for AI model applications in the real world and not all of them yield positive results, I'm curious how editors, reviewers view negative outcomes when it comes to integrating AI into clinical workflows. Would they still be considered valuable and worth publishing?
Of course, we do publish negative trials every day. I think the criterion is the same as for regular trials. Like, if a negative trial, we want to see how informative the result is for future developments. Often we recently had this trial in which they deployed a model, and the clinicians simply ended up not using it because they didn't trust the model. So nobody had explained to them how it worked. So this is a kind of very basic thing to think about, but as long as there is some indication how to move forward, then there's no problem in publishing negative trials.
Yeah. Hi, Lorenzo. Saurabh Shah, Memorial Sloan Kettering. Thanks for the interesting talk. So I was surprised by some of your remarks, especially when deciding what to submit to a journal. I mean, I try to advise my junior faculty and also postdocs that the extent of scientific advance is really the motivating factor. And you mentioned that in what you were asking from reviewers, but I was surprised in your editorial assessment that wasn't, you referenced whether the study would make the New York Times or some plenary. That's for others to decide. The extent of scientific advance, in my view, should really be the core fundamental unit. And I just wanted to get your perspective on that.
Yeah, sorry, that was just a very generic, how should I say, criterion that I can, the one that I can tell you in a few seconds. Obviously, we also assess depending on the journal, the kind of, for us, it's more like the impact it will have on the clinic, I would say.
Sure. Great. More generally then, on that line, because I think there are a lot of maybe early career scientists in the audience here, and I think can be highly influenced by your remarks today. And I'm wondering, I think the process is obfuscated for a lot of junior faculty or early career people, and I'm just curious what the journals are generally doing to try to standardize the publication process and make it more transparent and give clear targets for people that they can go after, because as senior investigators it's less critical for us, but for the early career people they really struggle with this. And I wonder if you could just spend a few minutes just talking about whether the journals are actually taking steps to improve the process and in terms of transparency and actual targets to meet in the publishing process.
Well, in terms of transparency, there are the initiatives we have to publish reviews, etc. In terms of strictly editorial decisions, it's more of a, it's a bit more difficult to standardize. We have to follow, it's not a, something you can define and not change for years. I think the best is to interact with the editor. We certainly don't have any bias towards being senior or junior. Personally, I don't go after names, but I only look at the projects. So a lot of editors do outreach based on the names, of course, for many reasons. I try to focus on going on preprint servers, going clinicaltrials.gov, and really looking only at what's in the study, and that's I think a basic thing to standardize the process in a sense. So I don't write to Saurabh to ask what's going on, but if I see that Saurabh is doing something that hasn't been done before, I write to him or to a junior colleague, etc.
Thanks, that's helpful. Thank you.
Are there any questions for the other speakers?
I have one question for Evangelia and one for Carlo, Alberto Traverso, San Raffaele Hospital. So for Evangelia, one thing that really surprised me is that when we look at software for segmentation, so methods like DICE, source for distance, very few of the paper actually do look at the real clinical impact, which is saving time, not being correct, but even if you are not totally correct, but you still detect regions that are very different, you know, then it's still valuable, your algorithm. So I was asking to you, why do you think there is this reluctance of, you know, publishing or doing also this, let's call it trial or, you know, reading test? Is it because lack of data? Is it because it takes time? Is it because there isn't a golden standard? That's the question to you. And to Lorenzo, and sorry, to Carlo, I wanted to ask you, so I'm also a fan of federated learning, but I realized that when we were doing centralized learning, people were saying, I don't want to share my data because of privacy reasons. Now when you do federated, people say, I don't want your algorithm to come into my firewall inside the hospital. So is there any legal, you know, do you see any legal advantages using federated learning, or do you also see barriers for that?
So maybe, I hope I remember the question very well. So your question relates to the fact of considering further aspects that relate to clinical implementation apart from the metrics, the typical metrics. Yeah, that's a very important question. I think at one hand, a very important trade-off comes into play when it comes to a clinical implementation. So for a specific task, it's very context specific. So for a specific task, you might not want to target the highest performance, but you want to target the highest benefit in time or the highest benefit for the patient in any other way. I think there's not necessarily a reluctance to consider those aspects, because I can imagine that there are studies that take this qualitative or quantitative more from a qualitative perspective into account. But I think, again, most people that develop a new AI system, they want to do things the way that they're commonly done. So you report a table of results, you have those two, three standard metrics, and what you want in the end is a new publication that will secure a student or whoever else with some benefit of being able to submit a thesis or something like that. So this is the problem, I think, in this domain, that there are so many other aspects that come into play and hinder the clinical implementation of this new AI tool. So I absolutely agree with you. We shouldn't only focus on metrics. So the first step is to not only focus on one metric, but take multiple metrics into account, report variability in model performance correctly, tune hyperparameters correctly. I mean, there is such a complexity on factors that one needs to take into account to have a reliable model, a technically reliable model. But then on top of that, there should be all these other aspects that are very context specific. But yeah, sometimes I try to be optimistic, but I think we have a long way to go until those aspects get to be considered.
So thank you for your question. So as was mentioned this morning, federated learning, it's a way to overcome problems in terms of data protection, but it's very cumbersome in terms of IT, and there are the risks related to the sharing of an algorithm that should be trained on the data that are not coherent, possibly. So there are problems in terms of intellectual property on somehow, and the quality of the training of the algorithm. On the other hand, as I was mentioning in my presentation, synthetic data is an alternative to this. So instead of making this algorithm going around to hospitals share anonymized data using AI to anonymize them in a better way in order to make them available without preserving any problems in relation to data protection. Of course, this has to be measured, this has to be verified with data protection impact assessment before doing it.
If I may add a side comment and question to what you mentioned. So, because in one of your slides you said, the dichotomy between AI developed by, let's say, companies, so let's call it certified and open source AI. In terms of infrastructure, do you think it would be beneficial to actually have companies develop such federated learning infrastructure or blockchain solution? Because then, we have a certified infrastructure, not the research question on the infrastructure, so we know exactly, the responsible, which is, the provider and the stakeholder that develop, the service, or should we just continue going open source?
No, the European Health Data Space is going in that direction. So it's going to make a one only environment with certified data in order to train data in the best way. So we're heading to that to avoid fragmentation and cost.
Well, thank you very much. We have no other time to continue. So thank you very much for attending this session, and there is another session. Thank you.
Okay. I don't know if you, okay. Good afternoon, everyone. My name is Elena Linardu. I'm a medical oncologist working in Athens, in Greece. And together with Federica Corso, my co-chair, I'm very happy to welcome you to this keynote lecture of our Congress, of this amazing Congress. And before we begin, allow me a moment to express my gratitude to our president, Arcela Prela. Arcela, I came to know a few years ago through our collaboration in the European I3 Lung project. And since then, this professional collaboration has blossomed into a friendship. As we both try to build bridges between clinic and AI research. And I'm really grateful for her leadership, her vision, and her passion in this. Through this collaboration, I had the opportunity to meet our keynote speaker today, Professor Jacob Cather. And I think he's a person that doesn't really need many introductions. Jacob is one of the most well-recognized globally AI experts. And he's one of those true clinician scientists in the field of AI in oncology. And I think that you will all agree that his contributions in the field have set and really continue setting, and I hope for many years, new standards in the data-driven precision oncology. So I think we're all really fortunate to have him here with us today. His lecture is going to delve into the transformative potential of large language models, and I think we're all really excited to welcome him. Jacob.
Thank you very much, Elena. Thank you very much, Federica. And thank you, Arcela, for bringing us all together here. This is really one of the main highlights of my year, and amazing lineup, amazing conference, my favorite conference. And thank you, everybody, for being here. So I'm Jakob. I'm a medical oncologist by training, doing work in AI and oncology. I've spoken here the last 2 or 3 years as well, and my disclaimer for today is that I completely changed my talk today. So for the first time, I will not mention anything about all the stuff that we did in the last couple of years. As some of you might know, we did a lot of work in the field of AI-based image analysis and pathology for new biomarkers, a lot of which was rejected in Nature Medicine. Actually, some of which made it into Nature Medicine. But I think now, because they gave me generously 30 minutes here, I thought, what is the topic that we really should address that is still underappreciated? And I thought that we need to talk about large language models and AI agents. So we've heard a lot about large language models and ChatGPT already today, but I don't think we've heard enough about it. I think we need to provide more substantial evidence in this field. And for this reason, I really now want to focus on this technology and want to take you through this topic from beginning to end to hopefully stimulate a lot of discussions around this super exciting topic. These are my remaining disclosures. So first of all, let me basically repeat very briefly the historical overview of how I see artificial intelligence in oncology. Basically, the established way of approaching oncology problems was through what we call single domain, single purpose models. You train a deep learning model on chest x-rays to detect COVID. You train a deep learning model on breast cancer biopsies to detect homologous recombination deficiency. You train a deep learning model on chest CTs and lung cancer patients to predict immunotherapy response, right? All of these are super exciting. There's hundreds of thousands of publications out there, hundreds of products that have made it into clinical routine. But ultimately, this is a bit limited because in clinical routine, we do tens of thousands or hundreds of thousands of different tasks, and we would need one model for each of these, which is not really feasible, right? Also, this approach only considers usually one type of data. So over the years, we have expanded the capabilities. There's multimodal models by which you can take different types of data, put them into one single model, and they can obtain one prediction. We have foundation models, many of which were published in Nature Medicine recently, by which you train one model on a large amount of non-annotated data and can then repurpose it on many downstream tasks. So foundation models have really changed the field because now unannotated, unlabeled garbage data becomes a super important resource that you can learn from and then apply this to the downstream problems later on. But now the real transformative development has been, in my point of view, these generalist models. And these are basically foundation models that have been trained only only on text or on a vision data plus text, and this means you can then interact with them as chatbots basically, and can apply them without any further fine-tuning, zero shot to a certain problem. You can ask them questions, they give you a certain answer, etc. And this technology has been taken even further to what we call AI agents, large language models coupled to other pieces of software extending their capabilities. So now I would like to focus on the right terms, because I think this is where the field is going to evolve. Let's start very simple. Large language models. Basically, people download all. How do you train a large language model? Basically, you download all available text data from the internet, including a lot of basically pirated data, anything that you can get. Then you train a large foundation model with self-supervised learning on these data. Then you do a little bit of decoration on the model, a few minor changes, and then you obtain, for example, a product like ChatGPT. And ChatGPT, of course, has changed our society very profoundly. What I find very interesting is this plot here that shows the uptake in the time in terms of number of users of this technology. So for ChatGPT, it took just a couple of days to reach 100 million users, compared to any other technology in history of humankind. This is super short. I mean, it took centuries for fire or the wheel or the whatever to reach 100 million users, right? So this is really super fast. And also these models are super good now. They beat, for example, benchmarks for artificial general intelligence, which were predefined, right? So these models are super good, are super widely used. Also, of course, in healthcare, a couple of years ago, we mapped out potential use cases of large language models in healthcare, and basically we distinguished three classes, three categories that I will not go into in so much detail, but basically research purposes, patient care, and education. And I think that these still remain the key applications of large language models in what we are doing. One important principle that we postulated 2 years ago in Nature Medicine that I still think holds true is that the real power of these large language models lies in using them as reasoning engines, not knowledge databases. If you want to ask who was the 32nd president of the US, you should probably go to Wikipedia and not to ChatGPT because it might hallucinate. But if you want to, if you have a PDF document of 100 pages and you want to have a summary, well, then you should go to large language models. And what does this mean in oncology? Well, we can use large language models such as ChatGPT in what we call a zero-shot way. You just ask, what is the first-line treatment of patients with metastatic breast cancer? And you will get a certain response, and nowadays the hallucination rates are super low. This response is it's better than a human doctor in many cases, but still there is downsides to it. For example, you ask it, the latest models, what is your knowledge cutoff, and it would tell you October 2023, right? So this is clearly outdated. So a better way to use this is as knowledge, as reasoning engines by providing additional context. For example, you upload the ESMO guidelines on breast cancer, and then you ask what is the recommended treatment in this situation based on these guidelines. And actually, we validated this recently using not the normal ChatGPT interface, but a custom bespoke software pipeline where we compared just asking oncology questions in zero-shot versus together with guidelines, and with guidelines you get much better much better performance. Let me show you a couple of other tasks in oncology that are highly relevant where we can use large language models. One of these is it's basically super boring tasks, named entity recognition. You have a document, a pathology report, and you want to extract certain items like which biomarkers were tested. Well, the gold standard to do this in the past was a human, because you cannot do this with pattern matching. This inevitably fails, right? So you had to hire a student who did this for you, which is not ethical, I think, to use human workforce for such a task. Because now you just ask a large language model which biomarkers were tested, what's the TNM, etc. And of course, this needs to be properly validated. And we did this in these and for example, these two studies, and there's many others, showing that you reach a really good performance by using large language models for this task. Another related task is translation between different terminologies in healthcare. We human doctors document everything as free text, unstructured free text, and then somebody has to go through our notes later on and translate it to basically machine-readable codes that can be used for reimbursement purposes, for quality control, for scientific studies, for epidemiological studies, etc. And this is really bottlenecked by the human workforce. Well, also in this case, you can use large language models to translate between free text and machine readable codes. And I think as this technology is here, of course now we have to implement it. There's several barriers on the way, but once these are overcome, I hope that nobody will ever use human workforce to do this, just overseeing large language model here, which also, just an anecdote on the side, which also I think will improve the quality of healthcare, because when I remember my time in the emergency unit, we had to basically for every patient use drop-down menus to basically document what types of symptoms, what types of severity, etc. Was there, and in most cases people just made it up. Just the doctors just selected something to make the computer form go away. People, if you ask humans to document and structure data, they will just fake it because it's so painful. So I think it's more, and this is what we argued in this correspondence article here. We should allow humans to use human language and then let machines basically take care of the rest. A very interesting extension of large language models is vision language models. I mentioned this before. It's really, from a technical point of view, not such a big step. You train the large language models not just on text, but also on images, and then you obtain a model that has an understanding of images and text. And you can use, for example, the normal ChatGPT to just get an interpretation of a pathology image. Of course, this is not good enough for for many purposes, but it's as good as like a medical student or like a it's much better than the average person out there. So it's actually pretty impressive. And of course, people like our friend Faisal Mahmoud from Harvard have trained their own vision language models specifically, for example, for histopathology. I will not go much more into this field, just mentioning it here. So there's so many applications of large language models in healthcare that we need to bring, and specifically in oncology, that we need to bring a bit of structure to this, okay? And this is exactly what we are right now doing in our professional society, ESMO, led by many of the people who are here. The group LCAP was put together, Evaluation of Language Models in Clinical Practice, where we basically distinguish 3 different types of applications of language models in oncology. One is patient-facing apps, so chatbots used by patients, and patients are already using large language models all the time. So this is an area of application that we need to provide guidance for. The second is doctor-facing LLMs, basically decision support tools. And the third is background LLMs, helping, for example, to convert unstructured nodes into structured codes, right? So these are the 3 buckets, and then we basically did a Delphi procedure to outline the requirements for each of these buckets. This is hopefully going to come out sometime this year, so stay tuned for this. I want to wrap up the part of my presentation about large language models with an outlook that that we are underestimating still the pace of development here. Soon, large language models will be, now large language models are better than human doctors at some tasks. Soon, large language models will be better at human doctors at every single task. And of course, we can debate how soon is soon, right? Will this be? But it will definitely. So my retirement age, set by the German state, is July 2056. So before that, I believe that definitely this will be this will be the case, right? And now even there's this very striking evidence out there for large language models capabilities, even at unexpected areas. For example, delivering psychotherapy. There was a prospective randomized trial showing the efficacy of large language models-based interventions. And I don't think that we anticipated this a couple of years ago. So much for large language models. But large language models are fundamentally limited because they cannot take action on your behalf. For example, I can ask ChatGPT how do I get from Milan to Dresden, where I live, right? And it might tell me, well, there are certain flights, there are certain train connections, whatever, you can take a car, but then it cannot make the actual booking for me. It cannot book the actual ticket for me. And this is a limitation no more, because you can, for example, you can just give a large language model access to a web browser, and then I give it my credit card, and then it can basically look for the connections and also place go to the Lufthansa website and place the actual booking. And this is the definition of an agent. A large language model based agent is a system that you basically connect to external components, and this enables it to perceive additional information but also take action. And large language models-based agents have been conceptualized by many. Basically, it's super simple. It's also super simple to I mean, a 16-year-old person can implement this, right? You can implement this in a few lines of code. You just call a large language model, and then you give it access to additional. You link that to additional other tools, for example, knowledge databases or any other software that has an interface for this, or also for example memory. So large language model, AI-based agents have been around for a long time, even in this very ancient. Maybe the technical people here in the audience will recognize this very ancient textbook on artificial intelligence. Even there, agents were defined. Nowadays, they have evolved beyond such a concept to actually useful software. And one piece of one area of our society that's already massively impacted by these agents is software development. You might have heard the term vibe coding. So that means you just tell a large language model to code basically a mobile app for you. And if you just ask ChatGPT to do this for you, it will not be able to come up with something that is not just a trivial thing, because for a mobile app you need like a front end, a back end, you need like an authentication of users, a database, etc. But agents can do exactly this, and software development agents using different tools have already made a tremendous impact in real world things like the job market for freelance software developers, where you see that basically hourly rates are going down. Agents can also address other problems that were not addressable before. Let me introduce you to a very interesting paper that came out early this year called Humanity's Last Exam. Basically, it was observed that any benchmark that we put for large language models to solve has been smashed in the last couple of years. So benchmarks really become useless. Benchmarks of medical knowledge like MedQA become useless because any large language model gets like 90% correct, right? So you cannot really compare models anymore. So a group of experts from many domains came together and came up with Humanity's Last Exam. They devised questions that were so difficult that large language models were not able to solve them, so they passed all of the questions, they question candidates through ChatGPT and everything, and only accepted it if it was, I think, below 4% solvable, right, by these tools. And as part of these, so it was the most difficult exam ever conceived by humanity. And there are questions from a lot of different fields in this exam, one of which is medicine, oncology actually. There are quite a few breast cancer cases in there, and I mean this is super small here, but if you can, if you just take a look, this is like a long description of a patient with breast cancer and figures and like I even shortened this here. So, and then you have to choose a right answer, and ChatGPT just gets these correct in less than 5% of cases. Well, it turns out that an agent system, OpenAI Deep Research, gets 25% correct in these exam, and this was basically within a couple of months of that being released. And why is that the case? Because the agent can basically reflect and think and iterate and also get collect information from different external tools or from PubMed and from wherever. This is just an example for an agent that collects information. An agent that also calls different tools is, for example, a tumor board agent. And we have, Dyke from our team has implemented this. This is in press at Nature Cancer, where we basically built a GPT-4-based agent system that can simulate a tumor board. It can read the patient history, and then you give it basically the radiology images and the pathology slides, and what the agent will do is to call other models that can read pathology images, to call other models that can read radiology images, and it can even like compare radiology images at different time points and then synthesize the information and give a recommendation. So this is a deviation from what we thought 2 years ago would be the future. 2 years ago, I think, that we would have giant multimodal foundation models that we train on everything, and then they would be experts in everything and would basically replace a tumor board. But it turns out this is not even needed. You don't have to have this giant multimodal model for everything. You can just have an agent that has access to specialized tools, and then you can even solve complex workflows such as tumor boards. The challenge here is evaluation. How do you tell if this is working or not? And basically there are no good benchmarks, so we had to benchmark this against a group of human doctors, which is not really scalable and not really satisfying. So we have to come up with better ways. One very interesting thing when we think about benchmarking agents is the following. We do not just have to think of the final result. Typically, when we think of AI models, we compare the final result to the ground truth, or we compare the final result to an expert panel, right? But with agents, we can compare another thing, and that's the workflow. How many steps did it take the agent to come at the final result? Did it, for example, the tumor board agent, did it have to look at what was the sequence of tasks? It basically, we would expect that it reads the case, it looks at the radiology images once, it looks at the pathology slides once, and then it will think a bit and then come up with a recommendation, right? We do not want the agent to basically look at the radiology images 1,000 times and then again at the pathology images 1,000 times. This would be wasteful, right? So we, again, Dyke and others from our team, include, and also some of the my students and lab members who are here have contributed to this. We built an agent that can interact with an electronic health record system and can a simulated one, and can basically, you present it with a medical case, and then it can query imaging exams, it can request laboratory tests, and then it will get the results back and will basically take the next steps. So what we want is that it comes to the final diagnosis of this case in a very efficient way. We do not want every single patient to have a whole body MRI and to have every single laboratory test, although maybe this would give us the best diagnosis. We don't want this. So we have to benchmark basically the workflow that can be visualized like this and the result. And again, we lack the conceptual frameworks for this, so that's a big unsolved question. Agents can also not just occur alone, but in teams. This is basically the latest development, because imagine you have that everything is agentified, that you have different types of agents in the hospital. Well, then they will also start talking to each other, and this is exactly the vision that is being put forward for research and for healthcare by these perspective articles. I have not seen any substantial evidence, original studies in this field. I think we're still missing this to show that this is actually useful, but many of these perspective style articles are proposing that in an oncology hospital of the future, we will have different specialty agents that interact with each other. And actually, many people are taking this agent-to-agent thing pretty seriously. For example, all these companies came together and defined a protocol, a standard for how different agents can talk to each other. Imagine every company will use agents for any of their administrative tasks. So then if you have contracting between two different companies, well, then it will basically be agents talking to each other and figuring out the contract. And this is exactly what the agent-to-agent protocol enables. This is not specifically for medicine, for healthcare or science, but I think it has implications for this as well. Here, so another thing, we talked a lot about legislation, that sometimes legislation stands in our way, but probably it's quite reasonable to have some rules, right? So maybe not. Let's look across the Atlantic to our friends in the US. There was a draft piece of legislation introduced into the House a while ago. I think it's still at this stage, that basically says that artificial intelligence can qualify as a practitioner eligible to prescribe drugs. So if they would basically approve this in the legislation process in the US, then a lot of what we our whole concept of thinking about AI in healthcare would totally change. I personally probably don't think that this is so realistic that this will become law, but I think the US politics is unpredictable enough right now that we have to take this a bit seriously. I spoke about agents for oncology, healthcare. I just want to mention very briefly cancer research, because also if you think that you're a cancer researcher not interested in automating processes in hospitals, and so your life will be free of agents, this is not true. We think we and others have done some work showing that that many of the things that we do in the scientific process, for example, we have a digital data set, we go to GitHub, we clone repositories, we have a set of tools that we use to analyze this, we come up with a report in the end. Well, this is this can be agentified very, very well. You can have agents that write Python codes, that look for the right repositories on GitHub, compile them, use them. So basically the idea, the vision is that ultimately human researchers would only have to give a high-level objective, for example, for a data analysis problem, and then an agent would perform the steps. And then you can also think about, why do we actually need the human there in the first place? So this will probably keep us busy in the next couple of years, I think. Let me give you some very specific examples for how agents come into our research workflows. We have talked about, let's take the example of pathology foundation models that we have heard about today already. How do our workflows look like? Well, typically we have a small data set. Let's say we have pathology slides of ovarian cancer patients, maybe 95 ovarian cancer patients, some of which responded to a certain therapy, some of which didn't. Well, then we typically take this data set, we use a foundation model to extract the features, we use software workflows to train machine learning models to see if we can predict treatment response from these data. And a human basically does this using a foundation model, and that's the state of the art. Well, the future will likely in these cases look like this. You have a data set, and then an agent runs the foundation model, uses certain software tool, writes the code, and comes up with a response and iterates again. Of course, this will start with the reproducible basically standardized, simple tasks, but I don't think we have any reason to believe that it's going to naturally stop at some point. Let me basically jump over this because we're running out of time to just go to the very final thoughts. I think all of these technologies are giving us enough material to do research on, because for basically all the points that I mentioned, we need, I think, validated quantitative research with good metrics. Before we believe any of this, we need to see the evidence, right? And I think this is our homework for the next couple of years to tackle this in the field of cancer research and oncology. And there's many interesting questions that will come up. For example, what are the guardrails for agents? What do we actually want to optimize for? Imagine you have an agent in a tumor board. What do you want to optimize for? Do you want to optimize for optimal resource use? Do you want to optimize for cost? Do you want to optimize for patient survival? Do you want to optimize for patient quality of life? All of these things should somehow be defined, but we don't really know how, and we don't know what are our objectives actually in which circumstances, so we need to do some work on this. Also, how do we constrain these agents by some laws, etc. So if you want to keep discussing this topic, please come to our ESMO AI and Digital Oncology Conference in November in Berlin. This is like an ESMO spin-off company with 1,000 participants, and we will discuss AI-based biomarkers, large language models, and specifically also these agentic systems. So with that, let me close my presentation. I hope that this was of interest. I hope that this will inspire us as a community to produce some substantial evidence in the next couple of years, and hopefully publish a lot of that in Nature Medicine with that, I want to thank my research team in Dresden in Germany. This is a somewhat outdated photo. We are an interdisciplinary group, about half medical doctors, biology people, half computer science people, some undefined people somewhere in the middle. So I think we need this type of interdisciplinary teams to work in this field. Thank you very much.
Thank you, Jacob. Always exciting. Please stay there because I'm sure there's going to be many questions. We're going to have a few minutes of discussion and questions. This is your chance. You have Professor Kathar here, so enthusiastic. I think his main message of mixing different people together is what he has been trying to do over the last few years, and I think that's amazing, and you're doing it. You're an example and an inspiration all over the world, and thank you for that. Questions, please.
Thank you very much. I have a question about, during your introduction, you say, if I understood correctly, that now also garbage data are largely used by this model. So, since as a computer scientist or biomedical statisticians, we used to say garbage in, garbage out. Now, this is out of date, probably. This.
Yes. There actually, Arcella has a very nice statement that is garbage in, gold out. Of course, this principle still holds true in many ways, but one specific way where it's not true anymore is when you consider unlabeled data. Imagine a pathology department, for example, here at this institution. If you go to the basement, to the archive, you will find probably a million pathology slides, but they will be, even if you scan them, they would have been totally useless because you have to basically link them with the clinical data in order to use them for anything really useful. Well, now this is not the case anymore. If we just would go here, scan all the slides, and then train a foundation model on them. This is basically a model that does not have a specific task. It would just learn the distribution of patterns that are out there. And then this foundation model would be very useful because then we could take it for another data set and just fine-tune it or put another model on top to extract predictive or prognostic patterns from much much less data, because the model starts from a much higher baseline. So basically, that's the example where we have. That's one of the examples where we have garbage in, gold out. Of course, if you have really wrong data and you feed it into a model, well, then you will get wrong results, right? And this is happening. I mean, there's interesting studies about this of people placing politically motivated information on the internet so that it is ingested by large language models that then learn from it and basically spit out the same thing. So you can poison. This is basically training data poisoning, which you can do, which would be actually still relevant garbage. Yeah. Thank you.
Thanks, Jacob. I had a couple of questions arising from the same observation, basically. So we have seen models becoming bigger and bigger, more data, more tasks in time. So one question is, we sometimes say these new bigger models are democratizing the system because you can use them for a number of tasks. But isn't it also true that fewer and fewer labs are able to? How many labs now can develop their own large language models at the academic level? And at the same time, the most performing large language model is closed source. So I was wondering, what is the outlook in your opinion on that? And on a similar vein, for medical devices, in my understanding at least, you have to test them in the clinic for intended use, right? So how do we test models that can do anything?
Excellent questions. For the first question I totally agree with you. I mean, 1-2 years ago, we were really depressed because we thought, all of these multimodal foundation models are coming out. We don't really have so much data, so much compute. We cannot really compete here. But now I'm much more optimistic. Again, because the space is basically saturated. We have now very good pathology foundation models that are out there, or even genomic foundation models is still a little bit behind. Radiology foundation models is maybe also a little bit behind, but pathology is a good example. We have very good pathology foundation models out there. Many of them, they have varying types of licenses, but some of them can be used quite freely. And so I think there's diminishing returns now on training the next pathology foundation models with 100 million slides, right? It's not going to help you a bit. So this space is saturated. Many of the models are open source. Now I think this, and the same goes for large language models. I mean, the open source, many of the state-of-the-art large language models are open source. They're basically 3 to 6 months behind the commercial models, but they're still useful enough for our purposes. So we run many of these large language models on our computers under the desk, which works quite well. I think this field of agent really changes the dynamics of the field, because now having a open source large language model plus many smaller specialist models that are being used by the agent to solve specific tasks, this is, I think, the way to go, and this does not require an insane amount of data. Sure, you will always need high quality medical data, but now I think the rules of the game have shifted a bit. The regulatory question is super important. Indeed, I think that our regulatory systems are not really equipped to handle this. I mean, a large language model for healthcare is basically falls under the same regulation as a cardiac pacemaker, right? They all both need the CE MDR approval. Of course, it is not timely anymore. I think that the regulatory bodies are quite proactive. They're listening to the community. There's a lot of consultations going on. Of course, all of this is much too slow. But again, my takeaway is the rules of the game will be changed, because if they're not, people are just using these tools without medical device approval, right? Our patients, my colleagues, are using ChatGPT all the time, and it's not a medical device, and I don't think that this is what we want. Thank you.
I wanted to add a comment to what Lorenzo asked related to the trial, how we can test this AI agent prospectively, no? I mean, because we also, there is a second work that Inés, when we are doing, and obviously Jakob is leading with the AI precision group related to the AI biomarkers in general, but I think this can be also shifted and endorsed also with AI agents, right? In the future. Still, I don't think we have to finish the whole process of the final Delphi, but still, let's say that the validation process in prospective trials, I mean, it remains as let's say, as an idea if we want to see the effective value of these AI agents. Obviously, this based also on of what the AI agents do, which is the role. Because if the AI agents are specialized to predict a treatment, for example, in this case, they obviously have to undergo one path. If they are AI agents that help in diagnosis, has other different paths. So I think, at least for now, this in the validation process, this will not change so much. So let us imagine them like the algorithm, but they are a bit different.
Absolutely. I think we will need much more prospective clinical trials now than in the past, because all of these things have to undergo clinical trials. Of course, we have to discuss how should they be designed, how can we really validate a generalist agent that can do anything, but I think there are it's solvable. It's an interesting question that we should address. Yeah.
One interesting application here. One interesting application of AI agent is as nurse. I think you are familiar with companies like Hippocratic AI, which are using artificial AI nurses. So I wonder what is your experience and what you would comment on that.
Yeah, well, I don't have any hands-on experience with this because we live in a third world country where we don't have these technologies, unfortunately, in our clinical routine. I mean, the workflows have to be digitalized, and then you can add these agents on top. So I mean, we are pushing for this to happen, and I think this will happen. But right now, we don't have any of these agents in clinical routine. Indeed, this company is putting to the market agents that basically call patients, follow up with them. I think that's a very, very interesting application. So, Saurabh, you need the mic. Yeah.
Excellent talk, as always, Jakob. So I want to challenge you a little bit on large models, and I wonder if you could just comment for the audience on the role you see for small models, because large models are expensive to use and operate, you know, regardless of whether you're fine-tuning or just asking prompts or whatever. And we've seen even the tech companies are now pivoting quite strongly towards the use of small models for the majority of tasks So I wonder if you could contextualize your talk in the context of small models.
Thank you. Yeah, I think what I wanted to say, for example, with our tumor board agent, this is essentially a system that only uses small models. I mean, it uses a large language model at the core, but these large language models, they can run on my MacBook Pro, right? You can use Llama 3.3, 70 billion or whatever, and this runs, for inference, this runs on my MacBook Pro. It's good enough for many tasks, so I think it counts as a small model. And then this model calls other smallish radiology processing, radiology analysis, pathology image analysis models that all run on consumer hardware. So I indeed think that the agentified world is driven by small models that run on consumer hardware, which is quite a contrast to what we thought a couple of years ago when we thought we need multimodal foundation models trained on all of genomics, all of pathology, all of radiology, all of electronic health record at the same time, which would not run on consumer hardware. And yeah, I think we now have these two alternative ways of tackling, and I'm for sure on the small model side of things. Yeah, for many reasons. Good. I think we're behind.
Hi, Jakob. Just a quick one, maybe more philosophical. I love the talk. I wanted to ask, every time we have more voices claiming that LLMs may get corrupted at some point because we have more LLM-generated data that we will be using for training and this is something that can be really controversial when we get to the medicine field. We are already seeing that some of the big foundation models that we have use data that has been generated with other foundation models and stuff like this. So out of all of this, do you believe the field will be able to keep this under control, or that the very fast progress that we are undergoing will explode on this?
It's an excellent point. I mean, I do think that at some point the exponential growth that we are currently seeing will hit a plateau that requires some completely new innovations on the model design and data generation, etc. However, imagine today the development of large language models stop, and all we have available in the future is the models that we have today. Even then, there's so much we could do with them, using them in agentic workflows. I mean, it would keep all of us busy for years if the technological progress would stop right now. And so I'm not afraid of the future, because I think we will be very busy, because it's about bringing these advancements to our domain. And I do think that probably these scaling obstacles will be overcome by some new technologies, so that it's not going to stop here, but we don't really know. Yeah. Thank you.
Okay. I think we kept you long enough, and we could keep you here for the whole afternoon, but you'll allow us another moment. No, don't go. No. You're not allowed to go, because our president here wants a moment of recognition for you, so please stay.
It's my idea. So, no, I mean, I had this idea because I think you well deserve this award. It's and I want to read it because we dedicated it based on your work, your huge work, because this is the third presentation in this meeting, but you did other two presentations, which was much different. This is why I am very happy today in this third edition to give this award to our keynote lecturer, Professor Jakob Nicolas Cather, in recognition of his exceptional contribution to advancing AI application in cancer research, driving innovation in clinical AI, digital pathology, biomarker discovery, large language models, and now, and in the future, our AI agent expert, helping set up a new paradigm in pattern care, in patient care, sorry. Thank you very much.
Okay, so now we can move to the second part of this session. It's time for the best abstract time. So the scientific committee has selected some of the best abstracts that have been presented. One of these is from Dr. Anya Paver from University of Cambridge. She will present her work about radiology reports to early prognostic markers, benchmarking large language models in chronic liver disease. Please welcome to Dr. Paver. The stage is yours. Thank you.
Thank you very much for the kind introduction, and I'm excited to speak here today. Following on the topic of large language models after such a fantastic keynote, I'm going to give you an example of how we applied LLMs to our liver cancer data in Cambridge. So liver cancer is actually the fastest growing cause of cancer death in Europe. So we're not winning. And this is despite the fact we know which population is at risk of getting liver cancer. And that's patients with chronic liver disease. So the patient's journey of someone with liver cancer doesn't actually start at the cancer diagnosis. It starts much earlier when they're diagnosed with scarring of the liver called cirrhosis. And now cirrhosis is a nasty disease in itself. It can give all sorts of complications like fluid on the tummy called ascites, or high blood pressure in certain vessels called portal hypertension. But some people with cirrhosis, but not all, will go on to develop liver cancer. And we can see this cancer as LR lesions on radiology imaging, and we grade them from LR1 to LR5, depending on the risk of these lesions being cancerous. Now, we can even offer some treatment for this lesions, a local regional treatment, but in many cases, these lesions progress, and ultimately, the definite treatment for liver cancer is a liver transplant. Now, throughout this journey, these patients get lots and lots of radiology scans. We scan them every 6 months with ultrasound or MRI or CT. But at the moment, we're not looking at that data longitudinally at all. And the big question is, are there early prognostic markers coded somewhere in that journey that can help us predict who's going to do well, who's going to respond to the treatment, to help us predict outcomes for our patients? So what would this analysis look like? Well, let's start with a bunch of radiology reports for a patient. Ideally, we want to put that in a structured data format, like an Excel spreadsheet, so we can analyze it, correlate it with outcomes. Furthermore, we can visualize it. So on this timeline, we're going from the day of transplant and working backwards, and we can see this patient had 3 radiology scans, CT and a couple of MRIs, and also they had actually all 3 types of local regional treatment for liver lesions. We can also track these lesions. So here we can see what lesions were reported at each scan. This patient started with one LR4 lesion, and then they developed an additional LR3 lesions. Now, we don't really know how these are related, which one developed to which at the next scan, but we can see what happened over time. So at the CT, we could see an LR-TR non-viable lesion, which means that this lesion was treated and has no viable tumor in it anymore. Now, how do we extract this data from radiology reports? Well, these are just 2 examples of radiology reports, and I absolutely do not expect you to read any of this, but you can see at first sight, one of them is much longer. It probably has all of the variables of interest reported and has a really nice structure to go on, whereas the other one is none of those things and will often have lots of missing data, and then we're not sure if this feature is truly absent from the patient or is just simply not reported and we don't know the status. And furthermore, there are a lot of these reports. So for my cohort of 450 patients, we have nearly 10,000 radiology scans. And we cannot possibly do this task by hand. So can LLMs help us? Can we use LLMs to extract structured data from this free text report and use that for analysis? Well, this was the focus of my project, and there are certain challenges to that. Some of them have to do with radiology reports, just as I described, but some challenges have to do with LLMs themselves. For example, they don't always give you the format that you want for your Excel spreadsheet. And also, there are lots of these models coming out these days. How do we know which one is best? Which one is going to give us the cleanest, most accurate data? So to tackle these questions, I've manually curated a smaller calibration data set. I'm a radiology resident. I have not used a medical student to do this task. And I've curated data for 20 patients, a total of 126 reports. And I've chosen 31 questions about all of these variables I've been discussing, like liver lesions, previous treatment, cirrhosis, and so on. So altogether, I had more than 3,000 question-answer pairs to evaluate the models on. So it would be great if we could just ask a question and, for example, how many liver lesions are there? And the LLM would just give us a number, but that's not unfortunately what happens in my experience. So often, especially the reasoning models, they will start to talk to themselves and reason and try to figure it out. And that means that we don't get that nicely formatted data into our Excel spreadsheet. Looking at this a bit more quantitatively, that happened in 13% of answers, and that's actually over 700 answers that were missing when I ran this. And then looking at this per question, there were some questions which actually had 0 valid answers, so that's a whole column that's missing. So to address this, I've used a technique called constraint decoding. Now, in constraint decoding, you can specify the output format that you want, for example, a digit or a combination of digits. And this program looks at the LLM output and basically crosses out the tokens that are not in that valid format. And this has worked really, really well. I've tested 2 implementations of constraint decoding with Olama and with guidance package, and it works in 100% of cases. But it doesn't mean that the answer is necessarily right, because it doesn't change the probabilities of these tokens. So when I test my 31 questions and look at the performance of these models, well, I wanted to see if there is a clear winner with the best accuracy. And there isn't. There is quite a lot of variability in this data. So let's look into whether these differences between models are statistically significant. And let's actually start with regular expression search, which actually seems to be doing pretty well. And it turns out that in almost half of my questions, regular expression search was as good as the best LLM. This was mostly true for simpler questions with a binary answer like, is there portal hypertension, yes or no? There's only a number of ways in which radiologists write that. So I was able to write quite an effective regex. However, in the other half of the questions, LLMs were significantly better. And these were the more complex questions, more interesting questions perhaps, like counting LR lesions, citing information like what is the spleen size, or what is the date of the previous treatment, and tasks that require a bit more context from the whole report. So then I was interested to know whether I should use a medically fine-tuned model. So I compared Llama 3.3 70B with its medically fine-tuned counterpart, OpenBio LLM, which was actually in the top 3 at the medical benchmark leaderboard at the time. But in my data, there wasn't a single question where the medically fine-tuned model did better. In fact, there were 5 questions where the general model performed better. Now, this might be because the general model was at a slightly newer iteration, so 3.3 versus 3.0 for the medically fine-tuned model. But it also might be that in my prompts, which were quite specific, I already injected some medical knowledge, so it didn't really see the benefit of that medically fine-tuned model versus the general one. Now, furthermore, I was interested to know whether a bigger model is better. So I compared the 70B version with a 8B Llama. And again, for a lot of the questions, there wasn't really a significant difference in performance, but for 5 questions, the bigger model was significantly better. And these were some of the most interesting questions, like identifying liver lesions, which is kind of the whole point of this project. So then looking at this in a little bit more detail, how then does that translate into the timelines? So here on the left, that's the original ground truth timeline that I showed you at the beginning for that one patient. And here you can see the reconstructed one based on the data extracted by the bigger model and then the smaller model. And you can see that the smaller model added this new type of lesion here, an LR2 lesion. But the bigger model also added a couple. So these bars here for LR3 and LR4, they're a bit higher. It means it counted more lesions of this type. And now, if you look across the full data set, obviously some patients have no LR lesions, and a lot of them don't have a specific type of LR lesions. So actually, across the full data set, there isn't a significant difference in performance between the bigger and the smaller model. But when we just focus on the timelines themselves, you can see the smaller model missed 22 lesions and it overcounted 44. And this is compared to still overcounting 33, but missing only 4, which is really quite a small number of missed lesions by the larger model. So I think the bigger model is better in this case, but is it good enough? Well, let me take you back to these radiology reports I showed you at the beginning. Even in the nicely structured ones, these are all of the problems that I have curating this data manually, including some of these lesions are described as numerous. I don't actually know how many are there, but I have to put a number in my Excel spreadsheet. I might be adding lesion, or I might be missing them, because I don't know how many are there. Or this one, here the radiologist is not sure whether this lesion was treated or not, so they say treated lesion or an LR4. Now, if I disregard one of them, I might be missing the true lesion type. But if I put both, I'm overcounting lesions. And I do this as a radiologist. So even though the LLMs aren't perfect, they make this possible. It makes it possible for us to look at this longitudinal data over time, the data that's sitting there in the hospital, and makes it possible for us to analyze it and try to find prognostic markers. So in conclusion, I think this is a tremendous opportunity for us to analyze data quantitatively. I think we had an excellent talk about evaluation earlier, and I would like to echo that. I think accuracy can be really misleading, and the key is to know where the mistakes are and what are you really interested in the data. And to end on a perhaps philosophical note, how do we best evaluate an imperfect model against an imperfect ground truth? And if you have any ideas, please come and chat to me afterwards. Thank you very much.
Thank you, Dr. Power. Are there any questions from the audience? Just one, unfortunately, we are a bit late. No question?
Excellent presentation. Thank you very much. I'm very happy that you are selected among one of the best abstracts. So maybe it's a comment for Evangelia. I think that your last comment was very nice because also Federica was focusing, but also the Jakob group and many of others. Effectively, the metrics are one of the problems, let's say, when we want to compare, right, LLMs and the human and ground truth. So I think that you have your next steps. So working on this, probably you are working, but so a comment for.
Thank you, Ursula, for the question. Yeah, sorry that I'm answering a question on your behalf, but there is actually research with regards to the imperfect proxy accuracy that one can calculate via LLMs. And there is, I don't really remember the title precisely, but it's criticizing using an LLM model as a judge, that in the end so the motivation for using LLMs is that we have unlabeled data and we want to use an LLM to get labels for data and so on and so forth. Of course, conceptually this is a very good idea, but you get imperfect labels and highly biased labels. And this publication that I can share with you as soon as I find it is showing that in the end you need actually double the amount of data of the proxy labels actually from the LLM to have similar performance to what you would have when ground truth labels were available. So there is a lot of work still to be done so that those labels are actually approximating the ground truth labels in a more accurate manner. So yeah, this accuracy, so whenever I see accuracy for LLMs, I'm always feeling a bit uncomfortable because it's not really accuracy. Because accuracy conditions on the fact that you have ground truth labels available. But yeah, this is something
Yeah, no, thank you. I look forward to chatting to you after.
Thank you very much to everyone. Thank you, Anya. So now, please come back.
Stay with us.
Please, thank you. So also for you, it's time for recognition.
Yeah, so I'm again very happy to give another award to Hanya Pavert from Cambridge University for the Best Oral Presentation Award in the third edition of this conference.
Thank you so much. Thank you.
Come the chairs to make a photo. Can you come for a photo? Just another picture. Now it's coffee break. Now it's coffee break, so be in time at 16:20, please.
everybody. Welcome to this third session of this amazing conference about AI in oncology, and thanks so much, Arcela, for putting together all these people. And some of them are also colleagues and friends. I'm very happy to be with you today, and I'm happy also to co-chair this session with Sabina and Luca. I think we will ask to the speaker to be really within the 15 minutes of time, also because this is a session risky for a Pope election. And probably the election will be around 5:30, so during Marina talk. And with this, I'm really happy to invite the first speaker. She's a colleague and friend, Mihaela Aldea. She's working now in Dana-Farber Institute, and but before and also in the future after, she will work in Gustave Roussy in Paris. So the title of the talk is AI-driven biomarkers, how to incorporate and validate them in clinical trials. Thank you, Mia.
Thank you, Roberto, and thank you, Arcela, for the invitation. First of all, I want to say that I'm just a medical oncologist. I'm not an AI expert, but by being a medical oncologist, I will have to decide if I will use your AI tools in my clinical practice. So ESMO initiated a consensus that is not already published about what are the rules that we need to have, what are the recommendations to using routine AI biomarkers, and I will start to speak a little about this. So for me, I don't know for you, but at least for me, AI completely changed my recent life with the speed of a Formula 1 car. And actually, it's still me, but I'm way much faster. And I'm sorry, Jakob, if he's here for the typo. It's ChatGPT 4.0, not V4. I know that you would see it, but he's not here, thank God. And the first question when we work with AI biomarker is, should AI biomarkers follow the same validation standards as a traditional biomarker? And if I would ask you the question, instead of AI biomarker, put a new AI biomarker should follow the same rules as an already validated biomarker, you would say yes, without a problem. But if I ask you the question about AI-based biomarkers, you will probably think twice, because when you see a horse running a Formula 1 car, you're actually maybe have a little mistrust in it, because you're not used to see it. And while there are hundreds of AI tools that have FDA approval, what's interesting to note is that more than 40% of all the AI tools are currently lacking clinical validation. So importantly, FDA approval does not necessarily mean that there was a clinical validation. While me, as an oncologist, if I see an AI tool, I would like to see the clinical validation, I would like to see the data published, I would like to see the sample size, the population, the prevalence of a biomarker, how the methodology was done in order to be sure that I can apply that AI biomarker to my patients. So when trying to find some rules about all these AI biomarkers, we need to understand that they are quite heterogeneous. They are, and we cannot apply the same rule for all, but if we are able to divide them in some classes, maybe it's easier. So in the first image, let's see this example with the PD-L1 quantification. Here is, for example, I don't know if Julian is in the room. Julian, if you're in the room, this is you, like very tired after quantifying PD-L1 expression manually. Actually, Julian, instead of being in the basement and not seeing the sun during the summer because he has to quantify PD-L1, he could have been like in Bahamas running a script and automatically quantifying PD-L1, as Jakob said, easy from his Mac. So this is the next level. But then let's go even further, because we can even predict PD-L1 expression not only from immunohistochemistry, but actually from hematoxin and eosin tissue slides. And let's go even a step further. we have biomarkers. The PD-L1 is useful for prediction of the immunotherapy response, but we know that it's not the perfect marker. What if we can do better with AI? What if we can see beyond the human eye and find a better biomarker to predict immunotherapy response from hematoxylin eosin tissue slides? So ESMO came with this classification of AI biomarkers and divided in 3 classes. Class A is the biomarker quantification based on the same input that we used. Class B is the approximation of existing biomarkers, and I will talk about later. And Class C is completely novel biomarkers that can be either prognostic or for predictive purposes. And today we will talk only about the evidence tier 1, which is, according to ESMO, what are the criteria that we will need to use in routine these biomarkers, while tier 2 and tier 3 are still undergoing evaluation. So class A, the biomarker quantification, is the easiest example, and I will show you is this one. So is the quantification of PD-L1 from immunohistochemistry. So actually the input is the same as that used by a pathologist, but the method is new. It's an automatic quantification, while the result will be the same. Other examples of class A biomarkers are the quantification of HER2, of Ki67, that are already have developed tools. And the requirement for ESMO following the Delphi consensus that was validated in 3 rounds. The first question, would a prospective trial be needed to validate a class A biomarker? No, we do not need a prospective trial because it's a simple concordance between the evaluation of a pathologist and the automatic quantification of the biomarker. So for this type of biomarker, an analytical validation is enough. ESMO also considers that we need at least 2 expert observers, and there are needed multiple metrics, and I rejoin what Evangelia said before. Actually, we need these multiple metrics because we can have class imbalance, we can have different prevalence of the biomarkers, and by having multiple metrics, we are more sure about the actual performance of our AI model. And also, we need to have a tool that is generalizable. We need to be able to obtain the same results by using multiple scanners, by using multiple protocols, and of course, to validate it in an independent, completely independent data set. The class B biomarker, let's see it, it's this type of horse, if we go back to our horses, is the prediction of AI prediction of PD-L1, for instance, from hematoxylin eosin tissue slides, so this time not from immunohistochemistry. So here, the input is different, so we give another type of slide. The method is different because it's new, it's based on AI, but the result should be the same. A similar example is the prediction of EGFR status, the prediction of other genomic alterations, the prediction of MSI. And here, thank God that Lorenzo was in vacation during that time, actually, and Jakob managed to publish in Nature Medicine his publication on the prediction of MSI. And this was, Jakob is one of the pioneers in digital pathology, and this is one of the first main publications in the field, where the prediction of MSI was performed with a quite good performance. We see an area under the rock of 0.84. And it's actually one of the first proof that with the genotype, we can actually, the genotype is actually linked to the phenotype. But where are we today? Because even though we have MS Intuit, which is a commercial tool that we can use today to actually predict MSI from hematoxylin eosin, it's still not used as it's still not used among the community. And why is that? So there are 2 reasons. First, in order to replace a gold standard, we need to be as good as the gold standard. And not only, we need that the error rate should be less or at least equal to the inter-observer variability or the error between 2 techniques. So it has to be very small. Second, maybe the setting is not the best. If we develop a tool that competes with an already cheap technique in an indication where we will still use that cheap technique, the biomarker will not be useful. the AI biomarker. However, imagine the MSI prediction in a tumor-agnostic field, where today we are unable in every country to screen for all the solid tumors for MSI. But if we would have an AI tool that with no cost would predict the MSI in a pan-cancer setting, it will be very, very useful. Also, let's imagine that we are able to predict EGFR, but with a performance that is not good enough to replace the standard. But what we could do if we have, after a diagnosis, the prediction of EGFR, let's say, with 80% probability, we would say, okay, I will do a rapid PCR while waiting for my NGS test that takes 14 days up to 1 month. I will do a rapid PCR and I could have the results even in 2 hours with the proper technique. And that's how the patient would receive the treatment earlier. So for a type B biomarker, ESMO considers that there is no need for a prospective trial, that analytical validation, the use of retrospective data of good quality is enough, but it has to be compared with a validated gold standard, and the same as before, we need to use multiple metrics and to be generalizability. And then let's stick to the class C biomarkers. Here, it's actually the prediction of treatment response, for instance, based on the AI. And here the input is new, the method is new, and also the results is new. And we have these two classes, prognostic or predictive. In terms of prognostic, I show you an example with for example, the prediction of the risk of future lung cancer, but it can also be the prediction of the risk of death. In this study, the training was done based on trial data, and it was validated in 2 independent data sets from real-world data. But we can also imagine having studies that are poorly prognostic with with other known prognostic biomarkers. And for here, the validation that is needed is considered that for a prognostic that will not necessarily change your treatment, we can use retrospective analysis or real-world data or data from trials, but retrospectively. There is no need for a prospective trial. If we have as a comparator validated prognostic markers, that should be integrated, of course, in the statistical analysis and to be compared with that as well. And the same as before, we need multiple metrics and multiple protocols to have confirmed the validity. For the class 2, which is a prediction, I have the example that, of course, Dr. Garasino is better than me to present it. So this is a type of more or less hybrid biomarker between class A and type C, and class C. Why it's not a class A? Because actually the TROP2 quantification here, it is not just done based on the quantification of the membrane expression, it's done based on the quantification of the membrane and the cytoplasmic expression, and there is a ratio between the two. Although it still uses the immunohistochemistry tissue slide. So with this type of scoring, it was for the first time that TROP2 was shown to be predictive for the treatment with antibody-drug conjugates. And while before we had an expression of TROP2 for example, in lung cancer that was quite high, and we were unable to predict based on simple H scores the outcome with antibody-drug conjugates in this setting. But then, when this score was performed, actually in the TROPION-Lung trial, it was shown that there is a benefit in the patients that express this biomarker as compared to those that do not express. And for this type of biomarkers, I'm very curious what Dr. Garasino will say for the validation, but actually ESMO considers that there is a need of a prospective trial in order to validate this type of biomarkers. Of course, here there is not the case because we do not have other validated predictive biomarkers, but if we would have had them, we would have also compared to those that are already validated. And as a summary, the requirements that are needed actually to validate biomarkers in routine, there are 3 important metrics. The ground truth that has to be very highly qualitative, the performance that has to be high, it has to be generalizability, and also fairness is recommended for the reasons that you heard before. Actually, what you have seen with LLMs that gives like different outcomes for the same clinical scenario if you put different races and incomes and gender that are underrepresented. And here in this article, for instance, that where clinical vignettes were shown to an LLM and changing they had the same clinical scenario, but only the race, income, and gender was changed. And actually, those marginalized groups had more urgent, more invasive, and mental care, health care referrals. Okay, and so would you actually trust an AI model if you see it like without an explanation and you are not sure based on what it will actually predict? So this is a question for the ESMO experts, and despite having experts that actually work with AI, this is a question that was put by asked by Raquel during one of our meetings. If we have a radiomic biomarker that predicts EGFR with a very, very high concordance, would you still do confirmatory testing? And the answer of 1/3 of them, it was yes. Despite a super high performance, they will still do confirmatory testing. And I think we have to work more in order to validate these fields, and also not only to validate, to be sure that after we validate it, we have still a continuous monitoring for data drift, and also to share responsibility for errors, because actually it's not just the developer that is responsible, it's also the healthcare provider that will just trust the AI without checking, and it's also the institution that needs to take account for this, because the institution has to put in place this process of continuous monitoring for data. And in conclusion, so for these AI biomarkers, we need to check very well the ground truth, the performance, and generalizability. We can use the similar validation rules as for traditional biomarkers, but we need for sure post-validation monitoring. We need to fight with the trust of medical doctors and to prove that despite we do not have hallucinations after validation, and these models stay effective. Thank you.
Thank you, Dr. Aldea. It's a pleasure for me now to introduce you to Dr. Di Maio from l'azienda ospedaliera universitaria Città della Scienza, della Salute e della Scienza in Turin, with a presentation on enhancing the impact of real-world data in oncology through AI. Thank you.
Thank you. Good afternoon, everybody. Thank you, Arcela, for this kind invitation. Also, on behalf of our National Society of IOM, which patronates this third edition of this event. And I am grateful for the invitation. Less grateful because I'm not an expert of AI, but the topic is very interesting to discuss about how enhancing the impact of real-world data in oncology through AI. How can I? Okay. This one?
Yes.
Okay. So you can have a look at my disclosure. And I have already disclosed that I am not an expert of AI, but I want not to be too much traditionalist or too much conservative, but in our traditional vision, large randomized control trials are considered the most robust evidence to choose our treatments and to make our decisions in clinical practice. But this traditional vision, of course, now is challenged in many aspects. The first aspect is that in some cases it's difficult to conduct randomized control trials, and I will give you an example in a few minutes. So we can decide how to use, for instance, clinical trials without a control arm, but using external evidence with real-world data as a control arm. And another issue is that we can decide to base our decisions on different levels of evidence, including real-world data. So in the attempt of integrating or to substituting, in some cases, the evidence produced by RCT, by randomized control trials. So we discuss what data are we talking about. Real-world data can have different sources. We can discuss about databases, also regulatory databases, registries, patient surveys, patient chart reviews, observational data from cohort studies, etc. So the sources can be really heterogeneous in our practice, but the aims can be really useful from a clinical point of view. Here you can find a list of some opportunities, so some strengths, but also limitations of real-world evidence when we try to define, to describe treatment outcome in oncology. We know that we can describe treatment outcome in clinical practice with real-world data in a population that is, on average, much more heterogeneous than the population included in traditional clinical trials. So the opportunity is to have data with lower selection bias. We can describe the treatment outcome in special patient populations that are underrepresented or sometimes are not represented at all in RCT. And we can decide to evaluate the outcome in settings where we do not have a randomized control trial, where a randomized control trial has not been performed. For instance, rare subpopulations, rare in terms of histology or in terms of molecular characteristics. So we can produce evidence in a setting that suffers from the absence of a traditional evidence, of a traditional control clinical trial. Of course, we have limitations. The limitations is that the first but also the second limitation have a question mark, because we have to decide if is lower this level of evidence compared to RCT, and is necessarily lower or can be the same quality in terms of data sources. We can, of course, discuss these issues. We have other opportunities. For instance, we can produce evidence with real-world data in setting where we have multiple options in clinical practice and we have no direct comparison within traditional randomized control trials. So we can use modern techniques to compare treatments adopted in clinical practice for the same condition in order to compare their outcome, to compare their efficacy. But you would say that there is an intrinsic selection bias when we as clinicians decide to choose one treatment or the other for that patient. So the comparison is dangerous, and we have to find with the new techniques how to compare in a trustful way, in a robust way, the data we are extracting. And I can continue with other opportunities, for instance, to produce local data for treatments that have been approved with trials conducted abroad in other realities different from a geographical, sociological, cultural point of view, also pharmacoeconomic point of view, and we decide to produce evidence after the introduction of that treatment in our clinical practice in order to produce local data. And what about the situation where, due to the rarity of the disease, or for instance due to some ethical or methodological and clinical concerns, to offer a randomization to patients, for instance a rare situation with a very dismal prognosis where the active standard treatment is the standard treatment is not so active. In some cases, we can discuss about a single-arm clinical trial without traditional randomization, but using external evidence, external comparators based on modern techniques of methodology. And this survey was presented some weeks ago at the ESMO meeting on sarcoma and rare cancers by Diogo Martins Branco, and I want to show you some slides because I had the opportunity of participating into this effort that is interesting because tries to describe the perceptions and of healthcare professionals, including oncologists and also hematologists, and also regulators on the use of real-world data as external comparators in oncology single-arm trials. And this survey was based on the background that real-world data are a potential source of external comparator for single-arm trials. And as I said before, when no effective treatments are available and the prognosis is poor, in principle, a randomized control trial may be conducted, but it's difficult to conduct. So we can decide together with the regulators if is useful for approval of new treatments, the evidence coming from a single arm without a lack of parallel comparator. And so in this setting, the use of external comparators based on real-world data can be really, really attractive, can be really, really useful. And this survey tried to describe the perceptions of healthcare professionals and regulators a few months ago. It was conducted in the spring and summer of 2024. The setting was, as I said before, late-stage disease without effective treatment with a very scanty prognosis. Median overall survival was 3 months. And were presented 4 real-world data external comparator scenarios divided according to low quality or high quality of data, and in terms of the magnitude of the benefit shown in overall survival. A little benefit, 1 month and a half, or a larger benefit of 3 months. In addition, there were 3 control scenarios: a single-arm trial without comparator, and traditional randomized control trial showing also in this case a little or larger benefit in overall survival. And as I said before, participants were clinicians, both hematologists and oncologists, and regulators both from Europe and from other countries. More than 200 people filled in the survey. And it's interesting to emphasize that when discussing about traditional randomized control trials, both healthcare professionals and regulators agree that the advantages outweigh disadvantage. So randomized control trial can be considered a robust source of evidence. But for real-world data, the opinion was not so homogeneous, because if you look at the table below, most healthcare professionals believe that advantages of real-world evidence outweigh disadvantages, but it's exactly the opposite for regulatory agencies, for regulators. Most of them believe that disadvantages outweigh the advantages. And if you look at this picture showing the proportion of respondents that were convinced about the overall survival benefit of the experimental treatment, you see that even with high quality real-world data, when the difference in overall survival that has been shown is modest, only a small proportion of respondents were convinced about that benefit. A higher proportion of them were convinced of the benefit when the benefit was larger, 3 months instead of 1.5, with real-world data high quality. But in any case, when the evidence was produced by randomized control trials, the proportion of people who are convinced about that evidence is higher than what is produced by real-world data. And unfortunately, when the real-world data is produced with low quality, most of the respondents were not convinced at all about the overall survival benefit that was shown. So, according to these results, that survey concluded that, in principle, both healthcare professionals and regulators share a positive perception of the use of high-quality real-world data as an external comparator for patients with advanced cancer when included in single-arm trials. But there are differences between those 2 categories on the familiarity with real-world data studies, and in terms of the belief related to advantages and disadvantages of real-world data. And the quality of real-world data remains important in order to use also for regulatory purposes those data. So just to finish in a couple of minutes, I kept these slides from my last year presentation in this same room, because we were discussing about the limitations of AI, and this survey showed that the most important problem, according to most of the respondents in this survey with the AI, was the lack of standardization in cancer-related health data. So it remains a problem also, at least at the present, for the translation of this very interesting theory into a practice of production of evidence. So, in my opinion, two requirements should be mandatory. The first is the interoperability of electronic health records and data, a very important problem and so hot also in our country. Most of you have read probably this disappointing article appeared some months ago in the Lancet Regional Health Europe, showing that the Italian health data system is suboptimal. The term used was not suboptimal, is broken. So unfortunately, we have to agree, because we all know how we are far from an optimal interoperability of our electronic health records in our hospitals and between our hospitals, and this is really important for research. And the other issue is that I remain convinced that even with the advent of AI, the role of personnel dedicated to the clinical research remains crucial. And so the presence of research professionals in our centers, large centers, small centers, large hospitals, cancer institutes, etc., is mandatory, together with the recognition of their professional figure. If you look at at our IOM FICOG annual volume describing the activity of clinical research in Italy, you see that most centers have not structured dedicated personnel for clinical trials. So this is a problem, in my opinion, also for the issue that we are discussing today. So just to conclude, a few concepts. The first is that real-world data may have a relevant impact in oncology, also from a regulatory point of view, and we hope that in the future this regulatory point of view will increasingly consider real-world data for approval of treatments. Quality of data is essential. I know that Arcela says that garbage in, gold out, but please imagine if you can obtain gold with the garbage, what can you obtain with high-quality data? And at the last point, the lack of standardization for cancer-related health data, suboptimal interoperability, and poor resources for research can challenge, unfortunately, also the use of real-world data. Thank you for your attention.
Thank you very much, Dr. Di Maio. We can move to the next speaker. It's a pleasure for me to introduce Professor Filippo De Bro from the Istituto Nazionale Tumori. He will talk about the role of AI in molecular tumor boards, the point of view of clinicians. Thank you very much.
Thank you very much for inviting me. Ciao Marina. And it's always a pleasure to talk of something that I don't know what to do and how to do. Anyhow, those are my disclosures. I don't need disclosure for this presentation. Here is what the field where in our job we can apply, of course, AI, and today I'm going to talk a little bit more about what we can do about cancer treatment. As you know, we need, on my point of view, AI for many reasons when we are talking about selecting patients for target treatment or individualized or personalized medicine. And the methodology is what you see here. You see there is a need to have some specimen for the disease, to know something about the person that we are going to treat, so how the metabolism, the body, the immune system is working. We should correct all this data. We should explore if there are some regulatory limitation about to use or apply any kind of treatment, and of course all this should provide something that is going to be helpful for the patient. So the first thing is what we need. Well, we need quick and complete analysis of any available data on targets, indication, studies, regulatory, etc. So we need to collect all this information very quickly, and probably to make them to interact each other, because sometimes we are accustomed to see only one thing at a time, and the AI probably can help us either to have a wider vision of the whole system, either to provide how to improve it in the future. The problem for arriving to integrate all the data in clinical trial can be raised according to a very simple sample. This is the experience that we have in National Cancer Institute, of Milan, of course, and you can see that we have a different distribution, but if we are talking about a patient with actionable target, we have about 30% of patients that 50% of patients that can have an actionable target. But if we're looking for the molecular profiling and the molecular variant beside the benign that we found in our analysis, this is an analysis done on almost 2,000 patients. The majority of this analysis show that there is what we call a variant of unknown significance, which is something that let us without any weapon, because we don't know if something is working, we don't know if something could work, if you don't know if this is really something that is not a target and so on. As a matter of fact, in our practice, you can see that even if we analyze more than 2,000 patients, the percent of patients that arrive to reach a proper treatment, individualized treatment, is about 10%. And this is the same result has been obtained in many trials where a molecular profiling was associated to the clinical decision making, even if the number of patients that probably have actionable or target suitable for a treatment are much more of that. And why? Well, that can happen also because we do not have only the actionable or non-actionable, but what is uncertain significance means that we don't know, so we should explore. There are no data, no enough data to support those as an indication. And besides the fact that we have to treat patients. So we have also the possibility that if we are not quick enough to define the target, if we are not quick enough to find a way to treat the patient, we are going to lose opportunity because disease progression can reduce our patient population. And this is exactly what you can see. And according to this, in our experience, you see that always out of our nearly 2,000 samples, there are about 30% of them that have an actionable or investigational class of target that can be treated. And as you can see, among these, more than 80% of the patient can receive a treatment. There is another 30% of the patient where there is probably a problem of mutation resistance, something that is an evolution in terms of tumor development and tumor biology development, where still we have some kind of opportunity to treat them in at least 1/3 of the cases, but the majority of patients or variability do not have yet a personalized indication, and this is a problem that we should solve. How we can solve? I'll make you very few samples. Those are the chemical structure of EGFF TKIs. You can see they are very different, and the binding site for any of these drugs that are all eating EGFR, if it's mutated, is different. And those are the number on target mechanism of resistance just for EGFR. And this is what you can see as a dynamic process. According to what kind of drug you start with, always if we are considering EGFR as a target, you can see that over the time, the distribution and the evolution of the disease has different subclass of genes or mutation that can be very resistant. And you can see that among the available drug, for some reason, there is someone, in this case is afatinib, for this kind of particularly EGFR 724AS, the affinity for this target is much higher for afatinib than for osimertinib or erlotinib. So what do we need more? We need to have model to design different kind of studies, or even to assess, to give to the doctor the possibility to decide if to try a drug, even if we do not have enough information from experimental, preclinical, or clinical data, when we have something that we suspect to be an actionable target, but we do not have information, so we call it a VUS. And what is the system to perform this? Docking. So means trying to understand in a silico, any model in silico, if your drug or the drug, or if there is any drug that can have a kind of interaction with the kind of the molecular profiling that we have to deal with. And the molecular docking is one of the most important, on my point of view, emerging tool that we are going to use in the future, and probably AI is going to help us a lot about this, not only to put together the data, but also to give us information and learning how to improve this kind of approach, which is based on very simple concept. We should have a ligand drug, a substrate, a kind of detector to see if there is an active site for the ligand drug, and after that, the docking in silico can tell you, for example, that your drug is eating also the wild your gene when it's in a wild form, not in a mutated form. And sometimes that can be also somehow active. You know that, for example, KRAS is a drug, is a gene that even if it's not mutated, is leading a lot of process when you are talking about a transmission from surface receptor in the cell up to MAP kinase pathway. And this is some really model of what you can look at with this kind of docking. Here it's very difficult to show you, and I'm not a pharmacologist. Those data are provided to me by my friend Romano Danesi, that made us a presentation about this, and we are working to develop this kind of approach in the Institute on what is a molecular interaction model for this kind of gene. The same thing is seen for ALK mutation with a double mutation for ALK, and to understand if there is a drug that is able to bind ALK even if there is a double mutation inhibiting the activity of the gene. And this is something that can happen exactly for sotorasib, which is a KRAS inhibitor just for the G12C subtype. So my conclusion are, on my point of view, there are enormous need to integrate artificial intelligence in the work of tumor molecular board, not only to have more information and quick information about what we have available in terms of study, in terms of approved drug, in terms of regulatory changement, and also in terms of what are the conditions of the patient. So integrating the clinical and the biological data, but also about what we can try to understand, either to define eventually unknown activity of drug that are anyhow docking and binding to a target, even if we do not know if that target has a clear significance in terms of activity, and or to overcome resistance of the drug that I show you, as I show you, is a very dynamic process. Thank you very much.
Thank you so much to all the speakers to be within the time. We can have some minutes for discussion if there are any questions from the floor. There is one question there. Sorry. It's my fault. Sorry. We have another speaker. Sorry. Okay, the next speaker will be Loïc Verling from Lyon, France. And the title of the talk will be how to use large language models in order to assist molecular tumor boards. Sorry.
Sounds good opportunity to be on stage, and hopefully can do it. And thanks a lot, Arcela and all the committee to have invited me. To discuss this very interesting and motivating topic because we are in a molecular tumor board, we are physician multidisciplinary team, and that's where we can implement AI and LLMs in our clinical practice. And that's where we can ask the question of the impact of LLMs in our practice. So that's some of the questions I want to share with you today. I have a lot of applications that I could discuss for application of LLMs, and you see the list. I'll go through quite quickly into all those applications. There are some reference, and you can go deeply afterward. But what I want to say to you is, as evaluators, as clinical evaluators of those AI tools, that's what we need to check, the handshake. I don't know what you feel about this picture. So it's an artist who made that, I think, from a little bit of AI. If I want to put some metrics out of this picture, maybe I will say, I don't know if you agree, maybe AUC 70%. But there are big problems, I think. I don't need to zoom in. So when you see AUC 70%, just remember about this picture and maybe go a little bit deeper into what exactly there is in the prediction. Of course, AI is very efficient, and you've seen so much examples. So in there are real, and nature is incredible. So there are pictures of nature and AI-generated plants and big stories around behind these pictures. So maybe I'll tell the true from the false next, because I don't have time yet. But for example, at the AI Cancer Research Summer School this summer, organized by Arcela, if you have the chance to come, there are many things to tell about these flowers. But just dig into our topic today. So at MTB, for those who don't know, what we do, we turn data, and mostly molecular data, but also clinical biological imaging for some, and histopatologic data, and among others, into treatment recommendation, mostly targeted treatment or personalized treatment recommendation on the cancer of patients, and also preventions, because we have a germline variant, and there are more and more tools for personalized preventions. So that's our task. We do that at the hospital, but we also are doing that more and more often virtually, and that is very interesting because it allows us to communicate between hospitals and between countries. And so these are the names of different European projects that promote this approach. And this is important because there are patients, for example, patients living close to borders that could go to clinical trials in hospitals that are closer to their house thanks to such initiatives. And that's also the opportunity to evaluate tools more internationally, an AI tool, of course. So first topic, LLM for molecular data. In fact, it's a very exciting field. And just to tell you, I think the state of the art right now is Evo 2. It's a preprint. It's built on other very important, so it's very big hybrid convolutional attention-based language models. So, but it's very big, quite complex architecture, and it has read trillions of nucleotides, and from that it can infer the VUS, the variant of, and the pathogenicity of variants. So there's a proof of concept on BRCA2, for example. So that's very impressive. It can also generate new DNA sequence that maybe could bring to some life once. We'll see. So that's very impressive. But on the right side, there is a lot of noise and sound around Varshat. But I don't know if you've tried this, but my experience is very bad. So you have a lot of noise, a lot of advertisement, but when you use it, and when you read the papers, there are no clues about the models, the data, how it works, and when you try it, it doesn't work, or it's useless. So be careful and go into the papers, go into the evaluation to just choose your best tools. Another application that we are exposed to in our everyday life at the hospital is ambient listening. It's, scribes, the speech recognitions. And that's based, on it's not only LLMs, but it's more similar, I would say. I've spotted so there are a lot of companies that do that. So I've spot Dragon and Praxi AI because that's the one we are using or in our hospital or collaborating to, but there are a lot of those. In general healthcare, they have shown that they reduce the burnout, they reduce the task load, etc. There are a lot of publications, you can see one here, but there have not been any evaluation in oncology, and nor in precision oncology, so in MTB. So we don't know what we are using, and in fact, when you use it, it's a nightmare. It doesn't know any genes, it doesn't know any trial names. So that's something we should do. We should also publish the performance of those tools and improve the tools so that it really helps us. Because for me, it's increasing the task in everyday life. So sorry to be a little bit pessimistic, but that's you and the community who can increase the performance and utility of these tools. Then there is a lot about LLMs for targeted treatment matching. So there is this paper from Carter and his collaborators, and there are lots, but there are good reviews on these topics, and you can see that from oncology application, there are 88% of application of LLMs that are dedicated to treatment matching with clinical or molecular characteristics. And when you go into a deeper field of healthcare in general, treatment is also a very, very important percentage of the applications. Whoops. Clinical trial matching, I think there's a lot to do. So this is a project where we implement some LLMs, we implement some trial matching tools, and we develop our own predictive tools. But the point, I think, is to install that in different hospitals. Why? Because the impact is to identify for all patients the clinical trials that they could correspond to, and then increase the knowledge and the equality for patients to access to clinical trials. And that's really the impact that we should go to. So that's technologies, this is fun, this is behaving quite good, performing well. But the final goal is to have the patient access clinical trials, new treatment modalities, and that's clearly what we do. So it's not, this topic is not all about technologies, but you have organization, you have communication, and you have policy a lot. So you have also to combine your technologies with things that could help the patient. And finally, the application I like the most is patient information. So the LLMs for patient information is really having a lot of potential. Why? Because we want to screen maximum of patients in terms of molecular alteration. We want to do DNA, RNA, protein level screening for all our metastatic patients, let's say. But for that, it's difficult to have enough human resource to communicate those to patients. And in fact, right now, most physicians don't give the results of the molecular testing to the patients. And that's a way we can use LLMs to do that, and that's very fresh results I share with you today. So we evaluate a company called Vulgaru that does it, so it's a specialty, and like just inferring that on 40 patients, it gave very, very impressive results. The reports were very impressive. They were very comprehensive in terms of vocabulary, etc. So there were almost 100% of correct or partially correct, but no big errors, no hallucination. And when you do metrics for readability, we see that we significantly improve the readability for patients of these molecular tumor board reports, which are very technical by principle. So there are many remaining challenges. I think one of the biggest challenge is, and this is a fact, you is decreasing in terms of clinical trial readiness. So the problem here is that if we continue this way, we will have less and less clinical trials to offer to patients, so less and less treatment at the end that could be approved and funded by EU. So for that, molecular tumor board has a role in screening the patient because more than 80% of treatments nowadays are targeted to molecular alteration. So we are at the core of improving that. And so if you want to screen a maximum of patients on their molecular alteration to orient them to treatment, you have to go much higher. And that's something that the pharma companies are looking at. So, but it needs a lot of technology to automatize or semi-automatize the process of MTB, which is quite complex. And this is a big work we should do together as a community, and some European projects are really digging on that to improve the molecular screening of all patients around Europe. And there are a lot of links. I won't go into the detail because that's at the end of my time, but there are a lot of links to make Europe important consortium and environment to improve personalized medicine, to improve clinical trial orientation for patient and readiness for pharma industries. And there are a lot of initiatives, so that's a good time to work on this topic. So with that, thank you a lot. Sorry for the 1 minute 40. Okay. Thanks a lot.
Now we have time for discussion. I don't want to say loudly, but it's the correct time. And so if there are any questions from the floor, maybe there was one question before.
Thank you for the presentations. To be
maybe
fair,
we can invite the speaker here. So
yeah,
we can invite the speaker here for some questions.
it's okay. Yeah. Okay. So to be fair, it's rather a comment than a question. The thing is that, but I'm just thinking this whole day that we see what AI can do, and it's truly inspiring. But to play devil's advocate, the problem is that currently any AI algorithm, large language models, and so on, they fall under the medical device regulation. So at the end of the day, we have to admit that it is a product. And when we say that it's a product, you must show the value of your product, and you must position your product. Because otherwise, they will not reach the regulator, they will not reach the clinical community. So what I'm really curious of, shouldn't we consider what AI should do in one specific setting and not all these broad potential applications, because then it's just impossible to design clinical trials, collect clinical data, or show anyhow the value of this tool.
Wants to answer?
So actually, that's why ESMO made these recommendations. We cannot design clinical trials for everyone because it's costly and it's impossible, and not every question will require a clinical trial. We need to take advantage of real-world data. We need to take advantage of clinical trial data, and this is also a challenge because you need also to convince pharma to give you access to clinical data from the trials in order to have access to high-quality data. So some of them manage, like Dr. Garasino, and we will have biomarkers that will probably be validated with high quality data. But I agree with you, it's very challenging, and today we do not have the necessary performance also for the majority of them in order to be able to use them in routine. And the problem is that if we start using in routine without having a good performance and validation, then trust will be lost as well, and we will be at very high risk of doing more damage than good to our patients.
Yeah, exactly.
I agree.
Thank you.
Another question from Alberto.
Maybe I can complement. So the molecular tumor board, I think, is a good place to do some evaluation, and you can even do prospective, non-interventional or interventional evaluation of those tools. Well, if you have a tool that is very specific for lung cancer screening, this is not the place, MTB is not the place, but for innovation, because this is our tradition to evaluate innovations. For example, MTBs were born from NGS sequencing, and we continuously evaluated our activity within those innovations. So now it's AI, we are in the AI area, so this is the place to evaluate those and combine with the necessary demonstration of safety and efficacy. Yeah.
Can I? Alberto. Thank you to all the presenter, and also very nice initiative by ESMO, to kind of evaluate AI biomarkers. I would be curious to see the other side of the world. So asking AI expert actually, what would they reply to the questions? So that would be also nice exercise. I've just comment and asking for a reflection about the biomarkers. So predictive biomarkers, predictive AI biomarkers are of course very, very useful, but I think they are very rare. And I think the reason is because the model we use with the AI are always trained on retrospective data of population receiving one or two type of treatments, so we cannot infer what would have happened to the patient with another treatment. So I think there is a lot of work to do on the type of model we use. Probably should require more logical model and so on. Regarding prognostic biomarker, and this comes also from the experience with Raffaele. So we made a prognostic model pre-surgery prediction of dying from kidney cancer. And when we talked to someone to certify, they said, well, actually, there's nothing, it's not a biomarker because it doesn't trigger any actionable, right? Just tell you patient at higher risk. So the question is, since prognostic biomarker actually are always associated to trigger action, can be, for example, changing the list, the priority of people getting surgery. So I was wondering, when you kind of say, okay, this is the validation path, and the difference between prognostic and predictive biomarker. Did you take into consideration a prognostic biomarker, even if they don't suggest treatment, they might always be associated with actually a change or a decision in the process? There can be, giving priority to patient at a higher risk and so on. Well, was that taken into consideration?
Yes, actually, there were a lot of discussion based on this. We initially separated prognostic biomarkers into classes with intervention and without intervention. And actually, after various discussion, it was considered that it's rarely that a prognostic biomarker does not have intervention, in the meaning that you will still probably offer to your patient earlier palliative care. You will still do something for your patient that is different once you know that it has a worse prognosis. And despite this intervention, but it's not an intervention of escalating or de-escalating treatment for which you will need a trial probably. It's more for these purposes of more monitoring, earlier palliative care. It was not necessarily considered that you need a trial, at least in the voting system performed by ESMO.
Thank you. If I can add also a question to the speaker that talk about the use of real-world data versus clinical trial. I was wondering if there is a role in actually using synthetic data or real-world data to actually generate the control arm instead of generating, or looking at real-world data for the, let's say, intervention. And if it is more useful to use real-world data to actually create control arms, virtual control arms in the trial.
Massimo, microphone.
Sorry, can you repeat more the question, because I was replying to
Yeah, Alberto, you want to repeat?
Yes, so the question is in the value of using real-world data or synthetic data in actually generating the control arms instead of looking at the, the treatment arm of a clinical trial. So using
the
all
control arm. What I was discussing before was the potential use of real-world data as a control, as a comparator. So you treat in a traditional way the patients within the trial with the experimental arm, in the experimental arm, and you use no randomization, but a control arm produced with real-world data. And the problem is that, as you have seen before, you can observe a magnitude of benefit, for instance, in terms of overall survival, that if it's very large, maybe will convince yourself and also regulators about the efficacy of the experimental treatment. But if you observe a small difference in terms of magnitude of overall survival, probably maybe if the same difference within a randomized trial will be trusted as useful for approving a drug, but the same difference could not be enough, considered enough to approve the drug with this innovative design. I don't know if it's clear.
And I think the other comment related.
Can I just add, just to add something related to this, because I think this is a very good point, because it's a very open question. So with the recent European Society, Interdisciplinary Society for AI and Cancer Research that we have founded with most of friends that are here, this is the first questions that we are trying to reply with an open paper, because the EMA and have discussed also in different tables with ESMO. So, and obviously this come up also in other meetings. So together with a group with Carlo Rossi Chavinot, the legal that was today, we have put together an interdisciplinary team to try to answer to this question, because I think there is an answer, let's say, that traditional arms versus synthetic arms versus real-world data arms, which is the best. What we are trying to do is to give some guidelines and the idea which can be better in which use case. Because to my opinion, there is different reason, different, let's say, spaces where, for example, real-world data is there. It's a very, for example, immunotherapy has a good real cohort composition. We have treated from 10 years now in non-small cell lung cancer immunotherapy, and then, for example, a real-world data arm can be very nice to be used. However, in some other cases, in rare diseases, for example, in order also for augmentation, for other reasons, synthetic arm is needed. So I don't think there is one of the other. For sure, either one of the other is needed in some situation, hopefully in the next future, to absolutely substitute the traditional arms.
I agree.
If I can add another concept, is that you know that on average the prognosis and the outcome of patients treated in the real world is more heterogeneous, and maybe the prognosis can be worse than those selected treated in clinical trials. So if you compare formally a selected population of the experimental arm with a comparator which is taken by the real world and can be worse as overall prognosis, this could favor the experimental arm, and the comparison could be biased by this. So it's very difficult to formally compare these in a unbiased way and convincing way also for regulatory agencies.
And just to add, I totally agree with what you mentioned. The problem is around data, right? We also do not have to forget that synthetic data are learned from real data. So if we don't solve the problem of the quality of data, we will also have synthetic data that are not representative, or maybe they are close enough to actually real data, so they are not synthetic per se. So I totally suppose what you said, that, and if we want to be the control arm, we will actually have structured data that you might not have collected for your clinical trial intervention arm, because there you really select few elements. If you want to reproduce, say, a standard population, you will have to have structured data about comorbidities, drugs, and so on, which is much more difficult than having 5 to 10 elements in high quality.
That was the reason why I said to Arcela, okay for garbage in, gold out, but please consider that you need high quality to convince also regulators that you are producing a robust evidence.
Thank you for for the discussion. We have to move to the next session, and I'm very happy to introduce the next speaker, Professor Marina Garassino from the University of Chicago. She will talk about AI in drug discovery in the era of immunotherapy. Thank you very much, Marina.
Okay. So, hello everyone. It's a great pleasure to be here, and it's a great pleasure also to give this talk, because it's one of the part in which I have more enthusiasm. I don't want to spend time that AI demonstrated utility in clinical fields and drug development 100% will be one of the most important. We know very well how long it takes to develop a drug in 2025 and also how much money it takes to develop a drug in 2025. And for this reason, I just want to be provocative in this talk because I presented with the economists in my institution. We presented a paper together with the director of my cancer center and two economists, a paper showing the economic infeasibility of the personalized medicine, and clearly the solution is the artificial intelligence. You know that I come from the lung cancer as a background, and for the people who are not here from this background, in 2003 the EGFR mutations were discovered, and since then we started to have a lot of targets targeting specifically the patients with this kind of alteration. But we know also that in the same group of the same alteration, there are an incredible number of variants for which it is impossible to say that for the same target you have the same reproducible response to the targeting, to the tyrosine kinase inhibitors. And so clearly you understand the big heterogeneity that we have not in lung cancer but in all the tumors. And so what is the personalized medicine in this chaos that we see? Another thing that you can observe is that since 2003, you see that there is a huge number of target therapies that started to be present, but you can also see that for the most rare alteration, like for example NRG1, HER2, and also NTRK, the number of clinical trials is 1, 2, or almost not existing. This is visible also if you ask clinicaltrial.gov. You see that for EGFR, which represents about 10% of the patients, if not more, there are an incredible amount of clinical trials, but for NTRK, there is almost zero. And second, if you want to develop if you want to develop drugs for the rare population, there is a second problem, that is we don't have enough patients. We know that about only 10-15% of the patients are included in clinical trials. For a very rare population, it's really impossible to conduct a randomized clinical trial. And so this is what could happen. It could happen that the pharma companies and also the biotechs will not invest in rare targets as they are not investing in rare tumors. So how can we solve that? We did some calculation, and you can see that if the target is expressed in 5% of the patients, the cost of the clinical trials we used both in the US calibration and the world calibration can go from 24 billions and can go to 2.7 trillions if the target is 0.05. So this really will create a disproportion of costs. The companies will not invest in rare targets, and we will not have the drugs for the patients. I don't want to stay to spend time here, but you see that if you increase the number of alterations, the cost goes to zero. The benefit for the companies goes to zero. And so the companies will never invest in this kind of alterations. So what we are doing, but we are not the only one at the University of Chicago, we have a great privilege to work with the Argonne National Lab. I don't know if you are familiar with the Argonne National Lab, but the Argonne National Lab is a national lab, and there is the biggest supercomputer in the United States. And so we can start from a target. We can screen, this was all the 1 billion molecules, but you will see that is even more. We can do a drug modeling in silico, then we can create the drug, and then we can go in cell lines and animal models. This process was also described in a very important Nature paper a year ago. You see on the top of the slides the whole process for which you have the target, you discover an active compounds, then you find the biomarker, and then you run the trial. But on the bottom, you can see how we can do with the artificial intelligence. That means that you can go to the target identification, to the drug discovery, the synthesis, planning, and automation, the preclinical trials, and then you can think to go in a post-marketing surveillance. So this clearly, the first part is the target identification. I don't want that you become, I put all these names just for the people who are, who knows everything about artificial intelligence. But just to tell you, and Luca taught me some years ago this story, these people won the Nobel Prize because from a sequence we can rebuild the protein. AlphaFold is one, but is not the only one. And with the new molecule, we can also predict not just the protein, but we can also predict the interaction with other proteins. So we can also create a sort of dynamic environment in silico for which we can really see if we target something, what happens to the other proteins. This is an example of what you can do. This is from the lab in Argonne National Lab. I hope that it doesn't work, unfortunately, the video, but in any case, thank you. So you can see that you can really explore the entire structure of the protein. You can see the spikes. You can see how the protein interacts with other proteins. And you can, in that way, you can really think about the docking. I think that I need, okay, and this is another way to represent the same structure. There are other modules and other simulations for which you can also see, because the proteins are not in a state for which they don't move, so you can reproduce also the movement of the proteins, and you can clearly create predicted states, and so you can also predict the docking. The process is becoming very fast with the advent of supercomputers, but many of these simulations can be done also with normal computers or not very potent computer. So once you have the protein, there is the second part, which is really the drug discovery. Here again, you can see some models that are basically able to see the molecules, and sometimes if the molecules are too big or too difficult, you can also cut the molecules in pieces and see how the pieces of the molecules can interact with the proteins. And you can do a virtual screening, a de novo screening, and the ADMET prediction, which means that you can also predict the toxicity, the absorption, the distribution, the metabolism of the drug that you are going to administer. This could be a possible pipeline. The possible pipeline means that you can, once you have the protein, you can show the molecular representations in monodimensional way, in a two-dimensional way, on a three-dimensional way. And again, as I told you before, all these names that maybe only the people who are in the field can understand, you can also really see how you can create a molecule that can interact properly with the target. This is an example just to give you how we are very close to this situation. With the supercomputers, you can screen 20 billion molecules in 40 minutes. So clearly, and we know that the technology will go very fast, so it is possible that in the future these numbers will become even lower, and potentially we can arrive, clearly not tomorrow morning, to a situation where we have the patient in the multidisciplinary tumor board. In the tumor board, you can identify the potential target because the molecular biologist can tell you maybe this is an actionable alteration. You can recreate the protein in minutes. You can run the system with 22 billion molecules in 40 minutes. And I don't know if you are aware, there is also a big field of research with the three-dimensional printers that are working also on how to produce the drugs in this way. So I know that is crazy to think, but maybe when we will be retired or old, we will see that you will have your alteration, you will have your protein, your drug, and the things will be totally different as they are now. Moving here, there is another step that is called synthesis planning and automation. Basically, there are two methods. One, you can synthesize the molecule from the beginning, just adding pieces, or you can also create automated system for which you can create immediately the synthesis of the compound. There is not one best, there are different solutions, and clearly it depends on the type of the proteins and the interaction with the other proteins. Clearly, we need preclinical studies, in particular now. So, unfortunately, the people like Sabina are not over, or Luca are not over yet, because we are in the process now that when we have a new compound, and think also that is not just a new compound. What you can do is also repurposing existing drugs for which you already know the toxicity, do exactly the same process and arrive to have a drug. So clearly you have, the drug is totally new and the target is totally new, you can take the target in the cell lines, in the animal models, and then you can go back again in the in silico lab. Another thing that I find very interesting, we are working with the LLMs on the creation of a sort of foundation model of cancer, where we are trying to invent eco-scientists. Basically, you can give, putting together all the possible available data coming from literature, coming from databases, coming from everywhere. We created this sort of co-scientist. This is an example, just suggests a way to design a novel biological therapy for targeting a protein. And you can give all the constraints to the system. And you can run, I think here I have again the video. Thank you. So you can run the process. It takes not so long. And you can arrive to a result like this one. So top 3 drug repurposing hypothesis. And these are possibilities, nanobodies, cell-penetrating antibodies. So you can have already an idea on how you can create your molecule by using the LLMs. This is another example, and you can ask to have all the protein and protein interactions, and in that way you can work on moduling the drug. Maybe you can think that I'm crazy and I'm dreaming. I'm not crazy, I'm not dreaming, because this was already done. This was one of the first examples, was like almost 2 years ago, was published, and there was the identification of a target. As you can see, there was a in silico creation of the drug, and then there was clearly a bioassay already created, and after the bioassay, there was the clinical part. So This was done in 30 days, and as I started in the beginning, this was done in years and years with the work a lot of people in the lab rebuilding the protein. It took a year just to rebuild the protein, then all the pharmacological screening with the libraries and everything that you know very well. So this was done in 30 days, and I can tell you that this can be done even less than 30 days. Clearly, the clinical trials are the end. I think that today we spoke already about the digital twins, but there are many other possibilities of trial simulation, patient stratification, outcome prediction. The clinical trial simulation can tell you also the likelihood of detecting a treatment that is effective, and they can help also in the post-market surveillance. So to conclude, I think that the future for sure will change. We need a lab like this one to do the drug development in an academic institution, because you need the computational part, the structural biology core, you need the clinical trial core, and you need all these things. So it's not easy, it's just the beginning. But the good part of the story is that we calculated the cost. Let me see, these are too difficult also for me, but here, can you go back one, sorry? Just to show you that if you don't have a drug that is already approved, also with the survival probability of 60%, there are a lot of incentives, economical incentives, to go through this process also for very ultra-rare populations. So the revolution is already taking place. What I have said is not far from the reality. If you open the website of a lot of pharma companies, this is already in their website, because it's not just at the University of Chicago, but almost is everywhere. And I truly believe that the future is in science of science, because we need to create multidisciplinary teams coming from the lab and arriving to the patients that are rendering this process possible in the future, and for all the patients, also those who have the only single mutation in the world. Thank you for your attention.
Thank you, Marina. It's my pleasure now to introduce to you Dr. Dean Ho from the University of Singapore in Singapore. And thank you for coming. Thank you for being here.
Great. I'm going to try to keep everybody awake. Thanks for sticking around for the end of the session. Thank you, Arcella, for the kind invitation. I am currently at the National University of Singapore. I was previously at Northwestern and UCLA, so there's a lot of Chicago people, I think, here. I'm going to talk about our work in using a novel algorithm we developed called Curate AI. And there's been a lot of good discussion here about trying to gain acceptance from the clinical community, validation, et cetera. I think we've worked through a lot of those issues. Here's my disclosure, and I'll talk about that today. All right, so we talked a lot about the importance of quality data. I argue that the data we actually need to properly treat people doesn't exist, right? So the work that we do focuses primarily on treatment, right? We don't do biomarker development, we don't do diagnostics, we focus on therapeutics. We do things like dose optimization, et cetera. But the challenge is when we do treatment of patients, we change over time, right? When we talk about personalizing healthcare, we already know we're different from each other. But the thing is, even a single patient evolves over time. However, our treatment of that patient is based on a snapshot, right? It's based on a snapshot of their biomarkers. It's based on an image. But people evolve quickly enough that a patient's optimal dose on a Monday can be very different for that patient a few days later, a week later, even a few hours later. And these are things that we've seen with the patients that we've treated. So then I would ask then, why is treatment based on a snapshot, right? Why is it based on a single data point sometimes? So when we think about doing personalized dosing, people ask us all the time, how many patients are you deriving your data from? The problem is, if you get data from 1 million patients, but you're only sampling a couple data points from each person, we're actually not able to use that data to dynamically adjust how we treat these patients. All right, and so the key challenges that we face as people that use data to try and treat patients is that prospective use of AI is actually very rare. I think it was mentioned a little bit today, but actual prospective implementation is not common, right? There's a lot of retrospective use. There's a lot of hypothetical or would-be validation of AI. And so with that being said, getting snapshots from a lot of people is not going to cut it. It's not going to be enough, all right? And so to solve this problem, we developed a novel digital twin technology, and what you're looking at are effectively three-dimensional curves that we use to only prospectively dose adjust patients. So we don't have internal data validation, external validation, that's all retro. Our external validation is only patients that we treat tomorrow, right? Because you can get tons of data and say, yeah, these people would have responded. They would have done well hypothetically. But every day, our institute that I direct, we make prospective dosing recommendations to patients at our hospital and our healthcare system. All right, and so I'm going to show you some actual prospective examples of us treating patients. This first one was published in NPJ Digital Medicine not too long ago. This is a patient with Waldenstrom macroglobulinemia, which in Singapore is quite rare. You get like one patient every few years. This patient was brought to us, and if you're looking at the data on the left, these are their, their hemoglobin levels, et cetera. The bottom there are the digital twins. These are curves that we actually use to dose this particular patient. This is an outdated slide. This patient was brought to us a while ago, in fact. We had hoped that the patient would be with us for about 12 months. It's actually been over 3 years now, okay, and this patient is still with us. We've eliminated blood transfusions and we've reduced dosing by about 18% for this patient, saving more than tens of thousands of dollars now for this patient. In Singapore, if we reduce the dose, the patients actually pay less. Our cost savings don't include the savings to the healthcare system by reducing the need for readmission. We don't solely treat single patients. We did cohort studies. A couple years ago, Arcella, we met up in Chicago for ASCO. I gave a presentation on this cohort that has since published. We published this in NPJ Precision Oncology actually just about 2 months ago. This is a cohort of solid cancer patients with CRC. If you look at the right side of each profile, these are respective curves of these patients. All right, so I'll tell you that what we predominantly see with our patients that we use Curate to adjust doses for is that we can reduce the dose for some patients to increase efficacy. All right, for some patients, if we reduce the dose at the right time, their efficacy goes up. And that efficacy is validated by biomarker, by imaging, all of the above. But I want to emphasize that we're also not trying to low dose every patient that we treat. That's actually not the objective. All right, we are guiding dose based on efficacy and tox, but that efficacy component has allowed us to reduce dose. This trial is a little bit different. This trial, we had patients where we were able to reduce dose to increase efficacy, but we've also had patients where when you give them the regimen at standard dose, right, which is a high dose, nothing happens, right? Their markers get worse. But the trial protocol allows us to fully calibrate the patient, and for some patients, without changing the drug, just by reducing the dose, we flipped non-responders to responders prospectively. All right, and so that was a shock for the clinical team because it's quite common to have patients that don't respond, right? Standard regimen, standard dose, you move them to something else. But in this particular case, by using the respective digital twins, we were able to flip non-responder to responder. I want to emphasize again, we do not use population data to train an algorithm to treat the next person that walks in the room, right? Nobody's data impacts anybody else. Our model uses only a patient's own data to address only their own care dynamically, all right? So in so doing, a couple things happened, right? We can eliminate bias more efficiently there because, again, nobody's data is impacting anybody else. More importantly, our Curate algorithm was developed using neural networks 10 years ago, validated in vitro, validated in vivo, now validated in human. But during the process of doing our qualitative research with doctors, nurses, pharmacists, allied health, everybody, we actually kicked AI out of the whole workflow. The Curate algorithm is actually pure algebra now, all right? Because by working with everybody, working with behavioral economists, behavior change, workflow optimization, change management, it's actually just algebra now. But we would have never known how to do this had we not utilized the neural networks 10 years ago. All right, so we talk a lot about implementation, about talking to the right people. If you look at my institute, I started my institute about 5 years ago. 5 years ago, my institute was mostly engineers working with doctors. Now my institute is about 70% social scientists, behavioral scientists, implementation scientists, behavioral economists. My very first hire, I had a vision for this, my very first hire into the institute came from the insurance sector, right? Because we wanted to make sure that our workflows were designed for real implementation. This one I'm going to go through quickly. I'm not going to get into it too much, but something interesting we found with our recent trial was that when we kept trying to increase the doses for patients, we had only a few instances when the cancer markers actually went down, right? We actually saw many more instances where by lowering the dose at the right time, the cancer markers actually responded favorably, right? So I think convention for the field is keep driving the dose high. We show that if you can manage the time component, right, you can actually help more people by giving them not necessarily a lower dose. We never go above MTD, but by giving them the right dose, by really ascertaining if this patient is going to be a responder or not, right? And so for data, especially with treatment, for pathology, radiology, diagnostics, drug discovery, the amount of data you get, that matters. But for prospective management of dose, it's not always about how much data you get, right? It's how you get it. In our workflow, if a patient walks in the room today, we have no data on this person. What do we need? We actually need to expose the patient to variable but safe doses of the drug. We need an actionable marker that the clinician will believe to change dose with. And we use a few dose modulations for that patient to craft the curve from which we can then guide the dose. And another thing is synergy. When people are given combination regimens, people ask all the time, is this combination synergistic? However, synergy is dynamic too, right? Synergy is not a static thing. And so you'll never know if a combo is truly synergistic for a patient unless you look at the interplay between the drugs over time. And so when we calibrate the patients, the doctor themselves builds the data set that they themselves will use to approve the final dose recommendation, so there is no black box anymore. All right, and so moving next, I'm going to totally, I told Arcella I would totally deviate. I knew I was the last talk. People ask me all the time, they're like, yes, people change over time. Does this stuff really work, right? Does the notion of building a digital twin for a person and understanding how they change really work? Does it only work for oncology? Does it work for other indications? I'll say that our very first in-human trial was done for transplant patients. After that, we ended up moving to HIV patients. After that, we moved into oncology, blood cancers, solid cancers. And about 2 years ago, I got IRB approval to implement the digital twin technology on myself, okay? And so I'm going to share my data, my own data today, of an experience that I went through where we actually made a digital twin of me to actually address my own metabolic health. So this was me a few years ago, all right? And there's no AI in this photo, okay? This is really me, all right? if you look on the right, it's a series of data I collect on myself, which I'll show you in a second. And we launched a trial called the Delta trial, all right? We call it Delta because we use dynamics to really understand how I change over time. And we looked at my metabolism, and I'll show you some of my microbiome data, my sleep data, cardio data, et cetera. And to do this trial, I wasn't sick, but I implemented a regimen that allowed me to kind of baseline myself so that my markers really do have a lot of flexibility to them, right? So if you look at me now, I fast about 20 hours a day, all right? So today I arrived this morning from Singapore, and I got to the hotel about 9. I managed to eat a little bit then, and I'm not gonna eat again till tomorrow when I go back to the airport, all right? And I do this quite regularly. Twice a month, the IRB knows I do this almost every week, but they allowed me twice a month to fast for 48 hours and to do blood dynamic tests before and after, all right? I work out at least 90 minutes a day, worked out today, still got the workout in, and my diet, sadly, is a little bit boring. You can see some examples there, but it works for me, all right? So the question I get is, did this technology work for me? On the left is 2021, and the right is 2024. No AI for either image now, in this case, all right? In the middle are my biomarker dynamics, looking at my sugar dynamics, my ketone dynamics. I actually have ketone data down to the minute from my blood, all right? To look at how rapidly I can change and how we can use that data to do a few things, all right? We have used Curate to dose my exercise intensity. We have used Curate to dose difficulty for cognitive training, including for brain cancer patients, by the way. We just finished that trial. And in so doing, I've actually used this to then optimize the dose of my exercise, right? To ensure that I don't overtrain, to ensure that I don't get injured. We use this to train pilots now for their multitasking, right? This Curate algorithm is agnostic to indication as long as we can modulate the difficulty or the dose going in, and we can record an actionable marker going out, all right? And so we do this for a number of my markers, right? I'm not gonna get into this too much. This is my microbiome dynamics. I've probably got about 26 readings of my microbiome over time as a function of 3 meals a day, as a function of 24-hour fasting, 48-hour fasting, to understand what the right fasting regimen is for me, to eliminate certain microbes I don't want, and to promote the presence of microbes we do want, all right? If we look at my metabolism on the left, and I'll get into where that is published, I was able to monitor my ketone dynamics for months at a time, fascinating data to see how repeatable but how nuanced my readings are depending on my sleep, my diet, my workouts, all of the above. I look at my sleep regularly now. For a person who's never cared about sleep, it's fascinating what this experience has done for me now. One thing I will note, I never expected, and I think what matters for a lot of people in the audience, I have a 12-year-old and an 11-year-old at home. And when they see their dad prioritizing his sleep, they actually now prioritize their sleep when most of their friends are sleeping like 5 hours a night. And for all the people in the audience, we do know that young people are getting sicker earlier at unprecedented rates. Metabolic health issues, sleep issues, they're related. We know that young people and GI cancers are skyrocketing. There's a lot of factors that go into this that go beyond sleep, but it was a pleasant surprise to see my kids care based on my own study. People ask me all the time, if I'm not eating for 20 hours a day or 48 hours, am I a walking zombie with no energy? I actually still do pretty well. For my age range, through this entire journey, I've been able to reach grip strengths far beyond what I thought was imaginable. It turns out my performance metrics put me in the top 1% of 20-year-olds now, in fact. All right? So to wrap things up, got a couple minutes. I actually did publish this study on myself as a follow-on to a lot of the work that we do for our patients. In this paper, I had to get IRB approval. Of course, and at our university, when they started the IRB approval for me, they quickly learned that there had never been a professor at our university who was their own test subject. And so they actually floated this IRB to our Ministry of Health. They had to do a secondary approval of that IRB. Singapore is efficient, super efficient. If you haven't been there, within about 3 weeks, the Ministry of Health got back to us. The IRB did take its time though, okay, because again, it was unprecedented. The IRB, this was a retrospective study on myself. I had already done the work. I paid for it myself. I already did all the work. And the IRB astutely said, we're pretty sure you're going to continue working on this stuff. So if you do it, please get a prospective IRB approved so we have better oversight, which I did. And in this paper, by the way, I do disclose that I am the subject. All right, and I promptly sent this paper to my insurance company and asked for a discount. Right, but and I'm still waiting. It's been like a year. I'm still waiting for an answer. But for the next study, we'll hope for better outcomes. All right, so I kind of took you on a little bit of a journey in my 20 minutes. Our Curate algorithm, we have prospective validation every day. We've got about 10 trials going on, all prospective, and that led me to the journey on my own metabolic health journey. But I will say that through all of this, I've learned that, you know, in the world that we're living in right now, we know that people are getting sicker earlier. In Singapore, we have a fascinating issue, right? Our life expectancies are super high, but our health spans are not quite as extended, right? The last 11 years or so of life are not spent well. And that's a common problem around the world. And so I ask people all the time, right? What are we really willing to do to future-proof our health when we talk about the importance of prevention, et cetera? And the answer is not that much, right? Healthy people are very efficient at becoming unhealthy. We know that, right? But we're willing to do anything it takes, including all the AI we have to past-proof health, right? When we're already sick, right? So the study that I'm working on is as much a journey in technology and metabolism as it is on behavior, behavioral economics, et cetera. That's why my institute is mostly social scientists now. Right, so Arcella, thank you for having me. It's always a privilege to be here. The trip is always too short. I'm always happy to keep in contact with everybody. I do data dumps, and I release some of my data here and there when I find something new. But thank you for having me. Enjoy the rest of the day.
Okay, maybe we can go to having a short discussion before the best oral. Is there any question?
Any question from the floor? Arcella says that we have a new pope, but we don't know exactly who is the person. Alberto, question on the Pope? No question on the Pope.
So I got your same bracelet, the fit tracker, Dean. I got your same fit tracker, recognize the skin, and I'm gonna say why I haven't got you as fit as you. So I'm gonna say, but no. The question is, do I understand correctly? So when your patient walks in, you kind of do some probing by changing a bit the dose of the treatment, and then you're gonna adjust, you know, the curve of the patient. So is the rational base that then people because there's been a lot some work about game theory and evolutionary theory for the tumor. So is it the change of the probe just to understand that maybe a lower dose will target the most resistant population, which might not be, you know, the whole tumor? Is that the biological rationale, or is there's something else?
It's a great point. There's a lot of really exciting work done on evolutionary dosing. And the evolutionary dosing modification guidelines are a little bit different than us. It's still a little bit generalized, right? Where if the marker changes by this much, you do this. It's still quite rules-based, driven by the marker. Our rule is based on the model. Our model is now fixed. There is no more training of the model. but the coefficients are patient-specific, and the coefficients change over time. So for us, it's not so much about trying, it may we do the optimization, then we go back to find out why, right? We kind of, in parallel with the dose modification, we can go find out through molecular analysis, et cetera, why is this happening? But I will say that when we do our dose changes, a constant thing that we find is that synergy, as I briefly mentioned, which is not an overarching reason, but I would say it's not uncommon that we find that patients are not often, I won't give like whether it's more or less, patients are dosed with combinations that for that person at a given time are antagonistic. We see it. And the reason we know it is because we're able to change the dose dynamically and we can see the interplay, right? And by adjusting the dose, we know that synergy is dose-dependent, time-dependent, and patient-specific. So the kind of simpler explanation is for many patients, we re-optimize their synergy, but the actual molecular or cellular reasons behind that are varied, right? And so that is one reason, but there are others as well. But the synergy alone at a macro scale, we can clearly see there are patients that get antagonistic combos at any given time.
And you mentioned you're doing that with drug. Did you try also to digital twins for radiotherapy or combination of radiotherapy and chemotherapy, or have you focused on?
Great question. Radiotherapy, we wrote a paper on it, and then we're preparing to launch a trial. For the drugs, first of all, we are agnostic to drug class. We have a trial finished for immunotherapy, we do targeted therapy, as long as the dose can be modulated, and as long as there's a marker that the doctor will believe. Or markers, and we work with companies, et cetera, ctDNA, all of the above, in parallel with the markers. We don't only do dose modulation. We also use the same quadratic function to design combinations for patients, and it is not based on drug sensitivity on plates. I will add that that component was spun out into a company, and that data is fascinating. Our positive and negative predictivity of our combos is over 80% in both directions, and we just launched it at the Mayo Clinic. So that one's actually implemented and deployed, right? And the reason is we are not looking for in vitro sensitivities to make combos. We take a set of experiments, we run real experiments on the patient samples, and we comb a parameter space. 20 drugs, that's over 1 trillion possible combinations when you look at the doses too. With our experiments and our AI, we will find combo number 1 out of 1 trillion, combo number 1 out of 10 trillion. We're looking for a different answer. And it's for that reason why the NPVs and the PPVs are so high, and that's why it's deployed already. Thank you.
Thank you. I have a question for Marina. What do you think in the flow process that you show, that target identification, drug identification, or model, what do you think it is the most difficult part to improve? I mean, do we have a good target, or do we have good models, or do we have good drugs? Because there was a paper that was showing that actually we are in a winter of drug discovery, because we are not able to find new targets, actually. We are just focusing, and also in the trial we see that all the molecules are always on the same target. Do you think that this is the main problem, or the right drug and the right model can be also other problems?
So I had this discussion with Charlie Swanton, because was always also my question, and he says that at least in lung cancer there are still a few that must be discovered. But the process can apply not just to the tyrosine kinase inhibitors or to the targets, but can be done, for immunotherapy, for new other possibilities. So potentially can apply to everything, and it's not said that you have to create a tyrosine kinase inhibitors. You can create a glue, you can create, whatever. So nanobodies or...
Because we have a 10 anti-TIGIT, we have always me-too drug, but we are focusing always on the same target.
Yeah, but again, I think that this is also part of the reason why if you find a target that potentially can apply to a bigger population, you are, multiple companies are there.
Yeah.
And nobody is on the, how many energy one we have? One.
Yeah. Okay. Sabina, you had the question?
Yes, I have a technical question. I am worried about the possibility of substituting our figure with the co-scientist, but beside that, my question is whether with your system you're also able to predict the capacity of a target of a molecule. I'm thinking, for example, to transcription factor, to interact with some portion of DNA and therefore to identify molecules able to interfere with the binding of these molecules with the targets on DNA.
So I think that the basic scientists will not disappear, but I think that as we will be different, they will be different. So it is possible that the co-scientists or foundational models for cancer will help you to arrive faster to the solution, and now you have to stay in the lab and doing thousands of mice and whatever, and maybe you can be more focused to show your hypothesis. And then clearly I think that we need also more a multidisciplinary approach that can be also the spatial part, can be the integration of multiomics. So maybe it's not just about the genome, but is about multiple strata, and clearly more and more the AI models will arrive, more precise we will be.
Okay, I think we stop with the discussion. Now we have the best oral, number 2. So I'm happy to call Flavia Jacobs from Italy, and she will present accelerating translational research with synthetic data, enhancing multi-state digital twin models for disease state prediction in breast cancer.
Okay, so good afternoon to everyone. First of all, thank you to the scientific committee for having chosen our project. I'm super happy to be here today to present our project. My name is Flavia Jacobs, and I am a medical oncologist, so please be kind with your question. And I'm going to present you, and I currently work here at in the breast cancer unit, but I'm going to present you the project, which is a collaboration that I developed during my period at Humanitas Research Hospital, and it was carried out with the collaboration of the artificial intelligence team at the Humanitas. And I want to thank you, the co-authors of this project, Elena Zazzetti and Saverio D'Amico, for their leadership in the project. So we know that the breast cancer is the most frequently diagnosed malignancy among women worldwide, and the evolving therapeutic landscape requires the need for a personalized treatment. So real-world data from electronic health records can be can help us to do this. However, problems such as privacy and data scarcity can limit their utility. And this setting, artificial intelligence and synthetic data can be a promising solution to overcome especially privacy concern, support data sharing, and augmenting existing data set. So the primary objective of this study was to investigate advanced generative model to generate reliable, privacy-preserving longitudinal synthetic breast cancer data to replicate disease progression, treatment patterns, clinical outcome. And as a secondary objective, we want to test the ability of synthetic data to accelerate translational and clinical research. We structured the methodology in 4 steps: the cohort identification, the generative model we use, the synthetic validation framework developed, and the 3 different experimental setup. The I2B2 is a data warehouse that was established at Papa Giovanni 23 in Bergamo, and from where we extracted information about demographics, tumor characteristics, and treatment and clinical outcomes for about 1,050 patients, both HER2 positive and triple negative, over a 10-year period of observation. And to simulate longitudinal electronic health record data, we explored a range of different generative models. For example, generative adversarial network that are extremely powerful for generating highly realistic data, variational autoencoders, and transformer-based models such as Halo, GPT-2, Llama, and Mistral. They are good, designed for natural language. They have shown promise in generating also clinical sequence and especially capturing the complex dependency between the features. So the model selection was based on achieving a good balance between fidelity, privacy, and utility for our application. The synthetic validation framework that we developed and that we call SAFE was evaluated basically four main aspects: the fidelity with metrics, different metrics for both discrete and continuous data, the correlation with correlation accuracy. Privacy was measured via a membership inference attack to be sure that the synthetic data generated do not replicate or resemble the training data. And for the utility purpose, we compared the Kaplan-Meier survival curves for real and synthetic data via a logorank test. The three different experimental setup are: in the first one, we want to create the reliable and privacy-preserving longitudinal synthetic data for the integration in our dataset. As a setting B, we want to augment a multi-state digital twin model with synthetic data to improve prediction accuracy for disease, for breast cancer disease state transition. And finally, in setting C, we asked ourselves about, is a proof of concept, what about using these synthetic data generated for a clinical question and, for example, as a comparator or arm in a clinical trial. Coming to the results. In setting A, we successfully created a high-fidelity synthetic dataset for the integration in the original dataset. And with the safe validation, we demonstrated strong performance in both fidelity and correlation. Fidelity measures how closely these synthetic data actually replicate the distribution of real clinical data, and the correlation preservation showed us how much the variable like treatment patterns and tumor characteristics were maintained in this synthetic dataset. Regarding the privacy, we assessed the secure privacy via, as I said, membership inference attack, and the results we had about accuracy, precision, recall were all about 50%. That it means it's basically similar to random guessing. So it was not possible to track back this patient from to the real one. And for the utility part, we used Kaplan-Meier curves to and we obtain a significant p-value, so there was not a statistically significant difference in survival for this patient between the real and the synthetic one. In the setting B, regarding the disease state transition diagram, we focused on modeling these this transition model from about 1,000 patients who had available state transition over time. These state transition were based on surgery, therapy, hospital contact, and at each time point in the data set, we assign a different disease state, and we track how the patients move between each of these states. And to predict this transition, we use a deep hit model that is basically a deep learning approach that is specifically developed for survival analysis with competing risk. What we can see here is that when we use only the real patients, the concordance index was good, but when the dataset was augmented with synthetic patients, and it was better. In particular, it was the best results was achieved with 3 times more synthetic patients comparing to the initial one. And also the models trained on synthetic patient predicted disease state transition as well or even better than real data, because we can see a reduction in the average confidence interval by about 70%. And finally, the setting C, where we asked ourselves what we can do with also this synthetic data. We started from very popular, I would say, trial in breast cancer that maybe if there is some breast cancer clinician, they know that is the APT trial that led to, this is a phase 2 study, but this is a single arm study, and it tested the escalation strategy of paclitaxel and trastuzumab for HER2 positive, not negative early breast cancer. However, as I said, this is a single arm study that tested this combination, but there was not a comparator arm. So because in our dataset we had both patients who received this Tolani scheme and the standard of care, we augmented both these patients with synthetic data and compared like in a synthetic control arm, and as you can see, the curves are basically the same. So, coming to the conclusion, we can say that the synthetic data can be integrated for scalable and anonymized data solution. Also, augmenting this data set can improve predictive model performance, and the synthetic data can address challenges, as I said, like data scarcity and class imbalance, and even they can be useful for like the creation of artificial control arm for the clinical trial. And I just want to thank you, and just to say that this paper is under revision in an important journal, so finger crossed, and this poster will be presented next week at ESMO Breast. So thank you.
Thank you so much, Flavia. Unfortunately, we have not enough time for questions, so now there will be a word for Dr. Jacobs, and then an important announcement from the ISAC steering committee. So the word, Flavia.
No run.
Okay, so please, I know that it's we are all tired, and I will ask other 10 more minutes. So I invite here in the podium the ASAC steering committee to join with me. I know we don't have all the chairs, but please come all here, Loic. So we leave this for the end. maybe some of you have seen that on 26th of February we have launched in different social media and the formal launch, let's say, and press release of this new society that we founded, which is called ESAC. Just to outline very two few words. So ESAC, it's a new society. It will be focused on AI in cancer research, and just the main message is that wanted to collaborate with different other societies, and the needs for this society was because we wanted to put together exactly as we are doing in this meeting. Scientists, for example, such medical oncologists, but from different fields, pathologists, radiologists, but also engineers and other type of specialists. So now I just giving to the word to two people from this society that have worked a lot and contributed in this very small presentation, 5 minutes. So Giovanni Squacek. I don't know if everyone knows, but Giovanni Squacek is let's say, a pillar of this society. He's a founder of the society also. He used to work until 1 month ago in this institution for 7 years, and now he's working, let's say, he's back in France, and he's working for himself, but also helping in the society. So, and at the other hand, we have Narmin, and Narmin, she works as a postdoc, works with Jacob in Germany, and she's the project officer, the scientific officer, sorry, of the society. And I wanted to give to them both the word for few slides that we have prepared for you. So the key word is that from this second, after 5 minutes, we need you all to be member of this society, and we will show you how.
Okay. I don't know if this is working. This looks like a weird job interview, but it's not. And thanks to the assist and me being in France, because I'm Italian and French, so I'm very keen on the importance of wine after a long day of presentations, and I'm standing between you and the wine at the aperitivo and dinner afterwards, so we'll be short. As Acela mentioned, yes, this is quite a big moment, I think, for all of us, because we are introducing this new scientific society. You may have seen it on LinkedIn. All of you are members already of some societies, I'm sure, in some shape or form, but this is a brand new one, so we will be counting on your support as well. The slides are quite busy, so I'll go over them quite quickly. You've seen, the full name of the society, ESAC. It's a long one, it's a mouthful, it has a lot of long, complicated words, like interdisciplinary, but we're very insistent on keeping it in the title because it's part of one of the core aims of the society, which is to build a community of AI experts, researchers, AI enthusiasts, even medical oncologists, imaging specialists, and anyone that's involved in the field of artificial intelligence, not just for oncology, but for cancer research in general, which is why we have that very long title. We are multidisciplinary by design, even in the steering committee. You've heard some of them today. You'll hear the rest, I think, all of them tomorrow. There's a wide range of different professional backgrounds represented here of medical oncologists. We have radiologists and pathologists, and engineer Ivani in the background as well. And we wanted this new society to reflect also this diversity, because we're in a context where everyone is doing AI in their field, which is clinical oncology, radiology, pathology, but there's not a group of experts that unites these different backgrounds in one organic setting, which is the main idea. So it's inclusive, it's community building. We really focus on bridging with different research consortia, different networks, and the different projects that the steering committee leads, and hopefully with more that will come out saying that they're interested in joining forces with the work that we're already doing. The other two core objectives are to give and create a platform for collaboration, which also goes for education. We've heard the word education 3 times in Vanya's talk alone at the end in the last slide. But we're very aware of the importance of promoting AI literacy, of sharing knowledge, resources, different approaches. We've heard a lot of them. So we're also very aware of the importance of setting up an education platform that will allow on one hand, cancer researchers or people involved in the cancer field to get more familiar with AI methodologies, and vice versa for AI experts to be more aware of the specificities of a cancer field and on how to better interact between these two worlds, which is what we've been trying to do with the conference for the past 3 years, but now we're taking it up a notch, let's say. And the last point is to promote responsible, transparent implementation of artificial intelligence in the clinical and research setting, it's been a long day for me as well, through different working groups that Nermin will present to you with a focus on other key aspects that we defined all day, which are transparency, explainability, but also safety, accuracy, ethics, and making sure that everything is done according to regulations and implemented properly. This is a very long slide. It's a bit more detailed version of what I was mentioning before, and it's a bit more concrete objectives of what the society plans on doing in the coming, from now onwards, because we're brand new, but in the coming weeks, basically. So building the community, as I said, connecting professionals, launching the working groups, advanced education. We're going to have already some events that we'll be publicizing at the end of the presentation. Contributing to e-policy standards. These are also fields that we have noticed. The European Commission, until recently, has not, for instance, interacted with experts in the field, but discussions are mostly on high-level ethics implementation guidelines, but there's been limited interactions with cancer researchers or AI experts in the field, and strengthening the impact of these methodologies in the clinical setting. And I'll finish by a virtual group picture, I say, with just to give you an idea also of both the fact that it's interdisciplinary, but the fact that it's all pan-European, because you see there's, I didn't count them, I should have. There's a lot of different nationalities and workplaces. The ones on the left are the members of the Initial Steering Committee, which is in place for 3 years. We've settled since the end of March. There will be some elections afterwards on a rolling basis. Estelle is going to be the first president, with Jakob that's kindly accepted to be the president-elect for society. So according to our statutes, the next president. We also have Mireia, who sadly isn't here because she's, for happy reasons, because she's expecting from Cambridge as a general secretary, and Elena was here as our treasurer. My 5 minutes have expired now, so I'll give the floor to Narmin for the rest of it.
Thank you very much, Ronnie, and I also want to thank all of you that you stayed until now. I will also talk not that much, but I would just want to, as Ronnie mentioned, so we are interdisciplinary, the interdisciplinary group of PIs, and also we built somehow interdisciplinary working groups, as we are saying. So for now we have 8 different working groups and 4 committees, somehow covering all LLMs, pathology, radiology, so most of the talks that you have heard here today, and it will continue, of course, tomorrow. So I would like to mention that just take out your phones, because like this slide and the next 2, there will be like QR codes and some that you need to scan, and also like take picture of this, so that you can keep in mind like what kind of working groups do we have in our society. There will be like some paper forms available here, so please take them, write down what is your interest, share your email with us, so we can later on just contact with you if you are interested to be involved in any of these working groups, or at least in the committees. This will be like the paper version form. I will share like all of them with you. But as Arcela mentioned, so that's like the most important slide and most important QR code that you need to scan. So this is like the QR code for you to be the member of the society. Sorry, I'm talking about wrong.
No, sorry. It's the,
is it like the?
I think it's the, it went out.
Okay, no.
Oops. Yeah, this one.
Okay, so sorry for that. I was talking about this slide. This is the important first QR code. Please first scan this one. So I think you all know why you should join it, but also there are like the benefits. We will provide very useful webinars and training courses, including somehow all the working groups that I mentioned. So it would be very useful for you. It would be like you will get the priority for the workshops and events that the society will organize in the future. And of course, like you will be part of this interdisciplinary group. You will have the chance to talk to all the leadings of AI in cancer research, and somehow be always involved in the news and activities that the society is doing. And we somehow offered like the early bird discount for the membership, so just don't miss this chance and register now for this. And hopefully now we will go to the last slide of mine as well. And I would like to use this chance to also talk about the summer school that we are going to have this year, June 13 to 17. And also I would like to thank the local organizers, especially like Helena Lindoro, for amazing job that they are doing. We are all looking forward to be in the summer school. Actually, I feel like everyone will be there from STR committee. And we are also like expecting you, if you're interested, there will be a lot of interesting talks about different topics that you have also listened to them. There will be like workshops, hands-on sessions in this amazing summer school, also especially in Corfu in Greece, so that's also important to mention. So this is the second QR code that if you are interested to register, please do that and join us there. Most of us will be there and we are looking forward to have you there. And saying that, so this is the last slide. This is the link to our LinkedIn, to our X account. Follow us, stay in contact, and as I said, we have like this paper forms. Please fill your emails if you are interested in any way of interacting with us and being involved in a society. We will come back to you and send you emails later on. Did I miss anything? Did I forget anything?
Yeah. So no, the only announcement that I'm, let's say, from the next year, I am saying that unfortunately, not unfortunately, but I mean, this Congress will not be anymore my Congress. So, and can you go to the, so I wanted to launch the save the date for the next year, because will be the 4th edition of AI for oncology and cancer research, but especially this will be next year, the first ASAC annual meeting. So I'm very happy. I think that we really need education, but this is such a big, let's say, event in education. I think we have to do few of them, let's say, but and this is why let's say, we all decided to put all the efforts together. And since, as Jakob mentioned, maybe I can leave him the floor for 2 words, but he mentioned also before that historically we started this. So I think that, no, this is the right moment and the right, let's say, Congress to put together all the ASAC society. And just 2 words for it.
Yeah, thank you very much. I just would like to wrap up all of this by saying a big thank you to Arcella, who's really the mastermind behind this. And I think the whole society evolved very organically, because, as you know, this conference has been a huge success now. Repeatedly. There's also other events that Arcella is putting together. Also, others here in the steering committee are involved in putting together summer schools, events, etc. And now we're just teaming up and putting it all under one single umbrella, which is much more professional and has much more potential to grow. Thank you, everybody, for supporting this. Please approach us with any questions. And now again, thank you to Giovanni, Narmin, and Arcella.
Yeah. Thank you again. So just to specify that also next year will be in Milan, this meeting, just because it's the first ASAC, but this meeting probably will change in different states from the after 2 years. However, the friends will remain the same, so we'll still invite all our friends. I want just the last word from a technical point. Do we have the Pope or not? Because we were waiting for the Pope. So let us just have 1 minute to see if the Pope is there, because in Rome, you know that in Italy it's very important this moment, and the Pope is yeah. So we have obviously now the posteritivo, which means that we have the second poster session. Don't forget that tomorrow we will have other 4 prizes on best poster, except from another best oral and different awards. And yeah. If you, I don't know, we can take the aperitivo, or we just I was so at 7. Okay, so go for the aperitivo. Okay, but leave it live, please. Okay, thank you. Thank you.
Jakob.